Good morning, good afternoon, and good evening, process from various parts of the world. Let us start the today's sessions in time. Anjana,
Yes, sir.
Anjana, please introduce the chair, Professor Somesh Kumar sir, and thereafter help him for further proceedings of the session, please.
Of course, sir. Good morning, good afternoon, and good evening to all the participants. We are moving on to the technical session 22 of WSTA 2023, which is a special session in honor of Professor A. Mathai that will be chaired by Professor Somesh Kumar from the Department of Mathematics, Indian Institute of Technology, Kharagpur. Dr. Kumar is deeply invested in statistical decision theory and inference, measures of entropy and reliability, estimation in restricted parameter space, and limit theorems for dependent models, among others. He has over 3 decades of teaching and research experience and has supervised several doctoral and master's dissertations. He holds various editorial positions in national and international journals and is an elected member of the International Statistical Institute and the National Academy of Sciences, India, among others. Professor Kumar has an admirable publication record with over 120 research papers published in reputable international journals and book chapters covering topics including two-stage and sequential estimation, problem of classification, and so on. He has received several prestigious awards for his work, including the Bharat Jyoti Award of Inter-International Friendship Society in 2011, the Platinum Jubilee Lecture Award of the Indian Science Congress Association in 2016, and Professor K. S. Rao Best Research Award from ISPS in 2022. As an educator, Professor Somesh Kumar has taught a variety of courses, including probability theory, statistical inference, multivariate analysis, real analysis, and many more. In addition to his academic pursuits, Professor Kumar has a keen interest in the contributions of ancient Indian mathematics and regularly delivers lectures on this topic. His video courses on probability and statistical inference, and statistical methods for scientists and engineers are available on platforms like NPTEL and YouTube and have garnered millions of viewers worldwide, myself being one of them. So it is with great pleasure and honor that I invite you, Professor, to chair the session. Without further ado, over to you, sir.
Thank you, Dr. Anjana, for a very cordial introduction. Um, Let me take honor of introducing Professor David D. Hanagal, who is the invited speaker for this plenary session on Professor Mathai. Uh, Professor Hanagal received his bachelor's and master's degrees from the Karnataka University in 1980, and subsequently he did his MPhil and PhD from the University of Pune, which is now called Savitribai Phule University, in 1992. And subsequently he worked for some college, and then he moved to the Pune University, where he spent his entire career. And he is emeritus professor in the University of Pune Department of Statistics. In between, he had several stints to universities abroad. He has visited the universities in Mexico, University of Düsseldorf in Germany, and in USA as visiting professor. He has published more than 125 publications in various very reputed international journals. Besides this, he has also written two books. One of them is Introduction to Applied Statistics, a non-calculus based approach, and second book is Modeling Survival Data Using Frailty Models. So his main focus of the research area is the reliability models, stress strength reliability, survival analysis. So especially the work on the lifetime distributions like exponential, Weibull, and other distributions, including multivariate and bivariate and multivariate models in such cases, and reality models. He has guided large number of PhD students. I think around 10 PhD students he has guided, who are now in various parts of the country. Today he will speak on the correlated compound Poisson shared frailty models. I request Professor Hanagal to deliver his lecture now.
Okay. Thank you very much, Professor Somesh Kumar, for a very nice, cordial introduction. I will upload the talk. I am audible to all, no?
Yeah, Professor. Audible.
I will just upload the talk. Is it visible?
Yes, it is visible. You can just make it full screen. Maybe just, yeah.
Full screen. Okay. Just control L. Is it okay now?
Yes, definitely. Yeah, it is nice.
Okay. All right. Thank you. The title of the talk is Correlated. First of all, I thank Satish Kumar for inviting me to deliver a talk in the honor of Professor A.M. Mathai. It's an honor to me to speak in the honor of Professor Mathai, a very good, well-known mathematician and statistician. And it's not that related to his area of research. Okay. The title is Correlated Compound Poisson Frailty Model. This is a Frailty model. Okay, this is a branch of survival analysis. That survival data is time to event data. It contains censored observations. It may be left censored, right censored, interval censored, current status data, or some other different types of censoring are there. I am using the random censoring, random right censoring in this case. And I will introduce what is the share frailty and correlated frailty. Okay. It is a unobserved covariates or some hidden heterogeneity involved. Or you can say a random effect model. See, there are so many covariates we can't observe, we can't measure it. And sometimes even though there are observed, we don't know the significance of the covariates. Okay. This we neglect or discard, or sometimes we just ignore it while doing the analysis. And this will be a random effect. For example, I can give example of genetic factor or environmental factors. Genetic factors, it is very difficult to get the idea of which genetic are uh, significant impact on the lifetime or environment factor. Sometimes it is not possible to measure also in that case. See, for example, in the family, the twins or the paired organs, okay, they are having common risk because they are in the same human body. They have the common risk, okay, and maybe within the family, they have a common risk within the family. If family changes from one to another, then there will be a change in the risk factor. Or if you take the group of patients in the hospital, if you consider different hospitals, okay, hospital centers, the risk changes from hospital to hospital, okay, because the apparatus used, doctors, staff, everything, they share the common risk. Okay? That is a shared priority model. Correlated means there are, say, for example, twins. Okay, the first one and second one, they have a common risk, shared priority model.
Professor Hannagal, your slides are not moving actually.
Okay, I'll just. All right, sir. It is the outline of my work.
Okay, sure.
Okay. I just explaining the surveillance. I'm coming to this before I just giving some introduction of the correlated priority model before coming to this slide. Okay. The correlated, what you see here in the twins, they have shared common risk also. Apart from that, they have individual risk factors, say Z1 and Z2, where Z1 is a risk for first twin and Z2 is a second, like that. And these two are correlated. This is a difference between shared and correlated priority. Okay, I'll start with the basic concepts of starting with Cox model. Okay, this is equation number 1. H0 is the common baseline hazard. X is the vector of explanatory variable. Beta is a vector of corresponding regression coefficient. This is given by Cox in 1970. This is used extensively in the literature. And the problem here in this model is we assume the homogeneity among the patients or individuals. The question of homogeneity is homogeneity is a questionable here. How far they are homogenetic in nature. There may be some random effect involved, maybe genetic factor or environmental factors. Okay, that we are adding. Okay, extending this Cox model to priority model. Say shared priority I already explained. Lack of appropriate tools to measure, too many covariates to consider, and research are not aware of influence of the potential covariates that might exist. That is the existence of genetic factor and all other things. Okay, these are the reasons. Sometimes we ignore, and that will create a problem, and we can't do the proper analysis in that case. Okay, what we do, we are extending the Cox model in this case. Some unobserved covariates U. I'm introducing this here, e raised to u prime beta. Okay, beta star. Beta star is a regression corresponding to u. That is unobserved covariate. I can write Z as this term, e raised to minus u prime beta star. Then you can have condition survival function, because you know the cumulative hazard and survival, this relation, integrated hazard H0, and integrate over Z, you get unconditioned survival function. That you can write in terms of Laplace transform of Z. Okay, Z is a priority term here, that is a random effect, that is having some known distribution. Okay, that will come later, which distribution it follows. If you consider two component system, then it can be written in this way. Okay, H0 T1, H0 T2. These are the cumulative corresponding to lifetime 1 and lifetime 2. Say if it is a paired organ, maybe any kidneys or eyes, ears, whatever, paired organs, T1, T2. Okay. Very first it was given by Cloton, then in 1979, Whipple, he gave the name Friety for unobserved covariate. Okay, that is was the thing very beginning, 1978 onwards. Okay, this effect or Friety is not directly estimated from the data, but instead is assumed to have unit mean and finite variance. We are taking unit mean because of there is some problem of non-identifiability in the model. That's why we consider the Friety has a unit mean and finite variance. See what happens if you ignore Friety. Suppose there is a heterogeneity involved, okay, but we ignore. Whatever decision we do, analysis and other things, that will be inappropriate, and decision based on such models will be misleading. And whatever we obtain, AIC, BIC, DIC, ACAICA information criteria, Bayesian information, deviance information here, it's model selection criteria. That will increase if we ignore Friety. Okay. And whatever decision is based on the model without Friety will go wrong. And there are some consequences of ignoring Friety model, Friety term. What are the different Friety models in the literature? Gamma Friety, inverse Gaussian Friety, positive stable Friety, power variance Friety, compound Poisson, compound negative binomial, compound, okay, this is the piecewise gamma, correlative Friety, additive Friety. There are a lot of literature on the different types of Friety models. I have also some other papers based on some other Friety models. Now, what is compound Poisson Friety? This was given by Allen in 1988-92. He introduced compound Poisson distribution as mixing distribution in the survival model. And see, there are two random variables connected to this. That's why it is called mixing distribution. Some examples are there. Death rates for the cancer patients, meaning that longer the patient lives beyond a certain time, the more improved are his or her chances. Diverse rates. And these are the examples of compound Poisson Friety models. There is one additional feature that is in this is the integrand under intensity is finite. The distribution is defective. There is some zero susceptibility. It has zero susceptibility. That means the individual will survive forever. Okay. There are some examples. Some patients survive their cancer. Some people never marry. Some marriages are not prone to dissolve. In medicine, there are examples of disease primarily attacking people with particular susceptibility. For instance, genetic kind, other people having virtually zero susceptibility of getting disease. Okay. There are some fertility examples. There are some couples unable to conceive children and other things. Okay. And in unemployment data also, some people never get the job, unable to get a job. These are our zero susceptibility. The random variable takes the value 0 in this case. All these examples. Okay, there are some, these are the advantages that we are taking into account. Zero susceptibility and some, this is a combination of discrete and continuous here. 0, when Z equal to 0, it will be discrete in that case. Okay, this is a definition of compound Poisson, x1, x2, xn. These are IID, and n is a random variable here. Random sum of the IID random variables. Xi's are gammas, and n is a Poisson distribution with parameter p. Can be okay. This is a and z equal to 0 is e raised to minus mu. Okay, this is n is a Poisson with parameter mu, and these are IID, gamma, and other things. Okay, this is the PDF of compound Poisson distribution. It's not compound, it's gamma, sum of the gamma, and this is for the Poisson random variable. We are combining these two, and this gives density of Z. Okay, compound by now. And write it here. It has 3 parameters now. So we are interested in obtaining Laplace transform. We are mainly using the Laplace transform, while because this is a convenient way to define a priority models in terms of Laplace transform. This is the Laplace transform of gamma, and the Laplace transform of Poisson is here. We combine these two, and we get Laplace transform of n in this is the argument minus log of Lxn. Okay, combination of 2 Laplace transform, and we get the Laplace transform of compound Poisson. That is final form. That is the form. I am not going in detail the mathematical formulas. Okay. Now, moments we can obtain because we need mean and variance. Mean we can obtain from this Laplace transform by differentiating. We get the mean equal to this, and second moment we get the variance will be this form. Now there is a problem of non-identity in the model. Okay, that means we assume Z has expected value 1 in order to resolve this non-identity problem. And when you take Z equal to expected of Z equal to 1, and we have a restriction in this here, u, gamma, and nu. Okay, that will be nu equal to this is a restriction, and under this restriction the variance will change from here to this one, and there is a change. There will be a change in the Laplace transform under this restriction, that is here. Now we have only 2 parameters, mu and gamma, mu, gamma, and only 2. Earlier there were 3. Okay. Okay, this is the final form of Laplace transform. Now correlated priority. Okay. I already explained the difference between correlated and shared, because twins example, if you take the environment factor, okay, the twin 1 and twin 2, the environment factors may be different, and some behavior may be also different. Okay, some genetic factors may be same, some are different, because the nature and behavior of 2 twins are not same all the time. That is the difference. That means there is another heterogeneity or another risk factor or involved in that random effect model. That will be a change in the between the 2 twins. That I am taking Z1, Z2. Okay, that is here 2 random effect models in this, and this Z1, they are correlated, and you can have the bivariate survival function given Z1, Z2, and after integrating over Z1, Z2, we get this one. Okay, this is the bivariate survival function after integrating over bivariate. I am just taking the one extension from univariate to bivariate. How do you extend from univariate to bivariate with when you know the univariate distribution? I am just using the Laplace transform of bivariate, and these are the Laplace transform of univariate. Okay, and correlated Z1, Z2 are correlated with rho is the correlation coefficient between Z1 and Z2. Okay, and rho is always greater than 0 here. It won't take negative value in this equation number 9. And when rho equal to 1, it leads to shared priority model. That means shared priority model is a submodel of correlated priority model here. And one can extend it to by a multivariate also. When rho equal to 1, it will become shared fatty. When rho equal to 0, they are all independent. Jumno ZK. All right. This is a Laplace transform of compound poison. Now, bivariate survival function using the bivariate Laplace transform, H01 and H02. These are the cumulative hazard of 2 lifetimes. That is here. Okay. I am just using eta as e raised to beta prime xi covariates. Now, if you take without priority, then this is the simple form. Here, T1, T2 are independent in this case. I am just using the baseline distributions, two baseline distributions. One can also have a semi-parametric, non-parametric distribution as a baseline. Okay, that can also be done. I'm taking two baseline. One is generalized Weibull. Okay, that is the form of distribution function, cumulative hazard and hazard rate. Okay, that is the thing. Okay, there are so many different submodels in this Weibull, exponential, and so many. And it may be increasing, decreasing, unimodal, bottom, different types. When we change the parameter setup, we get a different type of hazard functions in this case. That is the thing. This is the one. Second one is generalized log logistic. Okay. This is the distribution function, and this is a cumulative hazard, and this is a hazard rate. Okay. For different parameter setup, you get different failure rates, maybe either decreasing or increasing based on the delta values. Now I have 4 models, 2 based on the baseline with priority, another 2 based on the baseline without priority. In all, there are 4 models. These 2 are based on the generalized Weibull and without priority with priority 2021. Similarly, for 2022, they are with priority, without priority, with correlated priority and without correlated priority, like that. Okay. Generalized Weibull baseline, another is generalized log logistic distribution as a baseline. Okay, 4 models in all. I'm using the Bayesian techniques. Okay, you can have this is a bivariate sensoring. I can have likelihood divided into 4 different parts, and both events observed. Only one event is observed, other is censored. The first event is censored, second is observed, second event is observed, and both events are censored, like that. 4 different reasons. You can write likelihood in this form into 4 different reasons. Here n1 plus n2 plus n3 plus n4 is n. Okay. You can obtain f1, f2, f3, f4, differentiating this survival function twice, and with t1, t2, and so both when both are censored. I'm going directly to kidney infection data. Okay. Before that, we also did some simulation work, okay, without using the data in order to check the conversions of the Bayesian estimates. Okay, in the kidney infection data, there are 38 patients. There is each patient has first and second recurrence time in days of infection from time to insertion of the catheter until it has been removed owing to infection is observed. The catheter may be removed for the reason other than kidney infection, and this regard as a censoring. Okay. So the survival time of the patient given may be first or second infection time or censoring time. Okay. After the occurrence of the censoring of the first infection, sufficient time was allowed, that is around 10 weeks interval, for the infection to be cured before the second time catheter was inserted. So the first and second occurrence times are taken to be independent. That is the thing. One can also have dependent also, but here there is a sufficient gap between the first and second, and there is no overlapping of the first uh, and the second uh, lab event. That will not be. That's why we consider here independent. Okay. Okay. There are some covariates we are considering for this: age and sex or gender, whatever. Disease type GN, AN, PKD. Three disease type. Okay. The short form of GN, AN, PKD are here. Okay. And these are the three types of diseases. We are taking only occurrence, presence, and absence of these diseases. Okay. These are indicator variables, three types. And other two are the gender is also indicator, male or female. Age is a continuous in this case. Okay, now we have 5 covariates. That is, the model will be written in this form. Okay. I'm giving some summary of the tables, the results. This is based on the simulation study without using the data. Okay, I'm taking some true values of the parameters and their estimators. The estimators are close to true values of the parameters. You can see here they are very close. Standard error of the estimators, lower credible limit, upper credible limit, Gaveke values, and p values of the Gaveke, and Gelman-Rubin values. Okay, these are the values. What we see here is they are somewhat very close to true values, and the conversion criteria. We have graph also. I have not taken in these slides. They are also very the coupling from the coupling plots and the autocorrelation plots and different plots are there. This is for the model 1, whatever we are given here. The same way for model 3, I'm not using the simulation results for model 2 and 4 because they are without Friety. Okay. Only with Friety, I'm taking the simulation results. Similarly for model 2, model 3, this is for the baseline as a generalized logistic. Similar things we have done the calculation for this. Here also the estimates are close to true parameter values. We can see here for this. Standard errors are also very low, lower and upper limits, Kvk values, p values of the Kvk, and Gelman. This shows there is a conversion criteria is met in this simulations study. Now I'm going for the kidney infection data analysis based on that. Before that, I'm just doing the goodness of fit test, case statistics. These are the p values of case statistics for the model 1 time, first recurrence T1 and second is T2. I'm taking for individually, marginally I'm taking for T1 and T2. Okay. This is for similar. They are very high p value. Then we can say it's a good fit for these two Friday models. Now going for the posterior summary for the model 1. I'm just going very quickly because of lack of time. See here the gamma and rho. Rho is a correlation between T1 T2, that is 0.56. Okay. That is they are correlated. Okay, and gamma and mu. Okay. These are the parameters for the Z1, Z2. Okay. And these are the covariates, beta 1 to beta 5. This is for the age and gender. What we see are gender, the male and female. There is the lower and upper prevalent. Both have a negative sign. That means this is significant. 0 is not included here. Therefore, this is a significant beta 5 disease type PKD. That is also significant. That means absence of disease PKD, okay, that has a lower infection as compared to the presence. Here, females have lower infection as compared to male counterpart. That is a interpretation in this case. This is for the model 1, and model 1 is the or based on the generalized variable as a baseline, and this is without priority but using the baseline generalized variable. What we see here, similar things happened here, okay, and beta 2 is also here significant. All our other COVIDs are insignificant. And for model 3, what you see here, beta 2 is again significant. Same interpretation as we did in the model 1. Beta 5 is significant. Others COVIDs are not significant. Rho is also 0.59. There's a high correlation because rho takes value between 0 to 1 year. Okay. If the rho equal to 1, then this is a share flat model. 0, there is no correlation. That's similarly for model 4, beta 2 is significant, others are not significant. This is for the 4 models. I am comparing all the 4 models now. The AIC, whichever gives the smallest AIC, BIC, DIC, that is a good model, better model as compared to other models. These are all proposed models, and what you see here with priority, generalized variable, that is model 1, this has a least one, AIC, BIC, DIC. Then we can say that this is a better model as compared to other models. And another thing is all priority models, correlated priority models, are better than without correlated priority models. Okay? That we can see here. That means there is a significant effect of priority in the analysis, in this data analysis. You can also have base factors based on these 4 models. Here also you can see model 1 is better than other models. That is the thing. The base factor is high. Okay, there is a strong evidence against the model in the denominator. And now I am comparing all the 4 models, the present 2 correlated models with the existing models. There are some existing models, gamma, inverse Gaussian, positive stable, with the same baseline models, but the different correlated priority models. What you see here, AIC, BIC, DIC. Here also the proposed models are better than the other models. Okay, more or less 80 and 52. Okay. But this first one, correlated Poisson with baseline generalized variable, is better than all other existing models and also one of the proposed model. That is a thing. Conclusions. And here the sigma square you can obtain with using this formula, that is 8. Okay, for this one. Okay, for model 1 this is the value. For model 3 this is the value. Okay. And the correlation between these two is here Z1, Z2 for model 1, model 2. It is here. Okay. And we have already seen beta 2 is significant and beta 5 is also significant. And that is all you can see from this. And what the final conclusion is, correlated compound Poisson probability with generalized variable is that for better than existing as well as one of the proposed model in this kidney infection data. Okay, I think I will stop here. And one can also have semi-parametric models, and one can also have JUD as some process, Poisson process or some other process, some stochastic process. One can also have this also. Okay, thank you very much for patient hearing. Now, it's any questions. Uh, you can ask any question. Happy to answer the questions. Thank you very much.
Thank you very much, Professor Hanagal. Actually, you have given very excellent presentation of this frailty models, and then showing the superiority of the proposed model, and especially with respect to one of the data sets on the kidney infection. So really, it's very useful and I think very informative talk. Are there any questions? Then we can have one or two questions here from the audience. I think Professor Ghosh, are you speaking something? You can switch on your mic. Professor Ghosh, are you asking anything? I think he is mute.
Okay.
I have one question, Professor Hanagal.
Okay.
This is regarding your computation of the base estimates. So actually, I mean, maybe I just skipped a little bit here. Have you mentioned anything about the method of computing the base estimates and then credible intervals?
Yeah. We have used the Gibbs sampling. Okay.
Gibbs sampler. Yeah.
CMC techniques. Okay. All other things are there. That I have skipped it in this, but it is there in the paper. There are so many things to present. That's why I have to skip some of the things.
Yeah. And another point is that is there any specific way of choosing this Bayesian? Like generally in general, whenever we do the Bayesian, we talk about the choice of the prior and this.
Yeah, we have taken the prior also. One is the gamma prior. Okay. Another is the non-informative prior, uniform prior and other things. But both are giving us almost similar results in this case.
Okay.
That means it is independent of whatever prior we choose.
Another just related question is that whether likelihood function writing and any kind of discussion about the likelihood function, is it possible in this case? Because of course it's quite complicated, but is it really worth trying for the likelihood based inference?
Yeah, see, there are different ways of estimation procedures. Okay, one can have classical methods, MLEs and other things, because there are some problems in the classical method. The problem of convergence in the Newton-Raphson procedures. There are so many parameters involved, and the data, if the data is small, again the convergence problem will come. Because in our data, only 38 patients are there. It's a bivariate data, and with sensor data, and how many actually events are there, that is less than 38. And there is some problem of convergence. Better to go for Bayesian. That problem we can eliminate, convergence and everything. That can work with small data also, Bayesian inference.
Okay.
That's why we took the Bayesian inference.
Okay. Yeah, so let us thank Professor Hanagal for his brilliant exposition of this problem. And over to Professor Satish Kumar and Professor Anjana here.
Thank you, Professor Somesh Kumar, for chairing this session, and Professor Satish Kumar for inviting me and sharing some of my talk during this conference. Thank you.
Thank you, Professor David, for your very informative talk. In fact, you are always with us. We are proud of you, Professor. And like Somesh Kumar also, we extend our gratitude to Professor Somesh Kumar for chairing the session. Very nice way and in timely way. Thank you, Professor. Thank you so much.
Thank you.
Thank you both professors. Now let us move to the next session. I hope Professor Muralidharan also joined with us. Professor Akil is here in the group. What about the next speaker is Professor K. Muralidharan from MS University, Baroda.
Good morning to everyone.
Before the Swapna, please introduce the chair and invite the and do the help.
Akil Ahmad, good morning.
Yes, sir.
Yeah, please, Swapna, please. Okay.
Hello, everyone. Hello, everyone. We are moving on to the technical session 23 of WSTA 2023, which is a special session in honor of Professor K.C. Pillai that shall be chaired by Professor Akil Ahmad. Now, Professor Akil Ahmad is a faculty at the Department of Statistics and Operation Research, Aligarh Muslim University, Aligarh, India. His specialization areas include statistics, operation research, and data analytics, and has been in the teaching profession for over 13 years. He has over 19 publications to his credit, including 25 papers and presentation at international conference and seminars. He delivered more than 60 invited talks in different Indian universities and colleges on statistics and software packages. He has guided several students for the award of doctoral degree and MPhil. He has organized several international conferences as a general chair and organizing secretary, and also a life member of Indian Society for Probability and Statistics India. It's with great pleasure and honor that I invite you, Professor, to chair in this session. Over to you, sir.
Welcome, Professor Akil. Please.
Thank you so much. Good morning to everyone. Am I audible?
Yeah, audible, Professor. Audible.
Okay. So, what about Professor K. Muralidharan? Is he ready?
Yeah, he is ready and he has shared these slides.
Okay, but you have not shared about his brief data so that I could read. But anyway, and I know about him. I can introduce him without any brief. Yeah, please. Am I audible?
Yeah, Professor, audible. Yeah, you are audible.
So, okay. As all of us, we know that Professor K. Muralidharan is another stalwart in the field of statistics, especially in quality control. He is one of the most senior member of ISPS and has been contributing significantly in the field of statistics. So, Professor Muralidharan, are you ready? May I request you to please go ahead with your presentation? Professor Muralidharan?
Yeah, he's already in the group. He joined, but probably maybe some network issues. I hope so.
I think he's sharing his screen.
Yeah, he already shared the screen. Yeah. Good morning, Professor. Please. You have to unmute your mic, or there is some audio problem.
Okay, should I mute myself?
No, Professor, unmute the mic of Professor Muralidharan.
Okay.
We can't able to hear him from him.
Yeah,
we can't hear you.
Professor Muralidharan, please go ahead. I think he has some problem.
Also to unmute
There
the
is
mic.
some connectivity problem maybe.
Yeah, I think so.
Or because of rain, no, there is a network may not be a problem. There is a lot of rain in Gujarat.
Yeah.
There is a lot of rain in Baroda.
Okay.
Heavy rain.
We can see him in the video, so should not be a problem.
There is a heavy rain in Baroda. That I saw yesterday.
Okay. If there is network issues for sharing, we can share it from here, Professor. Please send to me so that I shall share from here. Professor Ghosh, you are also talking something. We can't able to hear you because you are muted your mic. Professor Ghosh is speaking something.
Yeah, but to whom he is talking?
He is muted. He has to
probably he's.
The thing is, he is on mute. That is the
Yeah, and he seems to be the speaker for the session. But what has happened to Professor Murli?
maybe some network issue. Maybe I
So
think
Professor Satish, can you call him, please?
maybe you can talk by mobile first.
Yeah,
Satish, you can talk to him by mobile.
I'm also connected with the mobile. I'm away from my place of work, but still I can communicate.
Mhm.
So I think Professor Satish Kumar, can you call him, please?
Yeah, you can call him with the mobile, maybe.
Yeah. These are the electronic glitches which can create problems anytime.
Your talk is there. There is. Can you join? Can you join and? Okay. All right. Okay.
So Professor David, what is the problem?
There is some problem with the mic. He's telling.
Oh, okay.
Some problem with the mic. That is.
Yeah, because the internet problem, if there should have been, then he would not have been on the
You're
video.
using the mic in the laptop. Maybe that. Maybe.
Yeah.
Now you can see him, but the thing is, he's not audible. Maybe. Okay. You can try. Okay.
Let us wait few minutes, Professor, for that.
No issues. No issues. He has got some serious problem with it.
Professor Murli sir, you can share from the laptop and speak through your mobile phone. Switch off the laptop's audio and speak with the help of mobile phone. And through mobile phone, you can join with us.
He is very good with the electronic gadgets. I don't know why he is not connected today.
Yeah, Professor. He knows everything. We know, but there is the network issue, or the mainly problem with the laptop. Some complaint with the audio.
Yeah, maybe.
No problem. We have time, so we can. In which mail you have? Would you please WhatsApp?
I think connectivity is not a problem, but he has got some problem with his mic and all everything.
Yeah, Professor.
Yeah. No, I think he is coming.
Yeah, this presentation is coming. It's better to use his mobile phone or some other device for audio purpose. Can speak through mobile phone or some other.
Okay.
Okay.
Can you hear me
Now we can hear you. Now we can hear you.
Okay.
Okay.
I'm just showing
Okay.
the.
Okay,
I
Professor.
through
Welcome, Professor Muralidharan. Welcome, Professor Muralidharan.
Thank you so much. I'm so sorry for the
Not at
technical
all.
glitch.
Not at all. You are not responsible
Thank you.
for
Not
that.
at all, Professor. Yeah, please.
Okay.
So,
Okay.
I had briefly introduced you earlier in your absence, but now you can
Thank you very
continue
much.
with your presentation, please.
Okay. Thank you very much.
Other speakers are
So I think
requested to please
I
mute.
believe all others will mute their.
Yeah.
Okay. Shall we begin now?
Yeah, Professor. Please. Can begin now.
Thank you very much.
You can switch off the other device.
Yeah, if somebody is still not muting, please. Other people are requested to mute, please. Okay, now it seems okay.
Now it is fine. You are. Please share it once again.
Okay. I'm doing it again. I'm ready.
Okay, Professor.
Please, others
You
to
can
mute
switch
their mics,
can
please.
switch off the speaker of that laptop. Or
So where is
He
there?
has to mute one device.
minimize the volume of the other laptop.
Professor Satish, he has to mute one of the two devices. Otherwise, it will continue.
Yeah, Professor. Yeah.
Okay. I'm just starting my presentation.
Okay, Professor. Just a request. One of the audio can be muted.
That's what I
Yeah,
did.
two
I
devices.
just tried to mute my. Okay. But if I mute here,
Or minimize the volume of the speaker of the laptop.
yes.
Now it's fine. It
Yes,
seems to
that
be
can
fine.
be done.
Now it is
Okay.
fine.
Wait a minute. Just a minute, sir. Okay, I believe it is fine now.
Yeah. You can share the slides. You have to share the slides.
Yes, I'm doing that. Okay, it's perfectly all right now.
It's okay, fine. Please go ahead.
Okay. Okay, so here is my title: Time Scale
Yeah, okay.
Self-Exciting Point Process Models. Am I audible now, sir? Okay.
Yeah, very much. It's okay, fine.
Okay, thank you very much. So you can see that there are three components in the title. There is time scale, then self-exciting process, then self-exciting point process or stochastic point process model, something like that. Okay. So I will explain what exactly this time scale means and self-exciting point process means. Okay, actually this work is jointly with my student Agniva Das of Department of Statistics, Sardar Patel University. Okay, let me discuss briefly what exactly the meaning of point process models. Then I will get into the self-exciting point process models. So let me start with a simple example. Self-exciting process models are generally the temporal point process models. So temporal process, when is the best example is the earthquake, for example. earthquakes, then landslide, if you see, flood-related issues, wind-related issues, all those incidents, if you can put everything into the temporal process. Temporal process means the events depends on time of its occurrence. That is the meaning of temporal point process. Okay, so a point process, most of the point processes or stochastic point process models are all non-homogeneous Poisson process models. And they are typically characterized by defining its conditional intensity lambda of t. So lambda t is as good as your hazard rate functional repairable, non-repairable system models. Okay, lambda t is defined as the average number of events taking place in an interval t to t plus delta t, given the history of the process. Okay, so history of the process is very, very important. We know that earthquake takes place after a long time. The high intensity earthquake happens once in a while, maybe once in many years. So, but there are a lot of history on the process and the background takes place. And that is why the history of the process is important in this case. So here is the basic assumption of homogeneous Poisson process as well as non-homogeneous Poisson process. So we have NT as the counting process. It has always independent increments, and probability of one occurrence between t to t plus delta t is lambda of t delta plus order of delta, where lambda t is called the intensity function. If lambda t is constant, it becomes the homogeneous Poisson process. Okay, the self-exciting process is in a simple way. In a descriptive way, we can define the process as if covariance between two occurrences, say for example, number of occurrences between T1 to T2 and number of occurrences between T2 to T3, if they are positive, that means there is a chance of a next event to take place. That is why it is called a self-exciting. So many often the temporal events, this kind of phenomena takes place. Okay, many events triggers actually the next event. So triggering a situation or triggering mechanism takes place. That's why this covariance function is always positive. Okay, so the self-exciting process, and if you see that the lambda t, the intensity function depends on many things. There are three components here. So you look at the whole intensity nu plus integral 0 to t g of t minus s and dnms. That can be descriptively represented in the summation form as summation t k less than t g of t minus.
So again, there is a audio problem.
There's some problem again there.
Impact, maybe due to
Okay.
wind.
Okay.
Is it okay? Any problem? Any problem, sir?
You have to.
Satish?
Yes, Professor. You have
Can I
to
continue?
repeat the last sentence. That's only.
Pardon?
Last sentence or last.
Okay.
Yeah.
Line is not seen. Okay, visible. Okay.
Yeah,
Fine.
few minutes.
Okay. So, okay. G function is actually the influence of an event or the intensity process or density function. It can also be a density function kind of. Okay. So there are many temporal specific models in the literature. Please refer to the papers by Weir Jones, Ogata, and Hawks and Dogs, etc., etc. That's very specific to earthquake occurrences. And most of the time, the earthquake earthquake occurrence analysis are done for Japanese related.
So again, the sound is not audible.
I'm here.
Okay.
Now it is.
So, okay. Now, so you have now history of the process. Now, again, the same example. Earthquake, for example. So many often earthquake takes place based on many covariance impacts. Covariances, for example, latitude and longitude. So look at the history here. So the history of the process depends on three components. The simple sense. We have now extended this for 3, 4, and 5 dimensions also. So Ti, Xi, Ya. So Ti is the magnitude of the event, or Ti the time to event. That can
Excuse me, Professor. There is again.
Yeah, again there is a problem.
Okay. So that is why we need to introduce the ground intensity function here. You can see that now suppose NT or delta T. Delta can also be a parameter kind of things, or maybe a sequence of parameters, which is indexed by say theta 1, theta 2, etc. theta m. So here that again depends on the history of the process. So probability that NT greater than 0 given the history as delta goes to 0 limit. Okay, so the ground intensity function actually describes the rate at which the events occur over time and is not only influenced by the current time, but also the events that have occurred before the current time. Okay, so if you look at the pattern of occurrences, many often events may be triggered by past events. Many fluctuations takes place within the many layers of Earth. Okay, if you're talking about the wind-related issues or landslide, so a lot of issues take, flood-related rainfall, precipitations, etc. A lot of issues, impact on the ground intensity functions. So that is how we get into the epidemic type aftershock sequences, ETAS models. So altogether, all these kind of models are classified under ETAS model. It's actually a statistical model that is used to describe the temporal and spatial patterns of earthquakes or floods or landslides, specifically the aftershocks that follow a main shock event. So that is why it is called self-exciting process. Most of the ETAS models are self-exciting because some events triggers the next event to take place. So self-excites, it excites self. The model is based on the assumption that the rate of aftershock is influenced by both the magnitude and frequency of the main shock, as well as the spatial distribution of previous aftershock. So you have main shock, frequency of main shock, magnitude of the shock, then spatial density, distribution. A lot of components are coming in the modeling aspects. So it has been used widely in seismology to analyze seismic data and make predictions about future earthquake and future landslide floods related issues. So here is the model development. You can see that again the lambda t depends on many factors. So nu beta and lambda theta. So there are two set of parameters coming here. So beta is actually the indexing parameter of the nu, that density. And lambda theta is another, theta itself can be a set of parameters. In fact, there are about 7-8 parameters in the theta vector itself. So you can see that the whole model. So nu beta is actually the probability density function of the magnitude, and lambda theta is actually the whole aspect, the other background intensity and the ground intensity and all those, which combines a lot of components are coming there. It also includes the quantity or function of the expected number of triggered events generated from the event of magnitude, Ti, and Mi as well. Okay, so there are many different forms for that. We have considered both exponential and gamma distribution for the magnitude intensity. So here is another
Again, there seem to be some
and we
problem.
also have a radial symmetry. Okay, there is a radial symmetric time density function called F. So D itself is a parameter there, gamma, Q are other important parameters. Now you can see that by now there are a lot of parameters included in the model. So with that we write down the likelihood function and plus, okay, let me go back to the likelihood function. Let me show that first. Okay, I think I need to discuss something more. After introducing the time scaling only, I will get back to that. Okay, there are two things we are going to do that. Now, occurrence data is available. Now, can we predict the next occurrence, or can we predict with some probability what is going to be the nature of occurrences? That is where we find this Pj and Pij. So Pj is actually the probability of an event J being a background event, and Pij is that the event J triggered by event I. So this whole probability can be easily found. And of course, this needs a lot of, care and this thing, because the convergence related issues are there with all the estimations, and a lot of parameters are there. So you have to be careful about estimating the values, the parameter values. There are many restrictions also imposed on many parameters, And you can see from outputs, we will discuss that once I show the outputs of. Okay, let us introduce the alternative time scales. This was again a recent study carried out by Dushan and Lawless in the year 2002. They have first actually proposed this time scaling for non-repairable situation kind of, non-repairable studies and situations. Okay, now after that, there was a complete silence on alternative time scales. Nobody actually discussed too much. But after later on, it was, some study from last 2-3 years we have taken up. We are now trying to see how the time scale can
Professor Murli, you are not audible, please.
be. So now you have very interesting results on those,
Okay.
estimations. So we have found many improvements also in the estimates by introducing the alternative time scales. So there are many alternative time scales possible. We have just detailed, because this is the one which we have used and found that this is useful for temporal modeling. So ideal time scale is as good as the same scale which you have already worked with. So there is not much difference there. But calibration time using that depth. So once, for example, if you see the occurrence place of a landslide or an occurrence place of a earthquake, for example, you can see a lot of So if you can measure the width, so this is another variable which we are bringing into the modeling aspects. So if you are incorporating those issues also, then by that you can do some calibration on the scale. So that calibration sometimes help you to identify the models. So here is another scale like proportional hazard time scale, then log linear time scale and power time scales, etc., etc. So they are different forms. So all this logarithmic scale also is very good. Many often that was better, and power time scale. Of course, they are very good in course. Okay, so let us now move on to the time. So this is the one which we introduced. It has time scale ETS model. It's actually a statistical model again describes the temporal and spatial patterns of aftershocks following a main shock. Temporal and spatial patterns of aftershocks following a main shock. So many often after, say, if you recall, the Nepal Kathmandu earthquake happened on 25th of April 1922. So after that,
Again, Professor, we can't.
Yeah, there are some problem again. Professor Murli, you are not audible.
is stabilized for it becomes stationary, and so that usually happens. So okay, the model is defined by a set of parameters including the background rate of earthquake. We have used two. So the
Sound is breaking.
I think this is because of the networking problem.
clustering method proposed by Jallier. Okay. Okay. So here is the likelihood function. You can see that likelihood is again a very long with a lot of components here. And interestingly, we have done a bifurcation of the likelihood into two parts, one indexed by beta and another indexed by theta. So now you see that we have now that the derivation. The reason why we did that was theta is actually indexing parameter of the ground intensity, and that can be estimated separately with beta cap as n dash divided by summation delta I of mi minus m. Now this was not easy. The reason is at least one parameter could be independently estimated, and the other the parameters were indexed by theta. And the derivation part is like this. There's some exercise we did. Getting it typed in PowerPoint is very difficult, so we have simply pasted the rough part of that. Okay, so we have done this likelihood into two portions. So that plus. So instead of maximizing the likelihood in one go, you can maximize the likelihood in two parts. So that beta estimated separately and theta is a vector of parameters and it can be estimated separately with all other. So here are the parameters. So you can see that there are about 9 parameters here, and each parameter has its own importance. Mu is actually the background seismicity rate. A is actually the minimum number of aftershocks expected in case of an earthquake at minimum threshold M equal to M naught. In our case, our data set, we have considered M naught as 5, means all those data sets where the magnitude is more than 5 or equal to, greater than or is equal to 5. But the rest of the data is not important as such. So we have to see those important magnitude values. So sometimes we have changed these M naught values at a later stage. Also, we have also seen what exactly the difference takes place. If we consider M naught as 4, 3, even there is no meaning in considering 2 or M less than or equal to 3, etc. Alpha is actually the triggering rate parameter. C is clustering parameter, because we have seen how the whole the intensity, I mean the occurrence clusters, or which area is actually clustered for, or which are the fault area for further earthquakes, tremors, etc. So that clustering parameter is also very important. Here some of the parameters are very, very important. Q and gamma is not very important. They are simply the radial parameters of the radial distribution. They are not much important. Mu is the important parameter. A, alpha, C, P, beta. They are all very, very important. Okay. Now we have seen. I will also show you the estimates where we will understand what is going to be the upper limit and lower limit of mu. So here is the earthquake data which is available outside, and we have considered the data from 90 to 22. So long, and we have now everything. It's official actually. The data is official, and that data includes day, time, so time is Ti, magnitude is Mi, and we have both longitude and latitude. Okay, so and we know the whole setup of the geography. Kathmandu comes the middle and down of that Nepal geography, if you look at, and they can understand where exactly this happened. So I will show you some graphs and tables how the whole thing happened. Okay, so yes, we have used the most comprehensive and up-to-date data sets of earthquakes in Nepal, and provides a valuable resource for studying the characteristics of earthquakes in the region. Okay, here is a basic graph. This is actually talking about the epicenter, location of epicenter. You can see, if you have a close vision, you can see there is somewhere in the graph, you can see somewhere here in actually the epicenter, the maximum the magnitude happened here somewhere in the Kathmandu region. Okay, so and this actually, so this is actually showing it as an outlier. So that outlier corresponds to the 25th April 2015, that the major earthquake happened. There are multiple, and after that, multiple great earthquakes also occurred in quick succession in the region. That is clearly visible in this graph. Here is another plots of estimates of the background seismicity rate. Okay, you can see that where it actually triggered. Okay, so this is the event where it is actually triggered. Okay, the total spatial intensity, and we also, location has been changed to T plus T is starting plus T for the fitted data, because that was necessitated because of our the data becomes huge for analysis. Okay, now there are you can see the Mars, the spatial neighbors where background intensity is high, and neighborhoods the clustering prone. So you can see that this red, pale red one area is actually the area where it is mostly clustered. So most of the aftershocks also happened at this region. Okay, now okay, so conditional intensity function is also plotted here. You can see that this is this includes the history of the whole process. So because the intensity function depends on the history of the process. So what actually triggered, what was the past events, etc., etc. So here is the estimate based on the basic model, where we have considered both exponential as well as gamma model. No doubt, gamma model is better if you look at the log likelihood function in terms of the magnitude. You can see that gamma model, but as far as the estimates are concerned, there is not much gain. They are almost similar. They are very, for every analysis we have found that gamma model is fine, no doubt, but estimates with the exponential distribution is also matching with that.
Okay, so here we have not done any calibration as such. You can see that T ratio set is taken as the original time scale itself. So here is where we have again found the estimates based on that two algorithms. Okay, ISDM algorithm and the DFT algorithm. You can see that how the so here this based on the exponential distribution, the G function as exponential, because we have found that actually there is no much gain. Estimates are going to be same. Now, from these estimates, you can also make a guess about what is going to be the maximum, minimum of the parameters. So, some of the parameters are very important, equal to 1.15. This indicates that there is going to be another event which can, means the rate of subsiding or being in its stationary is going to be, if it is perfectly 1, it is definitely stationary, but it's slightly more than that. That means it will subside after some time. That's all. It indicates a kind of pattern that there is going to be the tremors will eventually be stationary. Okay, so we'll see some other estimates as well. So here is the calibration where based on the depth of that particular plate.
Professor Murli, you are not audible.
Look at the estimates. Okay, not audible now?
No,
okay,
it's okay. We can hear you. Please go ahead.
Okay. So here you can see the calibration omega 1000. You can see the estimate is much better. Okay, so all parameters are estimated. Okay, so here is the more diagnostic graph. Here is a plot for the fitted ETAS model. So here is the plot correspond to the fitted distribution. So you can see that this particular one, they are the time point. If you get this, you will have to convert into time scale. At what point this has occurred? So you can see that at 2 to 3 points there is a greater magnitude occurrences of events. Okay, so here is similarly top left and top right panel. You can then earthquakes close to Kathmandu region have a lower residuals, meaning that the background intensity and the clustering coefficient of that region is well represented by the model. Okay, so that is for the kind of the normality. UI follows uniform unit 0.1 that at 5% level of significance. So that also shows that also support the conclusion that the Kathmandu region, the residual is very small. Very small, or actually happened and along in somewhere around that particular belt. Okay, so here is the most likely probability. So what is going to be the next occurrences? So this is where you can see this graph is important. You can see that types of clustering here altogether on the northern side and the down south. So this is the with two colors of marks here. You can see that. Okay, indicate most of the earthquakes in the Kathmandu Janakpur region are triggered, whereas states occurring in the northwestern region is most considered background is missing. So here is what is triggered. Okay, and in fact, it was true from the analysis reports and the official information came up after that from the Kathmandu earthquake that it actually happened with some triggering event. Okay, so that kind of triggering can happen in future as well. So we have now plotted some, found some probabilities also that in future there are a lot of chances for moderate to high or average tremor, intensity tremors possible in Kathmandu region. Because there are going to be if there is a triggering event. That triggering event can happen randomly, so it can happen in future. Okay, so that is what we are now going, and we are also now getting into the study on monitoring and forecasting aspects of the study as. Okay, so that is what is I have to tell you. Okay, thank you very much.
So,
thank you very much.
Thank you, Professor Murli.
Thank you. I'm so sorry. Sorry
not at all.
For the technical problem.
Not at all. These are the electronic glitches which are sometimes beyond the control of a person.
Exactly.
So,
exactly.
Thank you, Professor Murli, for presenting your lecture. And of course, this is very interesting and a new area. And you have talked at length on epidemic types aftershock. Perhaps we can venture out in this new field because this is the area where we are not able to make much headway. We should also explore the possibilities of pre-shocks also. But definitely you have to minimize the sound shocks in your mic. You have to get it corrected, okay? So thank you, Professor Murli. We have really enjoyed, except for some disturbances. So on behalf of the organizers, I extend my gratitude to you for presenting the findings of your area of research. May I ask for a few, one or two questions from the audience if they wish?
Welcome.
Yeah, please. If there is any question, please feel free to ask. I think none.
Okay.
Thank you so much. So nice of you. Thank you, Professor Satish Kumar.
Thank you, Professor Akul Ahmad, for chairing the session and supporting our conference in a very nice way. Thank you so much. Also, we would like to express our gratitude to Professor Muralidharan for your excellent talk. In fact, there is some network issues and some technical issues.
Yes.
In fact, that is beyond our control. Don't it is.
Actually, yesterday I had a presentation at Anand Agricultural University.
Okay. Okay.
Some changes in the mic setting, I suppose. I am strongly vouch for that. So I will have to correct it again.
You can also.
Yeah.
Yeah.
Okay, Professor. Okay, Professor. Anyway, we have it's a fine, very interesting talk. We are grateful to both professors for your.
Thank you.
Thank you so much.
Thank you, Professor Satish. So nice of you.
Yeah, thank you. We need your support in further.
It's always there.
Okay, thank you, Professor.
Yes.
Thank you. Can we leave, Professor Satish?
Yeah, Professor. You can join at any time and please.
Okay, in fact, I have some other meetings in the department.
Yeah.
Thank you so much.
Yeah.
Okay, Professor.
So nice of you.
Okay. See you. Okay, thank you.
Thank you.
Now let us move to the Anyway, Professor, please. Listen. Professor Muralidharan, do you want to say anything more? Now there is next session at 10:35. I think a few minutes are there. 2-3 minutes you can spend for anything. Anyone has to share anything. If it is not problem, please. That will be great. Please. Morning, Kalyanam sir. Good morning. Kalyanam sir. You have to unmute mic. You have to unmute, sir. See, mic is muted. Please unmute the mic. Your mic is muted.
See, of late, I am not able to hear properly. That is a major issue. And,
okay, Professor. Okay.
very slowly going out. And,
okay.
No, I attended Professor Muralidharan's lecture completely.
Yeah.
And there are some conceptual problems, which I think Professor Molidaran can answer. See,
Okay, okay.
time
Okay.
series, you say that it's a random behavior.
Murli sir?
Random behavior, the fourth component. And you say that you are predicting it. And how do these two things go together? Is there, Professor? I think he has left.
Mr. Muralidharan, sir?
And I don't think he has left, I think.
He's in the group, but probably he engaged in some other works, probably.
Okay, okay. Right.
Hello? Murli sir?
Okay. So I think you have another 8 minutes
Yeah, yeah.
for the next
Yeah.
session.
In fact,
We'll answer.
he is in the group. It is better to discuss that matter. Professor Muralidharan?
He's not there. He has left. Yes, he is there.
There is, yeah. He has some audio problems also. That's why, probably that's why he left. Whether he left or not. He is in the group. He's there in the group.
He is there, but otherwise engaged, perhaps. Okay, leave it. Anybody can answer.
Okay, sir.
If anyone is ready to answer, let them answer. No problem.
Oh, okay, sir. Okay, sir.
So the question is this. You say random component, you say you predict it. How do these two go together? This is the question. See, the earthquakes are randomly happening.
Professor Ghosh has said something, I think. No. Okay.
I think he is saying something not audible. I think he has to unmute.
You need my help? Dr. Satish? You need my help?
Satish, unmute. Satish, unmute. Your mic is off.
Oh,
No, my
okay.
mic is on.
Yeah.
Can you need my help?
Professor, our Kalyanaman sir has asked some queries with regard to Professor Muralidharan's talk. That's the point. By the time you are talking something, but the mic is unmuted. That is why we are asking you whether you are talking about that or no.
No.
Yeah.
Okay, I think you can call for the next session.
Yeah, Professor. Let us move to the next session. Where the Professor Ilangovan is here in the group to chair the session. Professor Ilangovan has agreed to chair the session. Since the session started 10:35, that is why I'm waiting.
10:35.
Yeah. 10:35. Let me to check let me to contact him whether he joins or not. What about the speakers? Professor Rudrapradhan is here in the group, isn't it? And Professor Ramakrishnan also there. Yeah, Professor Ramakrishnan is here.
Yeah.
Rudrapradhan also. The speakers are there in the group. Okay, very good. Yes, sir. Professor Elangovan will join shortly. Okay, Professor. Mulisa, we are waiting for the next chair. By the time Kalyanam sir has asked some questions with regard to your talk. That's why.
Yeah, please.
Now that we can Kalyanam sir.
Please ask. You are always welcome, sir. I'm here.
Yes.
Okay. Now the time for the next session, for Kalyanam sir, whether you have to ask the shall we start the next session because 10:35 is time? Okay.
Yes.
We can discuss those problems later. Mulisa joined and he is asking about you, sir, the question and the discussion. That's why. Even then, now it is a time for the next session. Let us start move to the next session. Tajunisa, please introduce the chair and do the needful. Mulisa, we can discuss that matter later. Okay.
Oh yes, I'm here. Yeah. You can just give me a call. And I will be joining.
Yeah, Kalyanam sir is not hearing what we are talking. That's why.
Okay.
Hearing is going out. That's a problem.
Yeah, hearing. There is a problem with audio.
Wait, you have time.
Yeah.
It's simple.
Now with the next session, sir. So we can discuss in the meantime after the session. That's fine, isn't it? Isn't it okay, Professor?
Yeah, fine.
Yeah.
Okay, sir. Can I start?
Okay, please.
Warm greetings to all. Now we move on to technical session 24 of WSTA 2023. The session will be chaired by Professor R. Ilangovan, the Faculty of Department of Statistics, Annamalai University, Tamil Nadu. He has more than 31 years of teaching and research experience in the field of statistics. He was awarded PhD in statistics from Annamalai University in 2000. He has PhD in business administration also. His area of specializations are reliability theory and survival analysis, biostatistics and cohort regression analysis. He has more than 158 national and international research publications in referred journals, and he is part of various national and international research collaboration. He is a visiting faculty to many foreign universities as well as a member of the doctoral committee. Once again, I invite Professor R. Ilangovan with immense pleasure to chair the session. Over to you, sir.
Thank you very much, sir. Now you proceed. Who are all the speakers, sir? Let me know. Who is the first speaker?
Yeah, I am, sir.
Yeah. Let us call upon the first speaker, Rudra. So he first present his then question will be asked after this presentation. Only 2 questions should be asked. Please, sir, go ahead.
Okay, sir. Thank you. Is it visible?
Yeah, yes.
Okay.
Yes, sir.
Okay, so thank you, Professor, and thanks the team and Professor Satish Kumar for giving.
Welcome, Professor Rudra Pradhan. Welcome. You are most welcome,
Yeah.
Professor Rudra Pradhan.
Yeah. Is it audible?
Yeah, yes, audible.
Okay. Thank you, Professor, and thank you, Professor Satish, for giving this opportunity to speak. Okay, so let me start with my talk, and in fact, in the last technical sessions, there was a good paper, and that too, there are certain questions also. So let me answer to that question also. Normally, when you go for any kind of statistical modeling, so we need data. Okay, and there are 3 different ways we can analyze. So one type of data is called as a cross-sectional data, where time is constant, and then we have a data from different locations and different kind of countries and different kind of persons. And the other type of data is called as a time series, where cross-sectional unit is constant, and then there is a variation in time, maybe hour-wise, day-wise, weekly, something like that. And the third type of data is called as penal data, which is actually mixture of cross-sectional data and time series data. So where actually both cross-sectional unit and time series units can vary. Now, corresponding to Professor Muralidharan's talk and that to research problem, obviously, the type of problems, so the particular earthquake issue in Nepal, it cannot be continuous for any parts of the world. So obviously, there is a cross-sectional data, and that too again time series data. And obviously, his analysis probably related to either cross-sectional type or it is kind of penal data type. So with penal data, we can do also forecastings. When you talk about penal data, then obviously there is something called as balanced penal, and there is something called as unbalanced penal. And whatever may be the issue, we can have unbalanced panel, then we can go for forecasting, and again we have a balanced panel and we can do the analysis. So that's why there is nothing wrong actually to do the kind of prediction with respect to cross-sectional data or penal data. Of course, time series data is well representative to any kind of forecasting because of consistency and kind of efficiency. So whatever statistical properties you can talk, time series can fulfill, but it has a limitation to cross-sectional and it has also limitation to penal data. Still, it can be possible. Taking this clue to that particular issue, my talk is also similar kind of study, and my talk is also penal data modeling. And of course, I attended a couple of lectures yesterday and also here in the first lecture. And I could find that there are very good techniques discussed in this forum. Obviously, there are 2 different ways if I can generalize. So sometimes you can start with typical kind of problems or techniques, tools, and then we can connect with particular applications, right? Yesterday I was Samesh Kumar's lectures and also here in this Muralidharan's lecture. Obviously, they started with some model and then they connect with some kind of application. Either you can start with the model and then apply to the applications, or we can start with some kind of an application problem area and then we can think about some kind of technique to solve the issue. My talk is actually the other way around. Okay, so we have some kind of issue related to financial market, and then we can talk, try to address this problem with the help of some kind of statistical technique. Of course, I can make it also reversed. For instance, my particular talk is actually RDL modeling. So I can start with discussing what is RDL modeling in a simple structure, that too in a simple time series structure. That too, there are 3 different ways we can analyze, RDL modeling. The first one is called as linear RDL modeling. The second one is called as non-linear RDL modeling. And again, third kind of cluster is called as penal RDL modeling. So again, it depends upon time series data and again penal data. Of course, if you have a strictly cross-sectional data.
Professor Rudra Pradhan,
Yeah.
slides are not moving, I think.
No, I am just introducing, so that's why
Oh,
it's not.
okay, carry.
Uh, uh, I hope it's moving now.
Okay, fine. I doubt whether any technically problem. Okay, please go ahead.
Okay, let me. Yeah, Is it moving now?
It is moving now. It is moving.
Okay, all right. So now technically, so whatever I have introduced, so we can start with the discussing RDL modeling. And obviously, the moment you start using RDL modeling, so because it is a time series technique, so you can use this model for individual time series data, or you can use this model for penal time series data. So this particular problems which I am going to discuss is a penal time series modeling, and again the application is on penal time series data. So I am not discussing the details about the RDL modeling, and again linear type, non-linear type, then again the kind of penal type. So I will strictly come to the application, and then with the help of this penal RDL modeling, so I like to address this issue. Okay. Going back, history or literatures, there is a issue about finance, right? So we talk about lots of financial markets development. Again, when you talk about financial market development, then it may be related to stock market, it may be related to banking, then it is related to equity market, derivative market, insurance market. So many varieties where you can analyze. Ultimately, the question is why there is a need of financial market development, and how we can go for modeling, and how to do this kind of forecasting, etc., etc. These are all several issues and problems which you like to address. Normally, when you talk about the financial sector development with respect to any kind of financial market, so the main objective or the main target is to have some kind of development in the economics, or we may whether the financial market development contribute to the economic in terms of sustainable development, or in terms of economic growth, etc., etc., right? So obviously, this is a kind of big investment, and this is a big problem which not only in India, across the world is looking for that. That's why financial market is a big problem in finance. And obviously, we like to always see whether any kind of financial market development has some positive impact or some externality impact towards the economy. This paper is specifically related to financial market development, and that too with the application is on derivative markets. Okay, so of course there are several other markets. So this particular work is strictly connected to derivative markets. So now we like to see whether this in fact derivative market is compared to other market, derivative market is very new. And across the world, if you see, the derivative market is not well developed. In Asian clusters, this is one of my research area. In Asian cluster, only few countries, hardly less than 10 countries are having a improvement in derivative markets, or there is something business is going on derivative markets. Otherwise, it's very, very low coverage in Asian clusters. Again, even American cluster and European cluster, this volume is also very low. And when you talk about derivative market, obviously there are two issues. Why you need actually derivative markets, again, so that will contribute to the financial sector development, and also linking with the other markets like stock markets and then capital markets, so that there is overall financial market development. And our focus is whether it's a derivative markets development or any other markets development, financial market development, that should have some contribution to the economic in terms of sustainable development and growth. And in this context, we are hoping whatever the coverage there in the derivative market till today, so that must have some kind of contribution to the sustainable development and economic growth. So that's why we like to see whether the growth of derivative market has a contribution to the economic growth and sustainable development. That's how the background about this problem. And we to because it is theoretically there are many ways we can just bring the issues logic kind of flaws, how this there is a contribution to the sustainable development and growth. But practically we need actually some kind of model, right? You can use any kind of econometrics model or statistical model to justify that. And here in this paper we are trying to address that particular issue, and that too with the help of RDL modeling. And of course what I have mentioned that the particular model RDL, it's not new, and this particular research area also new. Of course in the derivative markets the volume is low, coverage is very low, but still it is not new actually. So if you look into this literature, so the first paper which we have observed here 2010, right? So that means technically from here you can find that this market is not very well developed compared to banking banking sectors or stock market or any other market. So now what we normally expect when you talk about any kind of financial market development, so that means we technically expect that this particular market should have some contribution to the sustainable development and growth. And again we are expecting that when there is more and more growth and sustainable development in the economy, there is again more demand towards financial markets. For example, let's say more ATM booths, or more bank branches, or more kind of stock markets, or varieties of financial market. That is not actually supply driven. Sometimes it may be lead to demand driven. So when there is some kind of more and more business and more development, then automatically there is a huge demand of financial instrument, financial markets, and financial structure, something like that. So that's why we are expecting that so financial market and that to derivative market has a contribution towards sustainable development and growth. And again, sustainable development and growth, that should have also contribution to the financial market, in particular derivative markets, and in general overall financial sector development. So now coming to this a little bit literature, we find there are means the particular proposal is not very much uniform. So means we are hoping that they influence each other. Means causality will move both the directions. That means derivative markets have contribution to the sustainable development, and sustainable development can contribute to the derivative markets in particular, and financial market in general. But that does not normally happens actually, and that is not true in each country, or in a particular country in a different time frame. So sometimes it is a unidirectional, sometimes bidirectional, sometimes there is influence also. And if you look into this literatures, we have lots of such cases. And these are all recent, because this market is very new actually. Derivative market is very new. And if you look into this methodology part, so there are a couple of techniques actually used, and starting from simple RDL models, then penal data models, and that to GMM technique, simple correlation technique, and again some of the kind of causality technique like vector autoregressive, etc., etc. So now I am not going in details about this literature. So from the literature, what we observe that this is what the research gap we find from the derivative markets, and that to whatever research going on the linkage between derivative markets and sustainable development. So corresponding to the earlier available literatures, we find there is lots of complexity first to understand the derivative markets and their contribution to the sustainable development. And that too again in Asia specific context, the volume and the coverage and the impact is very low. And again we need a sophisticated technique to establish that particular linkage. Like Professor Krishnamurthy have already asked that how you can address if the coverage low data and cross-sectional data. That's why we use actually time series data, that's very less, and we cannot use actually individual RDL model. And that is how we are choosing few countries and few time periods, so that you can have a good panel data, and then you can apply this particular model to work out the relationship between derivative market and sustainable development. Okay, so in our models, of course I have already mentioned, so we are going to deploy a panel RDL model, and the structure is actually to study the linkage between sustainable development and derivative markets volume. But in addition to these two variables, we have other variables, because the other variable also impacting this particular linkage. Sometimes derivative markets not contribute to sustainable development, or sustainable development does not contribute to derivative market because of some missing variables, right? So if you bring that missing variables, of course it's very difficult to find out that numbers. But in this context, we have observed that some other variables which can establish this strong, bring some strong relationship between this derivative market and sustainable development. So these includes actually again stock market volumes, that is stock market capitalizations, then government investments, because government investment is a very important factor through which market can be improved. And then current account balance, that's financial market transactions. And the variables, these are the variables which you are using. And again, from the data side, as I have already mentioned, this market is very new, and as a result our time frame is actually from 2001.
Hello, only few minutes more.
Yeah, sure. 2022. And again, we have selected very few countries like India, Australia, Hong Kong, Japan, Korea, and Singapore. So that means in Asian context, these are the only country which have actually derivative markets coverage, and that too there is a impact on sustainable development. And methodological, I have already mentioned. So these are the techniques which we are going to use in addition to RDL modeling. So we have used actually fixed effect penal data models, and again penal corrected standard error estimates. So this is what the RDL model in general framework. Since we have a couple of variables, so every time we have a particular variable as a dependent variable, and then we have independent variables. And to address the endogeneity, we have also used as a log of the dependent variables. So this is the first models, and this is what the second models, and where the error correction modeling is actually used. So that there is actually depends whether there is a short-run linkage and long-run linkage, obviously with the help of data kind of structures like the tesonarity and cointegration. So we sometimes use the error correction terms, and sometimes we may not use. So that depends upon the presence of cointegration. So when there is a presence of cointegration, then we can use penal error correction models, and when there is no cointegration, then you can simply use the RDL modeling. Okay, so this is how the model improvement against, and this is the final model against to study the causality between these two variables, and against to estimate the again fixed effect models, and to study their impact. Against we fix another model here, and we start with the analysis descriptive statistics, and against this is the penal data statistics, and these are the variables. And from this descriptive statistics, we find that there is no large scale variations within the data, and that too data has large scale variations. So that's why we do not have a problem to link with this kind of data to address this issue. And we have also individually plot these variables to see whether every variable has an impact towards sustainable development. So the first figure reflects the derivative markets on GDP. So we find here there is a somehow positive link, and against stock markets, so there is also somehow positive link. Similarly, inflation's little bit very non-linear. It's very difficult to predict in this graph. And against there is also positive impact on government expenditure towards sustainable development. And finally, current account balance, that's actually a reverse structure. If there is more and more current account deficit, then that will negatively influence the sustainable development. So whatever the nature of the variables which you are observing, that's data is showing. And then coming to the empirical part, so all these variables first address the tesonarity issue, and that is the prime and vital for cointegrations, and then this RDL modeling. And we observe that most of the variables are non-tesonary at the level data, and then found tesonary at the first difference. So that means all these variables are having order of integration is actually 1. So I1 type of variables, and these are the results. We use actually ADF statistic as well as Phillips Perron statistics to see whether these variables are really having tersonarity or non-tersonarity, and that to level data, fast difference data, and against which have with intercept, without intercept, with a trend, without trend, and something. So in all these permutation combinations, we found that all these variables having actually tersonarity issue, and that is corrected at the fast difference. So that's why towards the end, Airedale modeling, so we connected with fast difference data to address this issue. And this is how against Phillips Perron statistics. Okay, so then pool mean estimations against, I can skip all these things. Okay, so this is how the results, and we find that some of the variables having positive impact, and means mostly all variables having positive impact except this current account deficit, which actually we observe individually from the graph. Okay, so again in the models, multivariate models, we that is also reflecting. So that means this particular problem is very well defined, and all these variables are supporting with this kind of data. So that means we are coming to the conclusion that so these variables having strong impact towards sustainable development. Okay, so then again, so we use a penal causality test and to address whether there is a reverse kind of causality or there. So so we find that means we are linking actually one-to-one basis. And many if you look into this series of analysis, we find most of the instances there is a causality. So that means there is a interdependence among variables. Actually this yeah, I just need 2 minutes. So we find that these variables are having sometimes unidirectional, sometimes bidirectional, and that's how the interdependence, and that happens normally in a macroeconomic environment. So normally a particular variable may not actually strictly unidirectional or bidirectional because of influence of other variables or other markets. So that's why it is happening. But anyway, so we find that there is some linkage between these variables, and we observe these are all variables which can reflect sustainable development, and again sustainable development reflects all these variables, including these derivative market, stock market, then government expenditure, then current account deficits. And again, to check the robustness, we use actually fixed effect models, robust fixed effect, and PCSE. So everywhere the observation is actually more or less same. So where current account deficit is having negative impact and the other variables having positive impact. So the policy implication is that so government should have more and more implication or means importance towards derivative market, stock market, and again government expenditure, and try to have some policy to reduce the current account deficit. Then it will address the sustainable development. Okay, so this is all about some of the more policy implications are here, and that's all. So thank you very much. Is it okay?
Yes, okay. Oh, your presentation is well. Now, any one question from the audience? Anybody? Yeah. Anybody ask question? Let me know, please. Any question?
Okay. Generally,
yes, sir. Professor
derivative market is very risky as far as I understand.
Yes, sir. Yes, sir. Yes, sir.
So, with such an amount of risk associated with the derivative market,
sir,
how is it possible that you can connect this with economic sustainability?
Yeah, okay. So that's very good question, sir. Of course, if you say risks, actually, the moment you enter to the financial market, then definitely there is some kind of risk factors. Of course, your point is very correct. So initially I have mentioned that when you talk about the financial market, then starts with the bank, stocks, and derivatives. So now when you start from bank, stocks, and derivatives, etc., so the volume of risks actually started increasing. Even if you invest in bank, still there is also risk factors within the banking investment. There is a fixed interest rate and flexible interest rate. So you are not at a particular point of time, you are not in a position to think whether to go for fixed interest investment or flexible interest investment. So that means technically you are also taking risks there because you don't know what will be happening in the next moment. So like other markets, so derivative market is also having risks. And by the way, the moment you enter to the financial market, So assume that you have to take the risks. And by the way, in the business or any kind of market economy, if you don't take risks, then probably you will not gain more. So you have to take the risks, and otherwise it will not happen. That's how the government is actually, few years back, government reduced interest rate in banking sectors, so that let's allow people to go to the stock market, derivative market, insurance market. Of course, indirectly government encouraging the people, you should take risks. Okay, so that it is win-win situation. You can gain and country can also gain. So that's how, even there is a risk factor, there is no harm. It will contribute sustainable development. So there is a possibility, because when the market will grow, market will be improved, and then their market efficiency will improve, and obviously it will contribute to the sustainable development.
It's okay, but when you do it with the data analysis point of view, or you call it with analytics point of view, when you go into that, apart from statistical validity, don't you think that model acceptability is more important?
Yeah, you are right, sir. So we have gone through lots of robustness check actually. So there, in the RDL modeling and penal RDL modeling.
Is there any studies related to model acceptability?
Yes. Once model is acceptable, then we can actually go for this kind of forecasting and implications. You see the particular RDL models, you can estimate in varieties of way. For examples, so it's basically lag modeling. So if you change the lag, then by default you will get plenty of models. Forget about inclusion of other variables, exclusion of other variables, the kind of normality. So just you increase the say lag length. So start with lag length 1, lag length 2, lag length 3. Then if you find all the possibilities and you estimate, then you will find plenty of varieties of results. Of course, we have gone through all these permutation combination and finally fixed a particular model, which is actually gone through all these kind of issues, and then we started our forecasting and the implications. It's not that we have.
I would request you to send some say references to the organizers so that we'll be able to collect it.
Sure, sir. Thank you. Definitely, I will do.
Hello, thank you very much, Rudra, for your nice presentation.
Thank you, President.
Big hands to Rudra. Thank you very much.
Thank you, sir.
Okay.
Namaste.
Please call upon the next speaker, please, sir. Next speaker. Hello.
Hello.
Well, next speaker, please.
So, Professor, I am Ramakrishnan here.
Yeah. Please, sir.
Shall I proceed? Yeah.
Proceed.
Thank you, Professor. Thank you.
I think Satish, just to introduce him.
Yeah.
I hope my screen is visible.
Yes, sir. You can go ahead.
Thank you, Professor. I thank Professor Satish Kumar sir. He's giving opportunity for me for the last 3 years to share my knowledge in this forum. So I thank Professor and also my supervisor and guide, Dr. R. Ravanan. He is the person brought me to in this position. So now already I have shared the same paper in Monomium University, but I have appended 2 or more things with that paper for this conference. That is one sample hazard rate estimation and another one is hazard ratio. With the help of the bootstrapping, I have added in the same paper. That's why I am going to share with you all. So how the bootstrap techniques are very much involved in the survival data. That is the only thing I'm going to share to you. I think I have 30 minutes. So here we have so many survival methods are there. Non-parametric and semi-parametric and parametric Bayesian methods are there to find some estimates with some classical techniques. But there is another techniques also introduced by Efron in 1981. That is the bootstrap technique. He applied for all measures, simple measures, starting from mean, correlation, and everything. But when survival analysis, to find the survival function and hazard ratio, and also many things, we can apply it, this bootstrapping. That's why I have applied everything in this paper. So, and also I have found the significance and also effectiveness of the bootstrap technique in survival. That is only I'm going to share. So this is the things we know. Survival analysis is different from other studies because of censoring. Here, the important thing is effectiveness of bootstrapping and the confidence interval of various parameters of interest. So here I have taken the four concepts. One is survival function estimation. Another one is hazard for one parameter exponential distribution, the lambda. And another one is a hazard ratio. Then another things, how it can change it with the help of the censoring concept. These are the things I'm going to share. So for that one, I have taken some real-time data and also I simulated some survival data with the help of the Linde R package in R programming. So this is the usual things, traditional non-parametric estimation of the survival function that is introduced by Kaplan and Nair 1958. That is S of t is a survival function. Then Greenwood's formula for finding the standard error, you have to find variance of the survival function. This is introduced at 1926. The another one paper is in Kaplan-Nair survival graph. It is a step function. Within the two survival time, within the interval, if any sensor comes, we have to keep the same survival probability in Kaplan-Nair. For that one, Rosa and Zelensky introduced one paper for Weibull smoothing. So in the Weibull smoothing concept, they are taken the two even time, and with the help of the two even time, they apply the Weibull survival function and estimated beta value and gamma value for the two even time intervals. Then they applied it and they smoothening the stepwise function. So then this is the way they will get the survival estimate for the times within the two even time also. But in bootstrap technique, this is the bootstrap technique. Also, Efron introduced the bootstrap technique is in the two methods. We know the time and censoring are independent. By the way of the resampling method, you take time and also you take sensor and do it. Then you will get the estimate. Then otherwise you take the pair time comma sensor and resampling them. Then you find out the survival function. So these are the things we are going to do. So this concept is called as a bootstrapping in survival function. So here, when finding the standard error, we have to use Greenwood's formula. Without using the Greenwood's formula, with the help of the bootstrapping technique, we have four types of methods are there for finding the confidence band, confidence interval for bootstrap estimates. So I'm going to use the only one method here, that is called as a percentage method. It is the easiest method. We have to find the estimates that forms a sampling distribution of the bootstrap estimate. That is arranged in a order. Then you find out the 2.5 percentile or 97.5 percentile. Then you can find it. This is the confidence lower limit and upper limit for 95% of the confidence interval. That is the things I have tried. So semi-parametric method also, if you want to find the parametric estimation, you have to use a partial likelihood approach, and also to find this one standard error, we have to use the information matrix that will take some more statistical procedures. Similarly, this is the statistical procedure. That is, you have to, for finding the standard error, you have to inverse I of beta. The same thing, the significance also can be obtained by wall statistics. But in parametric model is also, we have to use some statistical procedure for finding the standard error. But in while using the bootstrap technique, there is no need of using some statistical techniques, but just like you make a sampling distribution of our estimate, then you find the 2.5 percentile and 97% percentile. That is the easiest one. That's why I have compared the both classical and this bootstrapping value. This is the percentile method. Whatever I told you, C alpha by 2 and 1 minus say alpha by 2. Alpha is taken as a 5, that is equal to 0.025. This is 0.975. So now I have taken one data. This is a simple data. It's taken from this R package in survival leukemia patient data. It contains a censoring object also. And I have taken only one covariate. That covariate is they are maintenance chemotherapy, yes or no. That is the things. I have taken only one covariate. So here, what is the things we observed when using the 500 boost-off samples for this data? See here, this is a 5, 8. These are all even times. When using the Kaplan-Meier estimates, then we have to give 5 and 8. Yeah, in between, if anything is happened, we don't have survival estimate. But in boost-off techniques, here you see that this is a 12 and a 13. This is also 13, 16, 16. So now you see that this is the even time. This is the censoring time. That's why here in the even time 0.6957. But we have to keep other even time is 18. 18 only we got it our survival estimate in Kaplan-Meier because it is a step function. But when using boost-off, you will get survival estimate for the censoring also. By the way of this one, we can smoothening our curve also, Kaplan-Meier curve also with the help of the boost-off survival probability concept. So you will get survival probability for sensor time also. We will get it with the help of the bootstrapping concept. And also we observed the width of the confidence interval when bootstrap survival probability, when applying this one, bootstrap concept for this data, the length of the confidence interval width is decreasing. Here you see that when compared to the Kaplan-Meier, here in this case this is 0.44, but here this is 0.25. This is very narrower. This is the nice things we have obtained using the bootstrapping technique. So similarly, here this is the diagram. This is the red line shows of the Kaplan-Meier confidence interval. Black line shows our bootstrap band. So now here the bootstrap estimates survival curve also within the confidence band. This is the things, and also we observe the width of this thing is narrower when compared to the Kaplan-Meier. Bootstrap confidence band is narrower. So now here when applying the variable smoothing, so this is the variable smoothing concept. In variable smoothing concept, the Kaplan-Meier curve has smoothened here, but we have to use some statistical procedure. That means you have to assume this is this point, this is the even time, this is also the even time. You take it, this is also variable, this is also the variable function, and solve this one, we will get beta 1 and gamma in between these things. When applying these things for this interval, we can get these values. But when using the bootstrapping, simply you will get the estimates for all values. This is the nice things as happened. So when comparing to the survival estimates, we will get the same survival estimate. Kaplan-Meier 9130, this is 9150, this is for variable survival estimate. I already mentioned we will get the survival estimate for the censored observation also while using the bootstrap survival concept. Here also you will get the survival estimate for any time with the help of the variable smoothing concept. So another concept, this is up to this one part. Another things, I simulated the 3 types of data with the help of the Lindyar package. Then here one is a variable function with a scale parameter 1 and shape parameter 1. Another is 1 and 0.5, 1 and 1.5. So one is a constant and increasing and a hazard. To censoring rates also I have taken 10% and 30%. Number of sample size also taken. But this is a variable. Another they have taken the censoring as a uniform distribution. So this is rank sensor function in Lindyar package I have used. So while using this one, when applying simulated one survival data, making the lambda value of the exponential distribution is equal to 1 and fixing the different censoring concept. This is the different sensory. Here 10%, here 30%. Now this is the survival probability 0.75. Now this is the number of samples 10, 100, 150, and 200. Now this is the error rate. Error rate means the within the confidence interval my estimate lies or not. If it is not, that is called as a error estimate. So this is Kaplan-Meier error estimate. Now when compare these things, usually in the error estimate, bootstrap method, Nelson-Allen estimate always performs better. Similarly, when mean width of the confidence interval, bootstrap Kaplan-Meier estimate is performs well because it is the very least one. That is the one I have given here. The same pattern lies in the all exponentially parameter 1 or 1.5 or 0.5. This is for 0.5. You see here, here is also, this is 0.02. It is the very least one. Here, this is 0.2339 is the least one, but it will differ in the, this is 0.5. Now, this is 1.5. 1.5 here, it is least. Here, some difference may be occurred. Here, bootstrap Nelson-Allen, but here, this one, bootstrap Nelson-Allen, in both cases is the least one. This is the least error rate. Here is the least mean value of the confidence interval. So that means when compared to the standard method and also bootstrap method, bootstraps performs well. That is the things I got the information from this thing. So this is I've taken 1.5 by scale for different things. So the bootstrap Nelson-Allen is better than other methods in the sense of achieved error rates, regardless of the sensory rates and sample sizes. From the point of confidence interval, bootstrap KM is performed all. The another thing, we can make it as a sampling distribution of the quantile, and using the bootstrap methods, find the median of the quantile. This is also the same we achieved the while the survival estimate in the Kaplan-Meier estimate also. Both approaches gives the same estimates. Then while using the difference between the two curves, I have taken one covariate, non-maintained or non-maintained. Then while using the log rank test, it is there is no significant difference because we got it a p-value 0.07. But that is the usual procedure, log rank or any parametric test will be taken. But while you are comparing all quantiles, difference between the quantiles, whatever things when bootstrap techniques you applied median, you take it as a median of the first sample, median of the second sample, then you find it the difference and make it as a sampling distribution of the bootstrap difference of the median. Then you find it your zero lies within the confidence interval or not. If it is lies within the confidence interval, then you can say that there is no significant difference between the two samples. That can be, we can find it with the help of the bootstrap. That is also the case we achieved here. So now, other important things I have introduced now is one parameter estimated and standard error path, one sample exponential distribution. So in without sampling and with sampling, as a censoring, with censoring or without censoring, I tried it. In exponential distribution, the hazard rate is lambda is the constant because exponential lambda. By we can estimate the lambda at the estimation of the lambda with the help of this formula after log likelihood function. So therefore, n star is the number of events. This is the total time. This can be, you can estimate the lambda at. The standard error can be estimated with the use of the lambda at square divided by n at. So this is the usual procedure. When no censoring, n star can be taken as n. For censoring, you have to take only the number of even time, number of events only. Even. So another concept is by using the R survival function, when using the regression concept in time ratio method. So beta naught can be obtained with the help of the minus log lambda. Then find the confidence limits for beta naught. This is the lower limit and this is the upper limit for the beta naught. But if you want to find the limits for lambda, then we have to apply e to the power of minus u1 and e to the power of minus l1. This is the way also we can find the limits, lower limit and upper limit for my estimate for What is my estimate here is the lambda is my estimate for one sample problem, one sample. So for the two ratio between the two parameters, I have taken one covariance, maintained or non-maintained. That is, you can take it as a two sample problem. One is a maintained, another one is a non-maintained group. I want to find the hazard ratio H1 divided by H2. So while finding the hazard ratio, then you have to use the confidence interval. You use this F-test values, and then you can find the lower limit and the upper limit. The T1 bar is taken as so and so. R1 is the number of events in first group. That is the one sample. R2 is the number of events in the second sample. These are the things are given. But otherwise, I have tried in both ways also. While writing small functions, I tried it. Using survival function in R, we will get the beta naught value and the beta 1 value with the help of the survival package and the function survival regression. The hazard ratio can be obtained with the help of the e to the power of minus beta 1. The lower limit of the beta 1 can be obtained, upper limit. Then confidence limit for lambda 1 and lambda 2 are e to the power of minus v1 and e to the power of minus L1, because it is the inverse of the time ratio. So now, I have, for this one, I have taken the problem, number of samples I have taken and simulated with the lambda equal to 1, and 3 bootstrap values are I used 1,000 and 5,000 and 10,000 times I tried. So when initially, while taking the simulated one exponential survival data, then you find the lambda value, then again, and you find the values and find the number of coverage percentage. Number of coverage percentage means my estimate lies within the lower limit or upper limit. I have studied that one, and also I have studied the mean width of the confidence interval for both exponential using the normal method and also while using the bootstrap I have studied. Then also I find the mean and variance for lower limit of the confidence interval and the mean and variance of the upper limit of the confidence interval. So now these are the things I got it with the help of the simulated data. Now I have taken 100 samples, tried it 1,000 times, 1,000 bootstrap, 5,000 and 10,000. I got our coverage percentage. Coverage percentage is my lambda comes within my confidence interval 95%, here 95%, so and so. When using the bootstrap, I got like this. When you see that it value nearly it will be nearer only, and also the mean confidence width is less when compared to the general method. Bootstrap gets minimum value. These are the variants and so on. So things are. I tried it for 100 sample, 200 sample, 500 sample. Whenever samples are increasing or something, it gives the same way of the interpretations only, because this is 0.98, but here is you are getting 0.9420. Something will be very less only. Here also minimum. So while using the bootstrap, we will get the coverage percentage should be more, but this will be minimum. This will be minimum, but it is not more vary. Then I have taken the survival data with the 30% censoring. I told you already, I have simulated the data. Then I tried it the same concept here for the survival data. So the same type of the things, coverage percentage here is increasing. So somewhat so small percentage is increasing, but it's not different. So now here, this is the bootstrapping values. This is the bootstrapping. This is the normal technique. This is the normal technique 500. This is for the 500. I got these values. Similarly, I have taken the two sample problem because already I told how you can find the lower limit and upper limit with the help of the two procedure, the normal procedure. Another one is with the help of the R. I tried in both ways also. But here, this is one sample. I have taken 100 samples with following exponentially with the lambda 1, another 100 sample following exponentially with lambda n, and both I have taken 30% sample. We may take is 30 or 40 or something, but I have taken for this purpose only 30% of the censoring taken. Why I got it here? These are the things we got it. So now when this is 100, this is 500. While using 100, we are getting the coverage percentage 0.956, but we are getting the coverage percentage. This is called bootstrap estimate. This is bootstrap covering percentage 0.951. So this is the bootstrap mean value of the confidence interval with we got it. The same near value we got it, but when you find this one, we have to use finding the lower limit and upper limit. We have to use some concept, but here just you can use the bootstrap technique. That means you find the hazard ratio for the given data only. You take the hazard ratio and simulate it 1,000 times. Simulate the data 1,000 times or 5,000 times. This is the easiest one. Then that hazard ratio will form that 1,000 hazard ratio estimates will form a distribution. With the help of the distribution, you can find the lower limit and upper limit. But it is not like this in the case of the previous. We have to use some formula. But here I have taken one real-time data. Real-time data is a two-sample leukemia problem. So in the same problem, that is the previous one are all simulated survival data. Now I wish to confirm that one with the help of the same leukemia data. We have one covariate is that is maintained or non-maintained. Maintained is a one sample, non-maintained is another group I have taken. So here, when apply this one, this is the lower limit of the hazard ratio, upper limit of the hazard ratio, width of the confidence interval, AAC value. With the help of the AAC value, log normal is the minimum, but log logistic is only someone is different. But width of this one using our usual procedure without bootstrapping. So width of the hazard ratio, because we have two samples, that's why hazard ratio. Width of the hazard ratio when comparing to all the four techniques, log logistic is less. So this is the things we found it. But I tried it for using the bootstrap technique. This is the bootstrap technique. While using bootstrap, the same format, 1,000 bootstrap, then 5,000, then 10,000. These are the information I got it. These are the information. This is the width of the confidence interval. My hazard ratio lies. This is from exponential. This is from Bible. This is from log logistic. This is from log normal. Width of the confidence interval in log logistic model is bootstrapping is also least one compared to the other. So log here you see that 4.04, 4.04, 4.00, 3.86. But here is 3.9, somewhat little difference. Here is also the minimum is log logistic. But here while using the bootstrapping also I am getting the log logistic. With the help of this width, you can without taking AAC or something, we can take with the help of the bootstrapping, we can assume that the data is fit for log logistic model. These are the things also we can observe with the help of the bootstrap technique. These are the things I have observed. Whatever I told, I have written it in as a summary. This study examines the effectiveness of bootstrapping and the confidence interval of various parameter interest while handling survival data for a different groups. Bootstrap survival gives value for censored and uncensored cases for each time while applying the finding the survival probability for our even time or sensor time also. There is no jumps here, and also confidence width also minimum when compared to the Kaplan-Meier. So here also I given test of significance of the estimate also tested by bootstrap method. Log rank test we have to use some chi-square test also, but here without using this one, with the help of the difference between the median or difference between the quantities, we can observe it. It is the same or there is any significant difference between the survival pattern of the distribution or not. So throughout the analysis with the 1 and 2 samples, finally I have taken some simulated survival data. The bootstrapping did not seem to perform significantly better in lot of the cases because there is some variations are there. Mostly bootstrapping performed better when sample size was increased. When we have seen that 1,000, 5,000, then 10,000 times. Increasing of bootstrap samples gives only small variations. Then in the case of the real-time data, it is observed that width of the confidence interval for hazard ratio is least in log logistic and also bootstrap log logistic. From this bootstrapping concept, easily apply best model for our data. These are the findings I have observed while using the bootstrap technique for the survival data. So thank you. These are the reference I have taken. Hello? Hello?
Thank you very much, Ramakrishnan, for your nice presentation. One question to be asked from the participant? Anybody? Any one question? Any one question? Any question from the participant, please? Hello? Any question? If it is no question, let us thank the speaker for his nice presentation. Thank you very much, Ramakrishna. Thank you.
Yeah, Professor.
So let us call upon the next speaker, please.
Excuse me, Professor.
Yeah.
Someone is calling.
Yeah, can I ask a question?
Yeah,
please.
Okay. So you have mentioned, there are three types, parametric, non-parametric, and semi-parametric, right?
Yeah.
So can you just explain what is exactly the semi-parametric and can you cite an example with data set?
Yeah. So here, my slide itself I have given talks for semi-parametric model. No, so that's this slide.
Yeah.
Parametric, my times does not follow any distribution. For the semi-parametric, we have introduced the parameters in the exponential form. For parametric, fully it follows some distribution. We have to assume my time follows exponential.
That's true. Parametric, it follows some distributions, and of course, non-parametric means it does not follow some particular distribution. But my question,
you want Cox?
Yeah,
this is the Cox model.
No, that's why that is how my question. So how do you go for semi-parametric? Parametric is very clear, non-parametric is very clear.
Yeah.
But semi-parametric, how do you explain?
Because we have to assume our hazard ratio is constant throughout two things, throughout the two samples, two groups. Assumption of constant hazard. So here, this is the hazard function is h of t of x. Similarly, x is my covariate. X is the covariate. You can take it as your covariate is a dichotomous. That is 1 and 0. Okay. Then, therefore, your value, only the exponential function should be the greater than 0. Hazard ratio value should be always greater than 0. That's why the Cox formed this model. This is the hazard. This is h naught t is called as the values, our variables t, x can be separated into two parts. One is baseline hazard, another one is exponential form. Why they are given as exponential form means when you are dividing these two, when finding the hazard ratio, automatically this baseline hazard will be cancelled. Then this should be the exponential of the linear combination of our variables, so beta 1, x1, beta 2, x2. This value should be greater than 0. This is the excellent things introduced by the Cox in 1972 for the survival distributions.
Okay, thank you. Thank you, Professor.
Thank you.
Thank you, sir. Thank you very much. Any other question? Any other question, Professor? No, if it is not the question, let us thank the speaker for his nice presentation. Thank you very much, sir. Thank you, Ramakrishna.
Thank you, Professor. Nice opportunity. Thank you, Professor.
Thank you. Let us call upon the next speaker, please.
Thank you, Professor Elangovan. The
Yes.
session is over. Thank you for chairing the session.
Okay.
And also, let us give a big clap to both the speakers, Professor Rudrapradhan and Professor Ramakrishnan, for their excellent talks.
Yeah, okay. Thank you very much, sir.
Thank you so much.
Thank you. Thank you, sir. Thank you.
Now let us move to the next session. Next session is a particular session, in fact, a special session organized by Professor D.K. Ghosh. Teresa, please introduce the chair and the session organizer, Professor D.K. Ghosh, and thereafter do the needful for continuing the session in a smooth way.
A warm welcome to everyone. I hereby welcome you all to the technical session 25 with session chair Dr. D.K. Ghosh. Professor D.K. Ghosh did his BSc and MSc in statistics from Bhagatpur University and PhD specialized in design of experiments from ISI Delhi. He was a professor and head Department of Statistics, Saurashtra University. Presently, he is assigned as UGC BSR Faculty Fellow. He is a Fellow of Royal Statistics Society and won CSRs, JRF, and SRF, and won numerous awards through his academic life. He has an academic and administrative experience of 44 years, published more than 150 research papers, and supervised 43 PhD theses and published 3 books: Distribution Theory, Factorial Experiments, and Biostatistics. He has reviewed papers for more than 20 national and international journals. We are really lucky to have you with us, sir, sharing the session today. Without delaying further, I once again extend a warm welcome to you on the behalf of the organizing committee and kindly request you take over the session. Over to you, sir.
Dr. Satish Kumar, thank you for your offer to me to work as a chairman. Actually, I'm remembering that a few days back, he asked me to arrange a symposium in design of experiments, and I consulted few persons, and the 3 persons agreed to give a talk on the design of experiments. So now we have the 3 persons, and we have the 90 minutes. So each one will get 30 minutes. So 25 minutes will be strictly followed by them. 5 minutes maybe for the question and answer. So we are just starting 39 it is. We are going to start it. The first speaker is Dr. Nilesh Kumar, and he did his PhD at Delhi University under Dr. Poonam Singh, and he has joined Marwari University, Rajkot, very recently. So his topics is space filling, orthogonal and nearly orthogonal Latin hypercube designs for computer experiments. So he has obtained some of the orthogonal Latin hypercubic designs using some computers. That techniques he is going to explain before us. So I request Dr. Nilesh Kumar, please go ahead. Dr. Nilesh Kumar.
Hello, sir. Am I audible?
Dr. Nilesh.
Yeah, sir. Hello.
Yeah, audible. You are audible.
Sir, good afternoon.
Professor Dr. Ramakrishnan, please stop your sharing.
Sir, good afternoon. Professor, I'm very thankful to Professor Satish Kumar, Professor Ghosh, and all the participants. May I share my screen? Is my screen visible, sir?
Yeah. Now it is fine. Okay.
Okay, sir. My topic of, I'm Nilesh Kumar. My topic of presentation is space filling orthogonal and nearly orthogonal Latin hypercube designs for computer experiments. This is a joint work of Professor Poonam Singh and myself. Actually, space filling designs are designs which are basically used for the computer experiments, and these designs actually fill the input space of the input space very uniformly as possible. The second thing is here is the orthogonal Latin hypercube design. A Latin hypercube design, actually it is a sampling design, and it was introduced in 1979 by Mackay till 1979. And this sampling design is better than the simple random sampling and stratified random sampling in terms of the variance. This design was actually this was introduced as sampling design, but here in this talk I will be discussing about the orthogonal and nearly orthogonal Latin hypercube designs for computer experiments. Now, the question is, what is computer experiment? Computer experiment is just an experiment which is conducted using some computer model, means computer code. Computer code is working behind the system to produce the output. Actually, there are some processes in nature which are very complex that cannot be we cannot have an idea about the form of the response. In that case, that the response is considered as black box, and in that case, we actually generate the output using computer code. That is called a simulator. Now, for example, earthquake, volcanic eruption, change of weather, climate, all these processes cannot be replicated or cannot be conducted in laboratory. These are infeasible. Now, in that case, certain computer programs which are very difficult to it takes long time to conduct or to run for a single input values. So the problem is how to choose the input values from the input space. Now, the outline of my presentation is, and that is where the design of experiment comes into play. Now, outline of my presentation is, first I'll be giving an introduction to computer experiments and some designs, then preliminary some results, construction methods, and then a comparison with the existing methods, and then conclusion, and then some important references will be there. Introduction. Usually, computer experiments are conducted to explore the relationship between a set of input variables to the physical system of the process and the resulting output variables. These are usually basically conducted either physically or numerically using certain computer programs. Now, the one which is conducted in laboratory is the physical experiment, and the one which is conducted using the computer programs is computer experiment or simulation. Now, a simulator or the computer code or the one with which we generate the output or the response at the input variable is the simulator. Such experiments are conducted when the process is very complicated, expensive, time-consuming, or even infeasible. In contrast to physical experiments, the response from a computer experiment is deterministic, and this calls for a different approach for design and analysis of these experiments. And one of the important steps in implementing these experiments is choosing a suitable experimental plan. The commonly used designs for computer experiments are Latin hypercube designs, uniform designs, and maximum designs. Among these, the most popular is the Latin hypercube designs, as it is very easy to construct. It has inherent one-dimensional uniformity property, flexibility to different structures, that is sliced or nested. Now, the columns, it can also be used for categorical variables also, not only for continuous categorical variable also. The columns of a randomly generated Latin hypercube may be highly correlated, and efforts have been made to control the correlation between the columns of an LSD. Ye 1998 was the first who gave an algebraic method using permutation group theory to construct Latin hypercubes with orthogonal columns. A Latin hypercube is said to be orthogonal if the correlation between any two columns is 0. The thing is that orthogonality and space filling are the two important criteria which are used to select LSDs, Latin hypercube designs. Orthogonality is directly useful when the polynomial model is used to fit the data, and space filling property allows the points to select the designs which are scattered uniformly inside the input space. So these two tools are basically used to select a design from a class of Latin hypercube designs. Orthogonal Latin hypercube designs ensures the independence of estimates of linear effects when a first-order model is fitted, and when second-order effects are present, the OLSTs must satisfy these two conditions, that the element-wise square of each column is orthogonal to all the columns in the design, and the element-wise square of any two distinct columns is orthogonal to all the columns in the design. An OLST satisfying these two conditions is called as the second-order OLSTs. Now, the methods, from literature, we observe that the methods of construction of OLSTs are basically based on permutation matrices, rotation matrices, and some spatial matrices, or some computer search also. Now, the one which is based on permutation matrices has been explored widely and is based on rotated factorial designs. One which is based on the permutation matrix is relatively less explored, and so we are focused in this talk on the methods based on permutation matrices only. Among these methods, the method based on the permutation matrix has a strong mathematical background, and it was introduced by year 1998. It is a JASA paper, and for n is equal to 2 raised to power k plus 1 plus 1, 2 raised to power k plus 1, and m is equal to 2k columns. Later on, Chopin and Lucas extended the work of year 1998 to accommodate some more columns, but for k less than equal to 11, and conjectured that the method is true for all k. By relaxing orthogonality between the columns of a Latin hypercube, Chopin and Lucas gave an optimization algorithm based on modified L2 discrepancy and Euclidean maximum criteria to construct nearly orthogonal Latin hypercube designs with better space filling properties. Later on, using permute and stake optimization algorithm, Parker 2022 extended NOLSTs constructed by Chopin and Lucas 2007 by sequentially adding batches of runs. However, the methods are often, these methods, that is the methods based on permutation matrices, are often criticized for a small factor to run ratio. In this work, the groups generated by the sets ATE and small at have been used to construct orthogonal and nearly orthogonal Latin hypercube designs with better space filling properties in terms of discrepancy measures, where ATs are permutation matrices of 1 to 2 raised to power k, and small ATs are plus minus 1 vectors, and E is equal to 1, 2, and so on to 2 raised to power k transpose. Notice some definitions are there. A Latin hypercube LSD NM with n rows and n columns is a n by m matrix in which each column is a permutation of n equally spaced levels. A Latin hypercube in which correlation between each pair of column is 0 is orthogonal Latin hypercube. An example is here. We can see that OLST 5.2, the correlation is 0. If we take the inner product of the two columns, it comes out to be 0. Now, an LST is said to be nearly orthogonal Latin hypercube design if minimum of rho Ij, means the correlation between any pair of the columns of L, the minimum of that is very small, close to 0.05 or 0.05 or 0.07. Some other authors, different authors have taken as different critical values or some threshold value. Then we say that the design is nearly orthogonal Latin hypercube design. Some preliminary results. This result is by year 1998, lemma 1. The subgroup generated by the set of permutations ATE is commutative, where AT is equal to I Kronecker and so on, Kronecker I, Kronecker Z, Kronecker so on to Z is a permutation matrix. E is equal to 1, 2, and so on to 2 to the power k. I is 1, 0, 0, 1 identity matrix, J octagonal identity matrix. And the Kronecker of I is taken k minus t times, and that of J is taken t times. The commutativity of the subgroup is defined as AB is equal to BA, where A and B are the elements of the subgroup. Lemma 2. Lemma 2 is also by year 1998. The subgroup generated by the set of vectors AT under element-wise product is commutative, where AT is equal to 1 Kronecker 1 and so on. Kronecker B, Kronecker 1 and Kronecker and so on, Kronecker 1. B is minus 1, 1, 1 is 1, 1. Kronecker of B, 1 before B is taken k minus t times, and that of 1 is 1 after B is taken t minus 1 times, conjecture 1. For k greater than 11 and m greater than 67, the Latin hypercube constructed using the procedure of Chopin-Lucas 2007 is orthogonal and accommodates maximum of 1 plus k kc2 columns. Now the construction methods that we are proposing, that the construction of OLST 2 to the power k plus 1 to the power k and OLST 2 to the power k plus 1 to the power k using generator sets AT, ET is equal to 1, 2 and so on to k, and AT, small at defined in lemma 1 and 2 respectively. We shall use these two generator sets for the constructions, and that will accommodate more columns than the existing methods. The construction based on this construction is based on three square matrices P, Q, and R. P matrix is the permutation, is a square matrix which each column is a permutation of small e. Q matrix is a plus minus 1 matrix that's constituted to power m or k factorial design, complete factorial design, and R is just the element-wise product of P and Q matrices. The columns of P are chosen according to the equation 1. Now, A naught E, AI, E, and AI is the E, means all the pairwise combination of ATs, and then all the three pair, that is the tuples, the combination of three ATs, and then and so on to combination of all ATs, where ATs are permutation matrices as defined in lemma 1. We choose the Q matrix according to the equation 2. Similar way, steps of construction for OLSD to the power k plus 1 to the power k. Step 1, with E is equal to 1, 2 and so on to the power k, transpose, construct P matrix using equation 1. Then we construct Q matrix using equation 2. Then construct R matrix by taking the element-wise product of the P and Q matrices. Suppose L is equal to R transpose, 0 transpose minus R transpose transpose. Then L is OLSD to the power k plus 1 to the power k. OLSD to the power k plus 1 to the power k can be obtained directly by taking L bar is equal to R bar transpose minus R bar transpose transpose, where ith element of R bar denoted as Rij bar is defined by equation 3. Now we shall take an example. Example 1. For k is equal to 3, we will have E is equal to 1, 2 and so on to 8 transpose. Step 1. The columns of P matrix obtained using equation 1 are P1 is A naught E. A naught is just identity matrix into E, the same. 2 we get as per. With k factors with containing all the interaction terms. Now the R matrix is the Hadamard product of P and the Q matrices. So R matrix is like this. This is the R matrix. Now R matrix is here is an orthogonal matrix. Now, using this R matrix, we can construct OLSD. Now, thus L is equal to R transpose, 0 transpose minus R transpose transpose is OLSD 17H, and L bar is equal to R bar transpose minus R bar transpose transpose is OLSD 16H. We can see that R bar can be obtained from R very easily. Now, the theoretical results to prove the columns of OLSDs are now given in lemma 3. These are the theoretical, the proofs are very lengthy, so I'm not covering the proof. Lemma 3. Lemma 4. These are the theoretical results. Now theorem 1. If the matrices Pk and Qk are obtained as in lemma 3 and 4 respectively, Rk is equal to Pk into Qk, where this dot denotes the element-wise product, then for any integer k greater than equal to 1, Rk and Pk star into Qk, element-wise product of transpose into Qk transpose into Pk star into Qk is equal to Rk transpose into Rk is equal to small rk I to k, where Rk is equal to the power k plus 1 to the power k plus 1 plus 1 upon 6. Theorem 2, if the columns now, theorem 1 says that the R matrix that we have constructed above is an orthogonal matrix, and this gives a proof actually of that. Now, if the columns of the P in the Q matrices are constructed as in lemma 3 and 4 respectively, Rk is equal to Pk into Qk, then L is OLSD 2 to the power k plus 1 to the power k, and L bar is equal to R bar transpose Rk bar transpose minus Rk bar transpose is OLSD 2 to the power k plus 1 to the power k. L bar and L satisfy properties A and B, as L and L bar are just in the form of actually the plus and minus, means folded over, the folded form, and so it easily follows property A and B. Now the remark 1, from the remark 1, the method of Sopa and Lucas 2007 is just a special case of the method presented in alpha if all ATs and pairwise combination of ATs are used to construct the P matrix. Thus, theorem 2 provides a proof of conjecture 1. Similar to Sanatel 2009, Yang and Liu 2012, the designs constructed in theorem 2 accommodates maximum possible factors. Now, the construction of OLST are 2 to the power k plus 1 2 to the power k, and OLST are 2 to the power k plus 1 2 to the power k. Now, these generator sets, the two generator sets, ATE and small at, have been used to construct the OLSTs for some flexible run sizes, and the steps are here. Beta gives the steps of constructions. Here the steps of constructions for OLST are 2 to the power k plus 1 to the power k. These are the steps of construction for this. The method is little different, but obtained from the same generator sets. We take an example. Theorem 3, if U and U bar matrices are constructed as above, then L is equal to U transpose minus U transpose, and L bar is equal to minus U transpose or OLST R times 2 to the power k plus 1 to the power k, and OLST R times 2 to the power k plus 1 to the power k respectively. Example 2. For k is equal to 2, R is equal to 3, OLST 25.4 and OLST 24.4 can be constructed. Because R is 3, K is 2 means E will be going from 1, 2 and so on to 4, means K 2 to the power K. So 1, 2, 3 and 4, the columns will be permutation of 1, 2, 3 and 4 obtained from equation 1. Now from the step 1, for L is equal to 1, 2, and 3, we construct the P matrices P2L for that is P21 is like this, P22, P23, and then we construct the Q matrices. Q matrices for corresponding to the P matrices are same now. And for L is equal to 1, 2, and 3, we construct R matrices. These R matrices are R2L for L is equal to P2L, element-wise product of Q2. Now, Q is equal to R21 transpose, R22 transpose, or R23 transpose. Now here we obtain the U matrix. We just take 0 in the middle and U and then minus of U, we obtain the OLST 25.4. And if we set the levels by subtracting 0.5 from the P matrix here obtained here, and then multiplying by the corresponding Q matrix, we obtain U bar, and then using U bar, just take the foldover of U bar, we get L bar, and we get the OLST 24.4. Construction of nearly orthogonal Latin hypercube designs. All the results obtained above for E is equal to 1, 2, and so on to 2 to the power k transpose are true for E is equal to 1 plus B, 2A plus B, and so on to the power k A plus B transpose, where A and B are real numbers. Lineker 2010 proved that an LST with orthogonal columns cannot be constructed for N is equal to 4k plus 2. Means 4s to the power k minus 1 plus 2 runs, where s is positive integer. For these runs, LST with small correlation between the columns can be constructed. Yang and Liu gave a method to construct NOLST to the power k plus 1 plus 2 to the power k, NOLST to the power k plus 1 plus 3 to the power k, but the space filling properties of these designs are poor and cannot be improved. For E is equal to A plus B, 2A plus B, and so on to the power k plus B, transpose, the orthogonal designs constructed using theorem 1 can be used to construct nearly orthogonal Latin hypercube designs with better space filling properties. Now, this is theorem 4. Theorem 4, using theorem 4, we can construct NOLSD to the power k plus 1 plus 2 to the power k, and using theorem 5, we can construct NOLSD to the power k plus 1 plus 3 to the power k. Using these theorems, we can obtain the lower bound on the correlation. The correlation, actually, the minimum correlation is that rho I J F is equal to 6 upon this. This is the minimum correlation between any two columns, of the F. Comparison with the existing methods, the existing constructions for OLSTs based on generator sets ATE and small at are due to Ye 1998 and Siopa Lucas 2007. For n is equal to 2 to the power k plus 1 runs, Ye's procedure can accommodate at most 2k variables. The method of Siopa and Lucas 2007 can be used to generate designs for at most 1 plus k plus 2 to the kc2 variables, while our method can accommodate 2 to the power k variables, substantially larger number of variables for the same run size. From table 1, we can see that the proposed method accommodates much more number of variables or factors than the existing methods based on the generator sets. There are some where NA is there, means these methods we cannot construct for these runs. As we increase the value of k, the situation gets very worse for the existing methods, but the proposed method accommodates more factors than the existing methods. Now, this comparison is based on the desirable properties for a design for computer experiments, actually the orthogonality and the space filling property. The Ye's method and Siopa and Lucas methods can be used to construct orthogonal, nearly orthogonal designs, and it can be used to improve the space filling properties of the designs. But this method, due to Sun et al. 2009 and 2010 and Yang and Liu 2012, those methods cannot be used to improve the space filling properties. They are orthogonal. Those methods can be used to construct orthogonal Latin hypercube designs, but cannot be used to improve their space filling properties. Now, the orthogonality of OLSDs constructed in alpha and beta methods depends on the choice of permutations of E. For k is equal to 3, E is equal to 1, 2, 3, and so on to 8 transpose. Thus, there are 40,320 possible permutations of E. After complete enumeration, we find that there are 340 permutations of each LSD is orthogonal. Out of 640 OLSDs, OLSD 17.8, ML2 and CL2 are minimum for OLSD corresponding to E is equal to 1, 2, 3, 7, 5, 6, 4, 8 transpose, and maximum for OLSD corresponding to E is equal to 1, 2, 8, 7, 5, 6, 4, 3 transpose. Table 3, we can see that for this permutation, for this particular permutation of E, the space filling property in terms of the discrepancy is improved, because the minimum discrepancy is 0.28935111, and the maximum is this. Now, if the design has a low discrepancy, ML2 discrepancy is the minimum is this one. Now it is lower, and so we can see that the design OLSD 17.8 has better space filling, and it has been actually just using computer search we have obtained this, the permutation. That is 640 permutations are corresponding to the 640 permutations of E. The designs are orthogonal, and out of that, the best one is obtained corresponding to E is equal to 1, 2, 3, 4, 3, 7, 5, 6, 4, 8. The existing methods, we can see that the Sun et al.
You have only now 3 minutes.
Okay, sir. Okay, sir. I'll try to wind up.
You try to complete.
Okay, sir. Okay, sir. The maximum discrepancy, actually we cannot optimize or improve the space filling properties using these two existing methods, but our method can be used to improve the space filling properties of the orthogonal Latin hypercube designs. Figure 1 shows the two-dimensional projections of OLSD 17.8 with variables scaled to -1, 1 obtained using the best permutation, and is shown below. Here, this is we can see from this figure, the points are very uniformly scattered within this space, the input space, the two-dimensional projection from this. This is the two-dimensional projections of the designs, and we can see that the points are uniformly scattered. Now, this is the two-dimensional projection corresponding to the existing method due to Yang and Liu 2012. We can see that the points are not uniformly scattered; they are just clustered along a line, or they are clustered. Yes, they are not uniformly scattered. They are not better in terms of space fillingness, and so now the summary and the conclusion. In this paper or in this work, we have developed a novel algorithm to construct OLSD to the power k plus 1 to the power k, OLSD to the power k plus 1 to the power k, by the groups generated by ATE and small at. The proposed method has been used to prove the Siopa and Lucas 2007 conjecture on the construction and existence of OLSDs. It has been extended to construct some flexible the OLSDs for some flexible runs. The generator sets have been used to construct some nearly orthogonal Latin hypercube designs for which the orthogonal Latin hypercube designs do not exist. Now, the method, as discussed earlier, the method of Sanatel 2009 and 10 and Yang and Liu 2012 cannot have poor space filling properties and cannot be improved under any criterion. Our method is better and can be used to improve the space filling properties of the designs. Now, for k greater than equal to k, but actually we have done for k equal to till k equal to 3. But for k greater than equal to k, the number of permutations of E is so large that we cannot do the complete enumeration. So we can use some exchange algorithm or the method of optimization method of Siopa and Liu.
I think you have to conclude now.
Okay, sir, this is the conclusion part. To construct the nearly orthogonal Latin hypercube designs with improved space filling properties. Now, these are the references. Thank you. Thank you.
So, thank you, Dr. Nilesh. It is a good talk on orthogonality of orthogonal Latin hypercubic designs. Now, I think in 1 minute is there. Anybody can ask 1 or 2 quick questions. Please ask. Okay, Srinivas, you please ask a question.
Pranam, sir. Sir, I have a couple of questions, quick queries.
Okay.
Dr. Nilesh, which of these two parts is more important? Like orthogonality is more important or space filling? And how, if at all both are important, then how we will take care of that?
Okay. Ma'am, it depends. Actually, Bingham et al. It was Bingham et al. Who argued that 2009, who argued that if we search a space filling design within the class of orthogonal design, it is easy to obtain that. Means the orthogonality is a tool to obtain the space filling designs. If we actually to choose a space or select a space filling design, we restrict a class of design, a class of Latin hypercube design, and then we try to select the one which has a better space filling using some criteria.
Then
now,
why can't we depend on orthogonal arrays to construct them?
Actually, orthogonal arrays have been used to construct orthogonal Latin hypercube designs. Rotated using some rotation matrices. Actually, this has been done by so many authors. Actually, this is full of publication. You can see that the rotated orthogonal or rotated factorial designs have been used to construct orthogonal Latin hypercube designs, which has actually low dimensional projection, because you know orthogonal arrays have certain strength. If it is of strength 3, if you project the design on a 3-dimensional region, you get uniformly scattered designs. Means low dimensional projection will be highly uniformly scattered with the highest space filling.
Okay. At least in ISRA, I know few work has been done.
Lots of work has
Metrica
been done.
Metrica and all, some publications are there. You can compare with them also, I think. Thank you. Thank you, sir.
Thank you.
Nilesh, I just asked you one question.
Yes.
Did you analyze the data for orthogonal Latin hypercube design?
Actually, in real situation, I have not applied these designs.
But only
Real
for
data,
the commutative purpose.
So these designs are just theoretical part. I'm trying to have some real data from complex processes such as weather, change of weather, or some complex processes where we can have some data and apply these designs.
Why I am asking? Because the number of factors are quite larger than the number of run. So this may create problem for the analyzing the data.
Sir, in computer experiment,
Retiring, he is now doing still some research, and I think he did PhD under Dr. Narasimha Rao, who was the in fact student of Professor Hemen Das, my guru, and several people are always changing their style of working, but Dr. Victor Babu never changed. He was still on the rotatable lines, and he has published more than, I think, 160, 170 research papers, produced a good number of research scholars also. So if you find there is a talk anywhere on second order rotatable design, you think 90% cases this is a Victor Babu. So now today's talk is on second order slope rotatable design of second type. So I request Dr. Victor Babu, please go ahead.
Share this. Thank you, Professor Ghosh. Are you hearing?
Yes, I'm hearing, sir.
Okay. Thank you, Professor Ghosh. And thanks for the organizers for giving this opportunity. And I thank each and everyone who presented here in this conference. I particularly thank Professor Satish, who invited me for this presentation. So I go to my paper. The title of my paper is, as you see on the screen, second order slope rotatable designs of second type. Coming to the introduction part, the property of rotatability was proposed by Box and Hunter in 1957 for response surface designs and constructed second order rotatable central composite designs. Dasar Narasimham is my teacher, mentor. Narasimham is my teacher and mentor who worked under the direction of late Professor Raman Das. Is constructed second order rotatable designs using balanced incomplete block designs. Similarly, several others have constructed second order rotatable designs, namely index of rotatability by Draper and Gutman, measure of rotatability by Corey, and Park et al. Suggested measure of rotatability for second order response surface designs, etc. And myself and my scholar Vasundhara Devi have suggested modified second order response surface designs using BIBD. Coming to the present construct, Kim 2002 introduced new type of rotatable central composite designs. I call this as the second type with the actual points indicated by two numbers. My scholar and myself studied second order rotatable designs of second type using central composite designs, balanced incomplete block designs, and Subha with the two uncoupled block sizes, etc. The study of rotatable designs mainly emphasized on the
Sir,
estimate.
your slides are not moving.
It's not moving, madam?
Yeah.
Slides are not moving, Dr. Babu.
Okay. Let me check. Is it okay, sir?
Yes, sir. Now it's okay, sir.
Right. Okay. The study of rotatable designs mainly emphasized on the estimation of responses and its precision. Estimation of difference in responses at two different points in the factor space will often be of great importance. If difference at 2 points close together is involved, estimation of local slope, we call it as rate of change of the response surface, is of interest. Estimation of slopes occurs frequently in practical situations. For example, there are cases in which we want to estimate rate of reaction in chemical experiment, rate of change in the yield of a crop to various fertilizer doses, rate of disintegration of radioactive material in an animal, etc. Coming to the slope rotatable designs, Haddon Park 1978 introduced slope rotatable central composite designs. Myself and Narasimhan Garu constructed second order slope rotatable designs using balanced incomplete block designs. And myself and Narasimhan Garu studied second order slope rotatable designs through a pair of incomplete block designs. And myself and Narasimhan constructed second order slope rotatable design using pairwise balance design, etc. And we have studied a new concept called modified slope rotatable central composite designs and constructed these modified slope rotatable designs using central composite designs and balanced incomplete block designs in 2005 and 2006. And a review was suggested by me in 2007. Particularly, Park and Kim developed a measure of slope rotatability for second order response surface experimental designs. And myself and my scholar studied slope measure of second order slope rotatable designs using central composite designs, BIBD. Similarly, Jocelyn and myself studied measure of modified slope rotatability for second degree polynomial using BIBD, etc. We have studied similar papers in the second order rotatable designs, second order slope rotatable designs, and second order measure of rotatability, second order measure of slope rotatability, etc. Specifically coming to this particular paper, Kim and Co. introduced second order slope rotatable design of second type using central composite designs, and they constructed this design using central composite design for 2 less than or equal to V less than or equal to 5. V stands for the number of factors. My scholar and myself further developed this second order slope rotatable design of second type using central composite designs for 6 less than or equal to V less than or equal to 17. And further, we have studied slope rotatable central composite design taking actual points between 2 to 4. And my scholar and myself studied second order slope rotatable design of second type using pairwise balance designs. And we have also studied construction of second order slope rotatable design of second type using symmetrical unequal block arrangements with 2 unequal block sizes. In this paper, an attempt is made to develop a new method of construction of second order slope rotatable design using second type using balanced incomplete block designs. Different methods of constructions of second order slope rotatable designs of second type using central composite design suggested by Kim and Co. Pairwise balance design suggested by Ravi Kumar and myself, and symmetrical unequal block arrangements with 2 unequal block sizes suggested by myself and Victor Babu are also compared in this paper. It is found that in some cases, this new method leads to second order slope rotatable designs of second type with less number of design points compared to second order slope rotatable designs of second type using CCD, pairwise balanced design, symmetrical unequal block arrangements with 2 unequal block sizes. Specifically for V equal 7 factors, this new design needs 85 design points, whereas the corresponding second order slope rotatable design of second type using central composite design suggested by Kim and Co. 2004 needs 133 design points, whereas the corresponding 93 design points. For V equal 99 factors, this new design needs to 133 design points, whereas corresponding SOSRD of second type using CCD needs 165, pairwise balance design needs 213, and Subha with 2 unequal block sizes needs 181 design points respectively. For V equal 3 factors, This new design needs 261 design points, whereas the corresponding second order slope rotatable designs of second type using central composite design suggested by Kim and Co. Needs 309 design points, and pairwise balanced design and Subha pairwise balanced design suggested myself and my scholar needs 565 design points respectively. I'm going to the construction method of second order slope rotatable design. First, then I will extend this to the second order slope rotatable design of using BFAD of second type. A general second order response surface design D XIU for fitting the second order response surface equation, which is given in equation 2.1, where XIU denotes the level of the ith factor, I takes values 1 to V, and in the uth run, U takes values 1 to N of the experiment, and epsilon U's are uncorrelated random errors with mean 0 and variance sigma square. Then D is said to be a second order slope rotatable design if the variance of the estimate of the first order partial derivative of y of x1, x2, etc., xv with respect to each of independent variable xi is only a function of the distance d square summation xi square is equal to xi, d square is given by summation xi square, I takes values 1 to v of the point x1, x2, etc., xv from the origin of the design. The general conditions for second order slope rotatable designs are given as follows. We refer the papers for this general conditions, Box and Hunter, Adam Park, and Victor Babu Narasimham, 1991 paper. The general conditions are as follows. These are not the general conditions. Then we say that these are the general conditions. These are the conditions to simplify the. First, we have taken the to simplify the normal equations. We have taken these restrictions. The restrictions are as follows. All odd moments are 0. In other words, when at least one odd power xi is equal to 0. That is, summation xi is equal to 0, summation xi xj is equal to 0, summation xiu xju square is equal to 0, etc. Then second condition, summation xi square is equal to constant n lambda 2. Summation xi to the power 4 is equal to constant cn lambda 4. Then summation xi square xj square is equal to constant n lambda 4. These are the conditions similar to the second order rotatable design. Here in the rotatability we take c is equal to 3. Here we place c as it is in the slope rotatability. The variance and covariance of the estimated parameters are given in equation 2.3. Variance of B naught is given here, variance of BI is given here, variance of Bij hat is given here, etc. And other covariances vanish. An inspection of the variance of B naught hat shows that a necessary condition for the existence of a non-singularity condition is lambda 4 by lambda 2 square should be greater than V by C plus V minus 1. We call this as a non-singularity condition, which is very important for the construction of the second order rotatable designs. Second order rotatable designs and second order slope rotatable designs, which is given in equation 2.4. For the second order response surface, which is given in equation 2.1, for that we are finding the variance of the estimated response, which is given in equation 2.5 and 2.6. The RHS of right hand side of the equation 2.6 to be the function of d square summation xi square. I takes values 1 to v alone for the slope rotatability is 4 times variance of Bii hat is equal to variance of Bij hat. This condition is given by Had and Park in his paper, Construction of the Second Order Slope Rotatable Design using Central Composite Designs, which was published in Technometrics in 1978. On simplification of 2.7 using 2.3, we get a condition called E lambda 4 into V into 5 minus C minus 3 whole square plus lambda 2 square V into C minus 5 plus 4 is equal to 0. This condition we have obtained by using the construction of second order slope rotatability condition using balanced incomplete block designs. This paper was published in 1991 in Communications in Statistics Theory and Methods. Therefore, we say that condition ABC of 2.2, 2.4, 2.8 give a set of conditions for slope rotatability in general second order response surface designs. On simplification of equation 2.6, we get variance of dou A kappa dou xi is equal to 1 by n, which is given, simplification is given in equation 2.9. Now coming to the construction of second order slope rotatable design is in balance incomplete block design. Actually, this paper I give the only gist of this paper, which was published in Communications in Statistics Theory and Methods. The method of construction of second order slope rotatable design using BIBD is presented in the following result theorem. The design points 1 VBRK lambda into 2 power T of K union A 0 0 etc. into 2 power 1 union N naught will give a V-dimensional second order slope rotatable design using BIBD in N is equal to, N is the number of design points, is equal to B into 2 power T of K cube corner points plus 2V axial points, and N naught is the number of central points, design points, with the following biquadratic equation, which is given in equation 3.1. The design exists if at least one positive real root for the above equation exists. Then C is obtained from equation 3.2. Proof of the theorem is for the design points generated from BIBD, simple symmetric condition ABC of equation 2.3 are true. Condition A of equation 2.2 is true, obviously. Condition B and C of 2.2 are true as follows. That is, summation xi square is equal to r into 2 power T of K, which is coming from the cube corner points, plus 2a square, which is coming from the axial points, which is the constant and lambda 2. Summation xi to the power of 4 is equal to r into 2 power T of K plus 2a power 4 is equal to c and lambda 4. Then summation xi square xj is equal to lambda into 2 power K, which is given, which is also constant and lambda 4. These conditions are given in equation 3.3. From B2 and C of 3.3, we get C, which is given in equation 3.2. Substituting these values in the slope rotatability condition of equation 2.8, we get the biquadratic equation, which is given in equation 3.4. On simplification of equation 3.4, we get the biquadratic equation, which is given here in the 3.1. This is the actual new method of construction of second order slope rotatable designs of second type using balance incomplete block designs. Kim 2002 introduced a second type of rotatable central composite designs in which the positions of actual points are indicated by two numbers. Chiranjeevi et al. Studied second order rotatable designs of second type using CCD for 9 less than or equal to V less than or equal to 710, where V is the number of factors. Chiranjeevi and myself studied second order rotatable designs of second type using BIBD. Kim and Co. 2004 developed slope rotatability of second type using CCD for 2 less than or equal to V less than or equal to 5. Ravi Kumar and myself further developed a second order slope rotatable design of second type using central composite designs and for 6 less than or equal to V less than or equal to 710. Again, myself and Ravi Kumar, we have studied different methods of construction of second order slope rotatable designs of second type using pairwise balance designs and symmetrical unequal block arrangements with symmetrical unequal block arrangements with two unequal block sizes. The method of construction is as follows. The design plan of second order slope rotatable design of second type using BIBD, in which the position of the axial points are indicated by two numbers A1 and A2. Here the condition is A2 should be greater than or equal to A1, should greater than 0. Let VBRK lambda denote a balanced incomplete block design. 2 power T of K denote a fractional duplicate of 2 power K in plus or minus 1 levels in which no interaction with less than 5 factors is confounded and not be the number of central points in the design. The method is as follows. Let 1 VBRK lambda denote the design points generated from the transpose of the incidence matrix of BIBD. Let 1 VBRK lambda into 2 power T of K are the B into 2 power T of K design points generated from BIBD by multiplication. This is the multiplication suggested by Das and Narasimham, which was published in Raghavan 1971. We use the additional set of actual points like plus or minus 1, 0, 0, etc., 0, 0 plus or minus 1, etc., 0, 0, 0, etc., plus or minus 1. And any second additional point, we take it as plus or minus A2, 0, 0, etc., 0, 0 plus or minus A2, 0, etc., 0, etc., 0, 0, etc., plus or minus A2 are two sets of axial points where A1, 0, 0 into 2 power T of K1 union A2, 0, 0 into 2 power T of 2 power T of 1 denote the 4V axial points generated from A1, 0, 0, etc., 0 and A2, 0, 0, etc., 0 point set. Let U denotes the union of the design points generated from different set of points and N0 denote the number of central points. The method of construction of second order slope reducible designs of second type using BIBD is given in the following theorem. We refer the papers for the construction of this method, Kim and Co. and Ravi Kumar and myself. This is the theorem, new theorem. The design points 1 VBRK lambda into 2 power T of K union A1 0, 0 into 2 power 1 union A2 0, 0 into 2 power 1 union N0 will give a V-dimensional second order slope reducible design of second type using BIBD in N is equal to B into 2 power T of K plus 4V plus N0 design points with the following biquadratic equation, which is given in equation 4.1. The design exists if at least one positive real root exists for the above equation, biquadratic equation 4.1, and C can be obtained from equation 4.2. Proof for the design points generated from the BIBD, simple symmetric conditions ABC of equation 2.2 are true. Condition A of equation 2.2 is true, obviously. Condition B and C of 2.2 are true as follows. Condition B1, summation xi square is equal to r into 2 power T of K1 plus 2a1 square plus 2a2 square is equal to n lambda 2, which is a constant. Summation xi to the power of 4 is equal to r into 2 power T of K plus 2a1 power 4 plus 2a2 power 4, which is equal to cn lambda 4, which is also a constant, where C is the slope rotatability constant. And condition C, summation xi square xj square is equal to n lambda 4, which is a constant, which is also a constant. These conditions are given in equation 4.3. From B2 and C of 4.3, we get the slope rotatability constant C given in equation 4.2. Substituting these values, lambda 2 is obtained from B1 of 4.3 and lambda 4, which is obtained from C of 4.3, and C in equation slope rotatability condition equation in 2.8, we get the equation 4.4 is a biquadratic equation. On simplification of equation 4.4 leads to a biquadratic equation given in equation 4.1. We have to solve for the equation 4.1 for the solution of A1 and A2. Example. We illustrate the theorem 4.1 with the construction of second order slope reducible design of second type for 7 factors with the help of a BIBD 77331. V is equal to number of factors, V is equal to 7, number of blocks are equal to 7, number of replication of each treatment R is equal to 3, block size K is equal to 3, and pairwise replication of each pair of treatment appears lambda 1 is equal to 1 time. The design points 177,331 into 2 power T of 3 union A1 0 0 into 0 0 etc 0 into 2 power 1 union A2 0 0 etc 0 into 2 power 1 union. We have taken one central point N0 is equal to 1 will give a SO second order slope reducible design of second type using balanced incomplete block designs in N is equal to 85 design points with one central point. Here B and C of equation 4.3 are summation xi square is equal to 24 plus 2a1 square plus 2a2 square is equal to n lambda 2 is a constant. Summation xi to the power of 4 is equal to 24 plus 2a1 power 4 plus 2a2 power 4 is equal to cn lambda 4 is a constant. Summation xiu square into xju square is equal to 8 is equal to n lambda 4 is a constant. From B2 and C of equation 4.5, we obtain C value, the slope rotatability constant value C as 24 plus 2a1 power 4 plus 2a2 power 4 divided by 8. Substituting these values lambda 2, lambda 4 and c in equation 2.8, and on simplification we get the following equation, which is given following equation is there. Let us fix, we have two unknowns a1 and n2. To obtain the solution, let us fix a1 is equal to 1. Solving the above equation, we get the simplified equation in equation 4.6, which is minus 284 a2 power 8 plus 1456 a2 power 6, etc., which is given in equation 4.6. This can be alternatively written directly from the equation 4.1 of theorem 4.1. Equation 4.6 has only one positive real root, a2 square is equal to 3.9234. That implies 8 is equal to 1.9808. It can be verified that the non-singularity condition lambda 4 by lambda 2 square should be greater than v by c plus v minus 1, which is given in equation 2.4, is also satisfied. We may point out here that this second order slope reducible design of second type has only 85 design points, whereas the corresponding second order slope reducible design of second type using central composite designs obtained by Ravikumar, Victor Babu 2004 needs 93 design points. Thus, the new method leads to a 7-factor second order slope reducible design of second type in less number of design points than the corresponding.
Victor Babu, you have now only 1 minute.
Okay, I will complete.
You please conclude it.
Okay, sir. Okay. Second, and other cases we equal 9 factors. This new design needs 133 design points, whereas the corresponding SOSRD of second type using CCD needs 165, PPD needs 213, and Subha with 2 unequal block sizes needs 181 design points respectively. For V is equal to 13 factors also, we get the less number of design points compared with the CCD and PBD. The appendix table 1 gives the appropriate slope reducibility values of the parameters A2 with we have taken A1 as 1 for the designs using BIBD and star points, and for different number of central points and not, we have obtained the results for 3 less than or equal to V less than or equal to 16. Table 2 gives the variance of the estimated response of second order slope reducible designs of second type using BIBD for 3 less than or equal to V less than or equal to 16. Table 3 gives the comparison of different methods of construction of SOSRD of second type. Table 4 gives the optimum second order slope reducible designs of second type with the minimum number of design points. These are the results we have calculated for 3 less than or equal to V less than or equal to 16 with central points. N naught gives 0 central point, 1 central point, 5 central point, 10 central point, 15 and 20, etc. These are the new designs. This is the different variances and covariance of the estimated responses of the parameters. For example, for V is equal to 3 factors, 3, 3, 2 to 1, the variance of estimated responses is given in the last column. And this is the comparison table between different methods of construction. First column indicates the number of factors, second column indicates the SOSRD of second type using central composite design, and next column indicates the SOSRD of the second type using BIBD, PBD, and SOPA with 2 unequal block sizes. This is the optimum SOSRD of second type with the minimum number of design points for 2 less than or equal to V less than or equal to 16. For V is equal to 2 factors, only CCD is available. For V is equal to 3 factors, CCD has 21 design points, BIBD has 25. Similarly, for V is equal to 7 factors, BIBD needs 81 central design points and CCD has only 93, etc. For V is equal to 13 factors. Here BIBD 13, 13, 4, 4, 1. And
I think if possible, you can conclude it.
This is our, sir.
Please conclude it.
261, CCD needs 309 design points. These are the references for the construction of these methods. Okay, sir, it is over.
Thank you, Dr. Viturao. Very nice talk on response surface design, that is slope prototypical design. Now it is open to question. If anybody has question, please ask. If no question, just I want to just query Dr. Victor Babu.
Okay.
I found that in almost all cases, number of runs are very large.
Okay.
Is there any way to reduce the number of runs?
We are trying for that, sir. We are trying for the.
Okay.
We are trying, but using different methods of constructions. In some cases, BABD is with less number of design points, and pairwise balanced design we got with less number of design points. In some cases, SUPA with 2 unequal block sizes, we are getting the number of design points, less number of design points, etc. We are studying how we can reduce the number of design points.
Okay, thank you. So thank you again, Dr. Victor Babu. Very nice talk.
Thank you.
Now we have the third speaker, Dr. Rajya Lakshmi. When Dr. Satish asked me to arrange a symposium in design of experiment, and he asked me to have at least 3 persons, I approached Dr. Rajya Lakshmi by call, and immediately she accepted my invitation. So I am thankful to Dr. Rajya Lakshmi. She was a student at Nagaurdina University, Guntur. She did PhD under Dr. Victor Babu in design of experiment, specializing in second order response surface design. I have seen her several papers also. Now she has shifted to another university called CSC College of Engineering, Konerul Lakshmaya Education Greenfield, Guntur, and I had visited also that institute. She had invited me, but she has now shifted from second order retractable design to some other design, that is the Taguchi technique. So her talk is now optimal intent process using the modified Taguchi approach. So now, without losing any time, I request Dr. Rajya Lakshmi, please take the chat.
Thank you, sir. Good afternoon, everyone. This is Dr. Rajalakshmi, Assistant Professor, Department of CSC KLF. Today, I would like to introduce about the optimal Fenton process using modified Taguchi approach. I am requesting Dr. Satish Kumar sir, please provide the access to share the content.
Please wait, please.
Okay, sir.
In which mail you have sent, Rajalakshmi? Okay. In which mail you share the?
Rajalakshmi.kottapalli, sir.
In my mail. Okay, you can share it. No accessibility from here. No need to.
But I am not getting, sir.
Just share it once again.
Oh.
Upward arrow. You click on the upward arrow. Then
yes.
entire screen. Then you can click in the middle portion, so that share button will be active. Share will get the color, blue color, and click on the share button.
Sir, is it?
Oh, okay, now it is coming. Okay, now we can go to the
now it has come. It has come.
Yeah. You can make it full screen if it is not difficult.
Yes, sir. Okay, sir. Sir, I am sharing the full screen, but it is not showing, sir, to you.
Okay, no problem. You can continue with that if it is difficult to make it full screen.
Don't worry about the sliding changing. You can go ahead with your literature.
Mode. Yeah.
You can go ahead.
That's slide mode. Okay.
Okay, sir. So thank you. First of all, I am thankful to the organizers for providing me this opportunity to give a talk on this optimal Fenton process using modified Taguchi approach. So especially I am thankful to Dr. Professor C. Satish Kumar sir and Dr. Diko Ghosh sir, and also my research guide Dr. Victor Babu sir for helping me during my research, as well as to continue. I am in this position due to sir only. So now with their permission, let me talk this session. So it's my pleasure to attend this 8th international webinar on recent trends in statistical theory and applications. It is in conjunction with the 7th annual convention of Statistic Fraternity Kerala. So sir, actually I am changing my slides, sir, but it is not moving, sir.
Oh, then you please stop sharing and share it once again.
Oh, okay, sir.
Oh, now it is moving. You can see the content.
Now it is moving.
Okay, sir.
Go on.
1 second, sir.
Yes, you can tell yourself.
Sorry for the inconvenience. Please bear with me one.
Don't worry. Don't
again, I am sharing.
Take easy. Take easy.
Yeah. Don't get person. Okay, it is fine.
Okay, sir. So I am not putting in the slideshow, sir. Directly I am presenting. Okay, sir. Thank you. Sir, is it audible?
It is audible.
Yeah.
Okay, sir. Thank you.
It is audible.
So, okay, sir. Thank you, sir. Today, my presentation covers introduction and preliminaries, review literature on the optimization process, different parameters, and what is the Taguchi approach, and how we have modified the Taguchi approach to improve the process capability, as well as how to interpret it in the multi-objective optimization. So, many of the others have used the single optimization techniques, but we tried to apply multi-objective optimization problem using modified Taguchi approach, and concluding remarks and references will cover. So next one is the objective of this study is actually in any experiments we are considering, scatter will be repeated, and that measurement error also be coming due to some unknown process variables. So this influence can be caused through the error, as well as it should not be unavoidable. Maximum we are trying to reduce this type of errors. So usually Taguchi approach is suggesting through the orthogonal arrays. So with the research which has been done through the various practical experiment, I have been motivated with the practical exposure of these type of experiments. So we try to improve that modified Taguchi approach with less error, and we want to give some bandwidth for any practical experimentation. With this motive, we have tried to introduce the modified Taguchi approach along with Professor B. Nageshwarrao sir. He was retired professor in the ISRO. So along with him, I have tried to conduct this modified Taguchi approach and also recommended few tests as per the orthogonal array and provides the range of estimates for combination with less error percentage. So usually it identifies this methodology will useful to identify the optimal process variables and demands additional experimentation for confirmation. So in recent days we are observing in machine learning or AI in the test data and trained data for the confirmation purposes. So similarly in this approach also we have gone through with the confirm. Some tests should be repeated only for the confirmation. Sir, go sir.
Yes, yes, please.
Sir, is it clear, sir? Shall I
Yeah,
continue?
it is clear. It is clear.
Okay, sir. Thank you. So one of the widely applied advanced oxidation processes, so which will be used in the Fenton process. So that Fenton oxidation has been considered for getting the results of modified Taguchi approach, and to show the validity of this approach, we considered the Fenton process. So in this Fenton process, we have considered the 4 parameters. So with that 4 parameters, as per the Taguchi approach, we have went and then we have modified. We introduced the concept of modified Taguchi approach. So in 2019, myself and Nageshwarrao sir has introduced the modified Taguchi approach, and it will be useful to avoid the signal to noise ratio technique. So actually many engineering problems we observed here, many industrial or chemical engineering problems, while we are going to the literature review, everyone is using the SN ratio transformation. But it is a burden to compute the SN ratio when compared with the modified Taguchi approach in terms of computational task as well as in terms of cost of the experiment. So due to that way, we want to reduce the experimentation burden and we want to provide the additional information with the existing orthogonal arrays only, with taking the small modifications in the existing Taguchi approach. So for solving and for trying to apply that methodology, we have chosen this oxidation process, which utilizes the ferrous iron and hydrogen peroxide to removal of the chemical oxygen demand as well as the biochemical oxygen demand. With that process, we have to get the color deficiency and decolorization should be efficiency has to improve. So COD should be maximum and decolorization should be maximum in our experiment. So the present talk is mainly based on the optimal process variables of COD and decolorization. These are the two responses. These two responses we consider. So we call it as multi-objective optimization. So of Fenton oxidation adopting the multi-objective optimization techniques. So for this, we have developed many empirical relations based on the modified Taguchi approach, and also the existing test data also be compared, and we have given the bandwidth to get the less error percentage, and also made the comparative study, and we observed that the good agreement between empirical relations and test results have been seen. So next design and methodology we followed here is the modified Taguchi approach, which is to be proposed to find the optimum process parameters and to find the expected bandwidth of the output responses of COD and decolorization. So chemical oxygen demand and decolorization of the chemical process of Fenton process. The main findings we have seen is here we have been developed a simple methodology and its validation has been done with the existing test results. These existing test results are done by the Asghar and Abdul Aziz bin Abdul bin Rahman. So these professors belongs to chemical engineering. They are in the Malaysia. So they helped us a lot to provide data in terms of, actually they have conducted with the CCD, but when we want to conduct this modified Taguchi approach, they have provided the good experimental data to us to continue for further research. So in this way, we find the expected range of the output response, and we have given the modifications in the Taguchi method. So the limitations we have observed is adequacy of the methodology should be examined theoretically, and this time we have tried to apply the same process to the Fenton process. For this experiment, it has been valid. For other experiments, how far it will be valid or not, we have to check in future. So for different materials and structures, the modified Taguchi approach is giving the more accurate results, or we want to check with the SN ratio transformation. So by introducing or by this method, by this technique, we want to try to use the Chownet's criteria, and we also want to oppose the signal to noise ratio transformation on the repeated experiments of each test run, which will provide the fruitful results and less computational burden. So preliminaries of this study is actually we have taken the Taguchi approach, which was based on the orthogonal arrays and which demands few experiments to get the information for the full factorial design of experiments, and which also minimizes the cost and time of the experiment, so that automatically it leads to less time with the cost burden will also be reducing to the farmers, or it may be to the industrialists or any researchers. So Taguchi method has been applied to obtain solutions for many engineering and industrial optimization problems have been utilized. So Taguchi has introduced the concept with the signal to noise ratio. So in the signal to noise ratio concept, we are using the lower band is better and sometimes the larger one is better. Based on the experiment, we can take it into account, and we identified the scatter in the repeated test for each test run, and also provided a single value for the single optimization problem as a response. And also we perform the ANOVA to know the percent contribution, and also we have taken into account that ANOVA also, and based on that ANOVA also we can be able to determine the optimum process variables through the Taguchi technique. So as you in the normal ANOVA will be different, and as per the Taguchi approach, we have defined some ANOVA technique that I will explain in the next slides. So many researchers have utilized this SN ratio transformation for obtaining the solution of optimization problems, and highlighted here I am briefly some notable studies will be introducing in the literature review. So now I want to give some Fenton process, how this Asgar et al. Will follow the process. As a chemical engineers, they know the properties of the chemical and how to use those to get the optimal process variables, and what are the parameters have to change to get the COD and decolorization efficiencies. So according to their policy only, we just followed their process of Fenton. So based on that and based on their suggestions only, we have utilized the data. So in their experiments, they followed the 1894 Fenton discovered transferred properties which are be useful in the metals, and they used the catalyzed hydrogen peroxide, which will be employed to treat varieties of water pollution. So this process will provide the color. This can improve the color as well as the smell. Smell should also be very, very important. So odor and color by using different biodegradability by removing the biochemical oxygen demand as well as the chemical oxygen demand. So here, this is the process they have followed. First, they have given the Fenton oxidation utilization, ferrous iron and H2O2. So it will leads to this one oxygen. So based on these properties, here we have considered the 4 parameters which are influencing the Fenton process. So the 4 parameters are pH levels, reaction time, and initial concentration of dye such as H2O2 and catalysts. Here there is a need for minimizing the consumption of chemicals and cost of H2O2. So that is our objective. So the chemicals, reduction of chemicals, and we want to reduce the cost of H2O2 also to be minimized. With that objective only, they performed the experiments. So they conducted the experiments as per the central composite designs only. But we want to take their data along with the Taguchi orthogonal arrays with different orthogonal structures, but the central composite design structure will be different. So utilizing that one based on their experiment, we get the other parameters also through the experimentation only. So based on that, we have followed and tried to get the less means we want to get the minimal consumption of chemicals, as well as we want to get the COD and the decolorization efficiency should be increased in such a way we tried. So here all the experiments are designed as per the response surface methodology using CCD and the design experiment only, using the design expert, so which is a statistical software they have conducted and also provided the results of CCD through the design expert. So here this Fenton reaction process and these parameters have been taken Asgar et al. So as I mentioned earlier, and now the initial concentrations of 4 parameters have taken. These 4 from now onwards, which we are designated with the symbols X1, X2, X3 and X4. The efficiencies of Fenton process for COD removal and decolorization were designated with the symbols Y1 and Y2. So here how to calculate the COD? So different others such as, so here as per the standard method of Eaton. So here 15 is Eaton and Eaton et al. They have provided the standard methods for examination of water as well as wastewater. So with this, as per their measurement, Y1 is COD percentage can be calculated from the CODF by CODO. So which are the chemical oxygen demand of the treated and untreated dye measurements using the UV spectroparameter. So similarly, as same as the COD, we have seen the Y2 decolorization. So decolorization should be taken as absolute value of this one and absolute value of observed values. So which is also in terms of percentage. So decolorization percentage will be considered in based on the Eaton. So here ABC, which also following the UV absorbance of the treated dye and untreated dye respectively. So to optimize the output responses Y1 and Y2, generally design expertise suggesting they are not using the manual or they are not using the modified Taguchi approach for methodology, etc. Just they put their data in the design expert. Automatically it has generated the 30 design points with the CCD, 16 factorial, 8 axial and 6 center points. The assigned low and high levels of the input process parameters are 100 to 300. So this is the lower level, low level, and 300 is the high level, and in the middle 200 will be taken as the medium level for the X1 factor. So X1 is pH, and the dye factor 5, 25, 5, 15, 25, low, medium, high. Here X3 is 10, 50, 10 is low, 30 is the medium, 50 is the high, and X4 factor is taken 2, 9. So 2 is the minimum value and 4.5 is the medium and 9 is the higher factor. So using these combinations, so one time we have given the low levels. So as per the structure of orthogonal arrays of Taguchi as well as the modified Taguchi, we have introduced the COD and decolorization factors, and those parameters have been calculated by using the modified Taguchi approach. So here modified Taguchi approach provides the range. So within that bond, we will, based on this methodology, we can able to give the band. Within that band, all the values are getting, so that the accuracy or the COD or decolorization of the Fenton process should be increasing. If any value is outside those bonds, outside those bands, automatically it leads to the low quality. So basing on this, we can use the Chownet's criteria, whether some values may be falling within the limits, some values may not be within that limits, the test data. So when we are going to conduct the experiment, we will face many problems. So some values may not be within that band, what is the required band. Some values may outside the band. So this Chownet's criteria is useful to identify which variable is responsible to get the more variation. So whether the data is statistically acceptable to get the proper accuracy in our repeated test runs. So while we are conducting the experiment, we are repeating the test data for reporting the average value, how many are above and below. But this Chownets has suggested a bandwidth using that mean and standard deviation only. He has given some Chownets ratio values. Using that one, if any value is following outside the Chownets ratio, we should not be considered. And moreover, we have to repeat this Chownets criteria only one time while we conduct the experiment. So every time application of this Chownet ratio is not acceptable. So that is the Chownets ratio will be useful in such a way to avoid the unacceptable values from the data, or we can able to remove the outliers based on the Chownets criteria in the experimentation process. So these are some of the papers which we have followed to get the modified Taguchi approach. So Nageshwar Rao sir and this Rajiv Kumar et al. And Srinivas Rao et al., they have adopted and developed the empirical relations for the rocket motor casings in the ISRO. So they tested the failure times of the rocket satellite vehicles. So using the Taguchi approach, they tried to get the optimization processes through the empirical relations developed by them, and they have applied Taguchi approach, not modified Taguchi approach. Taguchi approach has been utilized in the rocket launch vehicles. So, and they find the sensitivity of several influencing input parameters is examined in the stage separation as well as strap-on separation and satellite separation process of space launch vehicles in flight. So, Singaravelu sir and Nageshwar Rao sir together did many research papers on the same area. So now Singh et al. Also examined the effect of the WEDM process parameters, so which is the weld dilution. So in this process, they used pulse of time, pulse on time, peak currents, servo voltage, weight, wire tension. So many variables, many influencing variables have been seen to get the output response on the surface roughness. So here they have adopted the L27 orthogonal array and wire type plus on time as the significant factors have considered. So similarly, many others like Naurbaksh et al. And Lakshman and Guru Raj and these all others have made many industrial problems, tried to solve many engineering and chemical problems, agricultural experimentations using the Taguchi approach as well as the Chownets criteria, but they have used the SN ratio transformation to get the optimum process parameters. So the same approach, if we follow, we will get the same methodology can be applied to using the modified Taguchi approach. Then we are getting more than their results in many of the experimentations. So in 2019, we did 2 papers. In the 2 papers, we tried with the 2 different data experiments. So we got that modified Taguchi approach is suggestible than the SN signal to noise ratio. So these are some of the references which we have followed. Next, modified Taguchi approach. So this modified Taguchi approach is here. This is the Taguchi approach formula. Here NT equal to 1 plus NP into NR minus 1.
I just interrupt. You have only 2 to 3 minutes. So you have to conclude it.
Okay, sir. Okay, sir.
You 2 to 3 minutes.
Okay, sir. Modified Taguchi. Okay, sir. Modified Taguchi approach, here n Taguchi equal to 1 plus n process parameters into levels minus 1. So using that one, we will go with the level 1, level 2, level 3. So here A1 is the low level of the process parameter, A2 is the medium, A3 is the higher level. So 4 process parameters I have considered. So 4 each are representing low, medium and high levels. So next one is, this is the usual Taguchi approach. A, B, C, D, all the 4 combinations have taken for the 4 process parameters, and these are the output responses like Y1, Y2 and so on, Yn. This is L9 example. So as same as L9 examples, we have find the ANOVA for the given data by using the means of first mean, second mean and third mean for the 4 process parameters using these formulas, and then we find the contribution of each factor. Suppose we consider the 4 parameters x1, x2, x3, x4 which are affecting the decolorization and COD efficiencies. So here those four out of four parameters, which parameter is more influencing the process? So if any parameter is less than 2% or 5%, sometimes we may be removing that variable. Based on that, we three variables only be considered. Which one is insignificant factor, that may be removed as per the experimentation. So as per this this is the Chownet's criteria, which can define an acceptable scatter around the mean value. So here our main goal is to optimize the COD and decolorization of the Fenton process variables. For this we have taken Y1, Y2. So already I have given all those. So as per the ANOVA analysis of variance we performed, Y1, Y2, two parameters are there. Those parameters have been representing in the next tables, which initial concentrations, and we have observed that the independent process parameters of X1, X2, X3, X4 are, these are the percentage contributions on Y1. Similarly, Y2 contributions are, so maximum fourth factor, that is H2O2 factor, is more responsible to move efficiency of COD and decolorization. So as per this analysis, as per the ANOVA, we got the 250 to 300, 10 to 20, 10 to 30, and 2, 3.75. So if the values are within this band, the test data is within this band, then we get the maximum COD removal efficiency, and it can be achieved within the range of process variables, so that the efficiency can be improved with the chemical consumption and COD removal efficiency. So we have given some range of estimates for Y1, Y2 using these formulas from the ANOVA and based on the test data of each test run. So here we got from the ANOVA, we got 67.51 and 90.93 have been achieved, and the process variables identified for getting the maximum output response are X1 fifth variable, X2 fourth variable, 2, and fourth one is 1. Similarly for the Y2, that is the second optimization process. Here we got Y1 is maximum 91.95 is there, then only we will get the maximum output. So here it is also percentage, so that's why we consider it should be greater than 100, we mentioned here. So as same as the other others we suggested, based on the others suggestions, we have considered the least and highest corrections with the inclusion of fictitious parameter. So this inclusion of fictitious parameters have been taken as per our research by improving the modified Taguchi approach.
So it will conclude now.
Okay sir, within 2 minutes I will conclude, sir, please.
Okay.
So these are the process variables: dye, H2O2, dye, and pH levels. These are the four. Actually, four parameters are there. Each factor is divided into 5 levels. This is the low level, this is the high level, and medium 3 levels. So -2, -1, 0, 1, 2 levels. These two fictitious we have introduced in the modified Taguchi approach. Actually, these four only be in the Taguchi approach, but these fictitious have been considered with our interest to get the maximum levels. So here the efficiency have been considered and calculated through the L25 orthogonal array. Here we clearly mentioned that levels of Fenton process variables and the fictitious parameters and the efficiency of Fenton process for COD and decolorization. So these are the values, so which I have mentioned in the theory part, that this is the table 3 which represented the ANOVA and the efficiency. By looking this here we have seen the maximum value in X1 is at 72.58, means high level of X1. So similarly X2 is X2 high level is at X4. So 5, 4, here 3 and 1. So like that we select the optimum parameters using the modified Taguchi approach. So finally we are concluding this with the Fenton process parameters X1, X2, X3, X4 at different levels has been given, where it reaches to the maximization, and we also provide the estimated range. If the values are within this bond, then we will get this accuracy in our results. So we are also representing the data through the pictorial representations. So this is the actual editula and this is the COD percentage by developing the modified Taguchi approach. So almost all the test data should be scattered nearer to the line. So this is for the decolorization and lower bound and upper bound and our equation based on our modified Taguchi approach, how the values should be lies. For the this is for the COD and this is for the decolorization. So finally here we have adopted a simple modified Taguchi approach and we try to get the maximum percentage of COD is 75% and decolorization is also to be more than 100. So these are the references which we follow to complete this research work. So we are extremely thankful to the Abdul Aziz bin Rahman, those who did this research experimentation in their labs at Malaysia, and also thankful to the Nageshwar Rao sir. And I am also thankful to the organizers for providing me this opportunity to give a talk on this topic. Thank you, sir. Sir, please
Thank
have any
you,
doubt.
Dr. Rajalakshmi. It was a very nice talk on the orthogonal related with orthogonal array and stability techniques by taking some data. Now, if any question, please, a short question can be asked.
Yes.
If there is no question, let us thank. But just I want just query. You just said that from orthogonal array we can take some of the observations. Suppose we have a orthogonal array with 7 factors in 2 raised to 8 runs. So how we can some of this? Is there any method of taking some observation?
Yes, sir. Based on the factors and levels, I have shown that, na, sir, n number of Taguchi should be getting 1 plus n process parameters into n level minus 1. But sometimes the exact value may not be possible. Nearer orthogonal array can be chosen. So that is the
Now
process
I
we are
hand over to the Dr. Satish.
Okay, sir.
Thank you, Professor Dilip Ghosh, DK Ghosh, for arranging this session in a wonderful session on design of experiments. In fact, very good speakers with the Professor Victor Babu, Professor Nilesh, Dr. Nilesh, and Dr. Rajalakshmi. We are very much grateful to you, Professor Ghosh, for organizing this session and also chairing the session in a very nice way. Also, we are very much thankful to each of the speakers. Let us give a big clap to the speaker and the organizer. Thank you so much. I hope. Yeah. Now we can move to the next session, in fact. Hello, Professor. Good morning. Before going to the next session, today we have no lunch break time. We are tight for it, so lunch can manage in between. 2-3 minutes we can take for a break, or you can spare your anything. You can, no problem. Thereafter, we can move to the next session.
Thank you.
Hello, Neha.
Yes, sir.
Yeah. Neha, please introduce the chair and invite him for its further procedures.
Okay, sir. Greetings to all the distinguished guests. We shall now proceed to take. Sir?
Excuse me, excuse me. Okay, Neha, please continue. Please continue.
Okay, sir. Greetings to all the distinguished guests. We shall now proceed to technical session number 26. It is my pleasure to introduce Professor N. Bhadracharyalu, Head of Department of Statistics, Osmania University, Hyderabad. His journey in statistics began with earning post-graduation in applied statistics, followed by MPhil, PhD, and PGDCP. He possesses a wealth of professional expertise gained through his work experience in different statistical departments. Professor is widely recognized for his contributions to statistical research. He has published more than 85 research articles in numerous reputed national and international journals. Besides academic endeavors, Dr. Bhadracharyalu is also a life member in various statistical societies like ISPS, STS, ISAS, etc. We're privileged to have such an eminent person with us sharing this session today. So without further ado, over to you, sir.
Thank you for nice introduction about me, and thank you, Professor Satish sir and Arya sir, for giving us this opportunity. So it is great pleasure to me to introduce today's the speaker, the Professor Carlos Kashesvili from Georgian Technical University. Sir is from Faculty of Informatics and Control Systems, Georgian Technical University, Georgia, and he has a number of the papers in the publications, and also is a senior scientific worker of the Waco Institute of Applied Mathematics, Tbilisi State University, and he also contributed the books on testing statistical hypothesis with the reliability and constrained Bayesian methods of estimation testing. And also he's contributed to many of the textbooks related to the Bayesian and computer algorithms and advanced modeling and computer technologies and etc. And so I am inviting and leaving the floor to Professor Carlos Kashishvili. Professor?
Professor Kachashvili, please.
Sir, is there?
Yes, Professor Kachashvili is here in the group. I hope he will. Hello?
Sir is joined or?
Yeah, he's signed in. He's joined. He joined the group, the meet, and I hope he will come forward.
Yes.
And this is a special talk, in fact, in collaboration with, jointly with, in fact, Professor Ashish.
Carlos is here?
Yeah.
Satish, Carlos is here, right?
Yeah, Professor, yeah.
Hi, Carlos, can you hear us? Carlos' mic is muted. Carlos,
sir, please unmute the mic.
Yeah, he has to unmute his mic. Carlos, you need to unmute your mic. We cannot hear you.
Yeah, sir is.
Just a minute, I'm writing to him. Let's see.
Hi, Professor. Please unmute your mic.
I've already sent him an email. The slides are also not visible, Satish.
Probably there may be some network.
There he is. Okay, Carlos, you unmute your mic, please. Unmute your mic. You need to unmute your mic.
Your mic is muted. Please unmute it. Red button, left red button. The bottom, there's a left red button. So as to unmute the mic. In the window, in the bottom side, there is a red button. Please click on that. Can you hear?
Your mic, please, Carlos, your mic is there, the icon. Click on that mic. Click on your mic icon. Please click on the mic icon. You need to click.
I think there is some disturbances there.
Yeah, probably. Let us wait some time.
Yeah.
Let me try to send Carlos a Gmail, okay? I've sent him already the webmail.
Or otherwise, please call once.
Yeah, let us try to contact him through other medias.
Yeah, I'm trying to contact him through Gmail, okay?
Okay, Professor. Okay, Professor. Also, I'm trying to call him via WhatsApp.
Yeah. I have sent him an email, Satish.
Yes, Professor.
I have sent him an email also.
Okay.
See, his mic is still muted.
Probably sometimes there may be some technical issues with the laptop. Or computer.
Let's wait. He's there, so he's trying to. We can see him.
Okay. At that time, what we have to do is left and join, then it will become better.
Right.
Do you see me now?
Yeah, we can hear you.
Good. Now you are on.
Thank you. I changed computer.
Yeah.
And,
Good.
hello, how are you? As I know, now it is my presentation time.
Yeah.
And how
now it is okay. We can
how I can share my file?
You can share your slides, Professor. Go to that upward arrow button, and
there is an up arrow button.
Or otherwise, you please send the files to me.
Now it is, do you see my file?
Yeah.
Do you see my presentation file? Do you see my presentation?
Yeah, Professor. We can see you.
Can I start? Can I start? Okay.
Yeah, we can speak now. Yeah.
Okay. Can I start?
Yeah, Professor. Please begin.
Okay. First of all, thank you very much to organize the committee and personally to Dr. Satish for giving me such opportunity to make presentation on such a valuable webinar. And let me start my presentation, my common presentation with Professor Ashish Sengupta. And title of my presentation is Constrained Bayesian Methods for Union Intersection and Intersection Union Hypothesis Testing Problems. Presentation structure is given on this slide. The consideration of the union intersection problem, where the basic hypothesis H0 states the simultaneous occurrence of several disjoint subset hypotheses. That means it is intersection of a subset of sub-hypotheses. Started in the middle of the last century, the reverse scenario where the basic hypothesis states the occurrence of at least one of the sub-hypotheses. It is when basic hypothesis is union of a subset of hypotheses was considered some time later by Professor Sengupta and was termed the intersection union testing of hypothesis problem. Both statements of the hypothesis testing problem deserve attention as they appear in many practical applications. For example, union intersection situations arise when one considers multi-parameter testing problem in multivariate distributions while intersection union testing problems arise one parameter situations such as equivalence testing problems, acceptance sampling in statistical process control, reliability and multivariate analysis, directional statistics, multi-parameter problems like contaminated or mixture models, multiple comparisons in verbal fluency disorders studies, group sequential clinical trials, and so on. The intersection of the separate critical regions obtained by the standard separate test for each H0I for testing H0 is considered in childhood and negarature. The general uniformly most powerful test is presented in the work of Lehman for solving this problem as approach based on the pivot parameter product as given by Sengupta is exemplified by computations for several practical exams and by comparison of the obtained results with the results given in the work of Berger. The pursue the above problem more general statement of union intersection union problems and application of constrained Bayesian method for solving it are presented below. Let's consider the problem of testing a basic hypothesis against alternative one when one of them is union or intersection of a subset of hypotheses and another is negation of the first one. Since these two cases easily can be transferred to each other by changing the basic and alternative hypothesis and vice versa. We will consider the case when the node hypothesis is union or intersection of a subset of hypotheses and the alternative is negation of the node. That means basic and alternative hypotheses are presented in such a form or in another form. In general, this problem can be stated as follows: to test the basic hypothesis against the alternative one when both of these hypotheses are the union or intersection of some subsets of hypotheses, respectively. Here, basic and alternative intersection of basic and alternative hypotheses is empty space, and the fulfillment of this condition where Rm is a dimensional parametrical space is not obligatory in contrast to the classical case. Hypotheses from one subset can intersect with each other, but hypotheses from different subsets do not intersect. These suppositions make the statistical hypothesis similar to the hypothesis usually encountered in real life and therefore makes them more natural. In general, here we consider the following combinations of testing of hypotheses. Here is offered for different statement of basic and alternative hypotheses. It is obvious that hypothesis which was offered in the beginning are particular case of this one. The standard separate test for each couple H0I and H1J offered in childhood and negarature, which yield a test for basic and alternative hypotheses with the acceptance regions given by the intersection or union of the separate acceptance regions, has the following drawback. The information that may be contained in the hypothesis H0I and or H1J concerning other sub-hypotheses are lost in such separate considerations. Application of CBM for testing these hypotheses is free from such drawback. It does not need the derivations of a new test statistics for every concrete cases and its distributional law, which may be not trivial in many cases. Besides, it is free from the necessity to have exact separate tests. Let us adopt the following notations for the application of CBM to testing of the formulated above hypothesis. Let's HI prime, let's denote by HI prime the hypothesis, sets of hypotheses which are incorporated in basic and alternative hypothesis. Then we have to test S equal to S0 plus S1 hypothesis instead of S0 multiplied by S1 separate test in pairs. Let's henceforth omit the upper index for simplicity. Let a sample be generated from this distribution law, and the problem of interest is to test HI hypothesis via parameters belong to the subspace from the parametrical and dimensional parametrical space, and requirements of being disjoint subset of theta I is not obligatory. Let the prior on theta be denoted by the following expression, where for each I, P of HI is a priori probability of hypothesis HI, and P of theta at HI is a priori density with suppose theta I. P of X at HI denotes the marginal density of X given HI. D is decision rule, component of which are determined by this formula. Gay I is HI hypothesis acceptance region. L1 and L2 are the losses of incorrectly accepted and incorrectly rejected hypotheses respectively. One of the aims of constraint Bayesian method is the following: to determine such hypothesis acceptance regions which minimize the average losses of incorrectly accepted hypotheses subject to the conditional probabilities of incorrectly rejected hypotheses. Statements offered just on the previous slide is one of the possible forms that can be modified to other forms depending on the specific hypothesis testing technique applied. This problem may be viewed as a generalization of the optimization problem of Danzig and Wald, which was considered in the work of Lemon for obtaining the most powerful test. Solution of the stated problem gives hypothesis acceptance regions of the following kind, where Lagrange and non-Lagrange multipliers are determined so that in the appropriate restriction conditions equality takes place, and these regions can be rewritten in a more compact form, which gives expression 5. And let's consider the following loss function, which we call stepwise loss function, and restrictions conditions for such loss functions takes the following form, and decision-making regions are the following. For testing into this hypothesis, decision-making rules are defined on the basis of these regions, and here are decision rules for all stated hypotheses, but for saving time, I will concentrate your attention only on the first case when hypothesis H0 is accepted if observation results belong only to the union of the regions, S0 number regions, and alternative hypothesis is accepted if observation results belong only to the region J S0 plus 1, and do not make this decision in any other cases. No other forms of hypothesis I omit because they are practically similar to the previous case. In all the above situations, this statement do not make decision in any other case was made since it is impossible to make decision at the desired level on the basis of existing information. If making a decision on the basis of existing information is impossible, then there are two actions: to change restriction levels in the appropriate restriction conditions until a decision will not be made, or to continue the sampling, that's to transfer to the sequential experiment until decision is made. For such statements of the problem, the following theorem is proved. Constrained Bayesian method for given statement of the problem for the cases of hypothesis B and the stepwise loss function ensure a decision rule with the error rates of the type 1 and type 2 restrictions by the following inequalities, where R2I are the restriction levels in the appropriate restriction conditions. K0 is the value of loss function. P of HI is a priori probability of hypothesis. Making the same transformations for other combinations of hypotheses which we are offered above, it is easily seen that the theorem holds for all these hypotheses. Now let's consider another type of hypothesis. Instead of stepwise loss function, we consider the following loss functions, which we call, for distinguishing from this loss and from other losses, we will call a complicated loss function. For such loss functions, hypothesis testing problem in CBM has the following form: to minimize such risk function at the following restriction conditions. And solving this problem, we get the following hypothesis acceptance radius, and here unknown parameters, Lagrange multipliers, are determined similarly as the previous case, so that in appropriate restriction conditions equality takes place. For such statement, the following theorem is proved. Constrained Bayesian method for such losses ensure a decision rule with the error rates of the type 1 and type 2 restricted by the following inequalities. Similarly, this theorem can be proved for other combination of hypotheses. Now let's consider examples for illustrating the fact that well-known cases of statistical hypothesis formulations are particular cases of hypothesis given above. In the example one, we consider the case of one parameter basic hypothesis, which is taken from this work. Let's say random variable x follow the distribution f of x theta, where theta is a scalar parameter, and let's consider testing basic hypothesis which proves that parameters value is outside of the interval theta 1, theta 2, versus alternative hypothesis which suppose that parameters value is included in this interval. Let's introduce the following set of sub-hypotheses. Then this hypothesis can be rewritten in the following form, and from here it is seen that both basic and alternative hypotheses contain two subsets with two sub-hypotheses, and total number of sub-hypotheses is equal to 4. Let's consider the case of stepwise loss function. In this case, restrictions take the following form, and decision ranges are the following, and the errors of type 1 and type 2 can be computed by the following ratios. And by theorem 1, for their restrictions on the desired levels at making decision, restriction levels must be chosen on the basis of the following conditions. Let's consider the case of restrictions functions or complicated restriction functions. That means second type of restriction of second type of restrictions. In this case, risk function has the following form. Restriction conditions are the following, and the decision-making areas are the following. And finally, restriction conditions have the following forms. It should be noted that the determination of Lagrange multipliers is more difficult for complicated loss functions than for stepwise loss function, because in the first case, the two-dimensional equations with respect to Lagrange multipliers must be solved instead of one-dimensional in the second case. For guaranteeing restrictions of type 1 and type 2 error rates at the desired levels according to theorem 2, restriction levels must be chosen so that the following inequalities are fulfilled. The comparison of these conditions with the appropriate condition for stepwise loss function allows us to conclude that at identical loss function a priori probabilities and restriction levels, type 1 and type 2 error rates for complicated loss function in general are less than the same error rates for a stepwise loss function at the solution of the state condition of the problem. Therefore, the use of complicated loss function is not only more logical than the use of stepwise loss function, but also it is preferable for minimization of type 1 and type 2 error rates. Let's consider the second example when we consider multi-parameter basic hypothesis, and this example is taken also from the work of Professor Sam Gupta. Let's consider the mixture model with the following density, where parameters P and theta, P is probability and parameter theta belongs to some space interval from the real line. Both of these parameters are unknown, and theta 0 is known point of the theta, and Q is an unknown parameter, possibly vector valued, to be interpreted as a Newton's parameter. The density f of x at theta and q is assumed to be sufficiently regular. We want to test the null hypothesis, which suppose no contamination, against the alternative one, which suppose there is contamination. Under the above setup, the null hypothesis of the contamination translates to the union of three parametric hypotheses. The null parametric sub-hypotheses are the following, and in this case, the following equality, we have the following equality, that means hypotheses H01, H02, H03 are the same. It is obvious that to the alternative hypothesis corresponds the following parametric hypothesis. Finally, we have the following set of hypotheses for testing H0 versus H1. H0 suppose that X is distributed by F distribution law, and H1 suppose distribution law is J. In this case, the number of sub-hypotheses is equal to 1, and after introduction of the following designations, the marginal densities for testing this hypothesis are the following, and here Q is the domain of support of Q small. It is obvious that we have a particular situation of the previous case, this of the example 1, where for testing we use again constraint Bayesian method. Therefore, the results obtained for example 1 and in particular theorem 2 are in force in this case and have the following form. We propose to reinforce the theoretical results given above and for investigation of their behavior depending on different parameters. Let us consider the following example. For testing introduce above hypothesis, let's use a sample with the size n obtained from normal distribution with known variance, because the sub-hypotheses introduced above are complex with appropriated densities, let us use Stein's method for finding the uniform most powerful invariant test. And let's introduce the following designations. Because X bar is a sufficient statistics with normality of distribution, we use it as a test statistics. Then for the marginal density of X bar given HI, we have the following expressions. And the probability density function of truncated normal distribution is the following. Because of difficulties to find sufficient statistics for all densities introduced above, we are forced to use these densities for determination of Lagrange multipliers and decision-making gradients, but at modeling, for making decision, we simulate the statistics X bar, which is normally distributed. As a result, the condition of theorem 1 is violated, and it is expected that its result will not hold. Let's consider the same example when variance is unknown. In this case, we can consider two methods based on the maximum likelihood ratio and Stein's method. In the first case, instead of variance, we use this estimation. And in the second case, for averaging influence of the variance, we use a priori density, that is the chi-square, the density with n-1 degrees of freedom over this interval, where the marginal density of X given HI are the following. Let's consider example 2. In this example, we can consider two methods too, based on the maximum likelihood ratio and Stein's method. The maximum likelihood ratio gives the following marginal densities for basic and alternative hypotheses. In these cases, we have the following hypothesis acceptance regions with the following marginal densities and the following parameters. And application of Stein's method gives the following marginal densities for basic and alternative hypotheses. Let's complete example 1 with the following initial data. That means there are given the values of loss function, variance, mathematical expectations, which correspond to the subset of hypotheses, a priori probabilities, restriction levels. And let's consider the case of stepwise loss function. For the determination of Lagrange multipliers, probability integrals with the suite of restriction conditions were computed by Monte Carlo method using appropriated sampling with size 5000. For computation of type 1 and type 2 error rates for the normally distributed sums of 10,000 were used. This sample size is used below in all Monte Carlo computations for similar probabilities. For the considered data, restriction levels in the restriction conditions are the following: 0.975 and 0.99 under basic and alternative hypotheses. And therefore, type 1 and type 2 error rates for testing of hypotheses must be restricted at the level 0.05 and 0.02 respectively, and Lagrange multiplier are the following. The values of acceptance probabilities depending on mathematical expectation of generated randomly distributed random variables are given in table 1. Hypothesis acceptance probabilities depending on the variance of truncated normal distribution. When expectation of generated normally distributed random variables is the following, this hypothesis HI is true, but sample distribution is close to hypothesis H0 are given in table 2, and the hypothesis acceptance probability depending on the expectations of truncated normal distribution. When expectation of generated normal distributed random variable is the following, this H1 is true, but some distribution is close to the basic hypothesis are given in table 3, and these results are presented in figures 1, 2, and 3 respectively. I omit this one. I only give some conclusions on the basis of these computations, and these conclusions are the following. Because of remark 3, the computed values of type 1 and type 2 errors probabilities exceed the values 0.05 and 0.02 respectively, determined in accordance with theorem 1. Discrepancies as great as the closer is the expectation of sample distribution to the borders of hypothesis domains of definitions. Probabilities of correct decisions at basic hypothesis are higher than at alternative hypothesis for small distance between mathematical expectation of sample distribution at the borders of hypothesis. When distance between mathematical expectations of sample distribution and the borders of hypothesis domains of definitions are increasing, type 1 and type 2 error probabilities are decreasing, and conditions of theorem 1 is satisfied. The number of observations necessary for making decisions at alternative hypothesis is greater than at basic hypothesis. In average, at hypothesis H0, it quickly decreases at increasing distance between mathematical expectation of some distribution and the borders of hypothesis domain of the distributions. At decreasing variance of truncated normal distribution through hypothesis acceptance probabilities increase at hypothesis H1. At increasing the variance of truncated normal distribution, some size necessary for making decision increase at hypothesis alternative hypothesis. At increasing of distance between parameters, mathematical expectations of truncated normal distributions at basic hypothesis, and the border of tested hypothesis domains of definition, probabilities of acceptance of true alternative hypothesis improves, and some size necessary for making decision decrease. Now let's compute for the same initial data when loss function is complicated. We use the same initial values depending on hypothesis, computed results of hypothesis acceptance probabilities depending on the mathematical expectation of generated random variables are given in table 4, and these computation results are presented in figure 4. From here it is seen that number of observations for making decision is quite small. From the obtained result, it is seen that sample size for making decision is quite small. Despite such small sample size, probabilities of acceptance of true hypothesis are quite great, and by choosing restriction levels, they can be adjusted in favor of one of hypothesis H0 or H1. For the elimination of the situation when probability distribution laws of a sample differ from the probability distribution law used for determination of Lagrange multipliers and for making decision, let us consider the following. It is clear that for such subset of hypotheses, more logical is, instead of stepwise loss function, the use of the following loss function, which we will call final loss function, final form of loss functions. And in this case, hypothesis acceptance regions are the following, and taking into account the fact that the risk of incorrect decision in constraint Bayesian method, as well as in other hypothesis testing methods, decrease when information distance between tested hypotheses increase. Instead of composite one, we consider this simple hypothesis, following simple hypothesis 2 by 2, and the parameters, initial parameters, mathematical expectations for these distributions are the following. The hypothesis acceptance regions are the following, and the Lagrange multipliers are computed analytically by these expressions, and the decision-making areas are also computed analytically by these ratios. Computation results are given in table 5 for this initial data, and the graphical representation of these computed results are given in figure 5, which was shown above. It is clear that the increase of restriction levels entails the increase of qualities of decision made for both hypotheses. Finally, for the same aim that was expressed in previous case and for more complete use of existing information, let's consider hypothesis acceptance ranges when stepwise losses are used. Let's again use the fact that probability of errors of testing hypotheses decrease when information distance between hypotheses increase. For determination of Lagrange multipliers, let's consider the following subset of hypotheses similar to the previous case, and in this case, hypothesis acceptance regions are the same, and initial values, the values of initial parameters are again chosen the same. Sums with size 10,000 observation are used in computation at determination of Lagrange multipliers, so at computation of error probabilities. As computation results are given in this table. Despite of ideal results of making decision, all decisions are correct. Let's see, all decisions are correct. Its practical value is limited because for making decisions, a huge number of observations are necessary, which is least likely to be possible when solving many practical problems. But still, the results of making decisions are so impressive that we consider it more appropriate to discuss this case in more details. In cases where a large number of observation results can be obtained, it is for big data. Therefore, computation results of these cases for different restriction levels are presented in table 7. Here, computation results for 3 different cases are divided by slanting lines, and for computation are made for this initial data. And here, as well as in the previous case, computations are realized very fast because normal distribution are used. They are computation results. It is obvious that the obtained results are excellent for all considered restriction levels, but the number of observations necessary for making decision are quite big, especially when restriction levels are high. The necessary number of observations for making decisions increase at increasing restriction levels. The results given in table 6 and 7 conform theorem 1 because the conditions theorem are satisfied. Let's make a short discussion. It is clear that the change of the values of type 1 and type 2 error rates in all the considered cases is possible not only by changing restriction levels in the appropriate restriction conditions, but also by changing a priori probabilities and by choosing the values of loss functions. Probabilities of acceptance of alternative hypothesis when it is true at complicated loss function are greater than at stepwise loss function, and on the contrary, probability of acceptance of basic hypothesis when it is true at complicated loss function are lower than at stepwise loss function. The sum size for making decision at complicated loss function is significantly less than for stepwise loss function. Probabilities of acceptance of basic and alternative hypothesis when these are valid are higher at final loss function than at stepwise loss function. At the same time, necessary sample size at final loss function is significantly less than at stepwise loss function, and computations are realized analytically in the first case. Probabilities of acceptance of alternative hypothesis when it is true at complicated loss function are a little better than at final loss function. On the other hand, probabilities of acceptance of basic hypothesis when it is true at final loss function are significantly better than at complicated loss function. Sample size at final loss function is no much higher than at complicated loss function. And on the basis of above finding, we conclude that final losses are preferable than the stepwise losses and complicated losses as well. Moreover, the computations at final losses are realized analytically and before are very fast. The best results are obtained at stepwise loss function when the densities of the worst simple hypotheses are used instead of average ones over the appropriate parameter subsets. Here is given a very short conclusion, and there are some references which were used at working on this paper. And finally, thank you for your attention.
Thank you, Professor. Now, if there are any clarifications or queries from the participants. So the professor is ready to answer any of the queries. If you are having any of the queries.
Let me just add one thing. This is Ashish Sengupta. So CART loss has been working in this area for quite some time, and it is really a different type of inference procedure that we are looking at. I just wanted to add the comment. He's trying to unify different ideas together. So, along with the big samples, you see here that the potential and the Bayesian aspect put together allows to potentially constrain. This is something very new, and I hope that his endeavors will go a long way. So I've been trying to collaborate with him. It's a new idea with a lot of applications that you saw, and good computational efforts needed also. Thank you.
Thank you. Thank you very much.
Suppose, Professor, if suppose here what you have considered is the normality under that the hypothesis. If the non-normality, if they are not conjugate pairs, so was there any complication?
In this case, as I understand your question, your question is the essence of your question is the following: what happens if instead of normal distribution we will take other distribution? It's right.
Yeah.
Yes. Yeah. We have other works where we consider it other distributions, not normal distribution, but other continuous and discrete distributions too. And this method works very well. But for a normally distribution, computation time is a little short because generation, we use Monte Carlo methods, and generation of normal distribution is faster than other, for example, truncated normal distribution or other distributions which are not realized in software, for example. We developed special software for generation such random variables, and it takes a little long time.
Okay. Thank you. Any queries from the participants? If no questions, then on the behalf of organizers and participants, here we are thankful to Professor Ricardo Kashvili for delivering an excellent and new approach. They talk on in obtaining the testing of the statistical hypothesis using the Bayesian approach in testing the union, intersection, and intersection union hypothesis through the minimizing the alpha, that is the type 1 error, and increasing the power of the test, and also shown with an example by simulation of estimating the parameters. And thank you, Professor. And also I'm thankful to Professor Satish Kumar and Professor Riaz for giving this opportunity for chairing of this session.
Thank you. Thank you to all of you, and especially to Professor Sen Gupta for stating this very interesting problem, and Professor Satish for giving opportunity to make my presentation. Thank you.
Thank you, sir. Thank you. I'm handing over to
thank you.
Satish.
Thank you, Professor, sharing the session in a very nice way. And thank you for the and for nice presentation, very informative. Also to Professor Gupta for your support and for both of you have the credits on the concepts and the development. Thanks a lot, Professor.
Thank you, thank you, thank you.
Thank you, sir. Thank you very much.
Thank you.
On behalf of the community, once again, thank you. Let us move to the next session. The next session is again a session organized by Professor Dr. Eldo Varghese. And I think Sangamitra is here in the group to introduce the chair, and the session organizer, and thereafter support the session chair to do the needful for the session.
Welcome to the Technical Session 27, which is a special session in honor of Professor K.R. Nair. The session is organized by Dr. Eldo Varghese, Senior Scientist from Central Marine Fisheries Research Institute. His focus of research includes statistical designs for product and process optimization, fish stock assessment, statistical modeling in fisheries, and statistical techniques for remote sensing applications in fisheries. He has been awarded the IARI Gold Medal for Outstanding Academic Performance and Meritorious PhD Thesis, New Delhi. This session is chaired by Dr. Sini Varghese, Principal Scientist and Head in the Division of Design of Experiments at the Indian Agricultural Statistics Research Institute, New Delhi. She has handled 20 research projects. She is a professor in the discipline of agricultural statistics and has been involved in teaching agricultural statistics for the past 25 years. Her research areas of interest are construction and analysis of designs for experimental situations in agriculture. She has published around 170 research papers in international and national journals. She has received the Lal Bahadur Shastri Young Scientist Award of ICAR for her outstanding contributions in the field of social sciences. It is with immense joy that I welcome you on behalf of the whole organizing committee and kindly request you to take over the session. Over to you, ma'am.
Thank you. Dr. Eldo, you will start.
Yes, madam. Thank you. Thank you, Dr. Sangamitra, for introducing us to the participants. Good afternoon to you all. At the outset, I would like to welcome you all to the session, especially the chair, Dr. Sini Varghese, and we are having, initially we expected to have 7 speakers, but we are having 5 speakers now. Dr. Sauman, he has joined.
then Dr. Shantini, then Dr. Vinay Kumar, Dr. Harun, and Dr. Sini Varghese herself. So we are having 5 speakers. So I would like to thank each of the speakers and the chair for agreeing to be a part of this session. And first and foremost, I would like to thank our respected organizers of this program led by Professor C. Satish Kumar for giving us an opportunity to have such a session during this conference. So prior to start this session, because I thought it is my duty to introduce the chairman, but it's already done. So that actually reduced my burden. So, but still, I have a couple of slides because I was very happy to, when you asked to organize such a session, and I was more happy when I learned that it is being organized to honor the late Professor K.R. Nair. Because when I was, thinking about who can be a chair of this session, because I was in my mind that someone who has done something extensively in the area of partially balancing complete block design should chair this session, because when we recall our late Professor K.R. Nair, we all remembered him majorly because of his contribution he has done towards introducing partially balancing complete block design. Even though he has done a lot of work in various spectrum of statistics, but mostly we all recall that paper which published in Sankhya in 1939. So I have a couple of slides about him. I have got it from your website and some other Wikipedia. So I will take a maximum of 10 minutes to share a few facts about him. So shall I share my slides?
Sure.
I hope my slides are visible.
Yes.
Yes, it is fine.
So thank you once again, organizers, for giving us an opportunity to organize a session on design of experiment, that to honor our late Professor K.R. Nair. So Professor Keshavan Raghavan Nair, who was born on May 10, 1910 in Kerala. After completing his graduation, he got a chance to pursue his postgraduate program in University of Madras with help of a research scholarship, and he obtained his Masters of Arts in 1932 and Master of Science in Statistics in 1939 from University of Madras. So his real success came about when he could read papers in journals like Biometrica and JRSS and formulate problems for his own research. After the end of his scholarship at Madras, he decided to go to Calcutta and join statistical laboratory of Professor Mahalanobis. And when Calcutta started a postgraduate degree in statistics in 1941, Professor Nair was appointed as a part-time lecturer there, along with great stalwarts like Professor R.C. Bose and Professor S.N. Roy as full-time lecturers there. And an interesting fact is that Professor C.R. Rao, the living legend, was one of the students in the first batch of this program. Professor Nair had a very fruitful collaboration with Professor Rao and Professor Bose during ISA days, and it is very evident from the research publication. One paper which published in Sankhya in 1939, which is on partially balancing complete block design, and another paper that was with Bose, Professor Bose, and another paper was with Professor Rao on confounding in asymmetrical factorial, that published in JRSS. So this is the paper which was mentioned. That's a breakthrough paper in which he introduced a concept, even though there were, some work about balancing complete block design in sense of lattice, which was introduced by Frank Yates in 1936 around. Then there literature we can find that most of the work on design which revolving around the balancing complete block design, specifically those which are balanced lattices. Later, when this concept introduced by Bose and Nair in 1939, we can find n number of papers which are exclusively dealing with partially balancing complete block designs. Then, since his position at ISA was financially inadequate to support his family, he later moved to Department of Food, Government of India, as per the advice from Professor Mahalanobis as Assistant Director of Statistics. He was still interested in research, and after the end of World War II in 1945, he was able to get a scholarship to study at University College London for his PhD. Subsequently, he received his doctoral degree in 1947 and Doctor of Science in Statistics in 1954. He was an elected fellow of Royal Statistical Society prior to his admission, prior to his PhD degree. As soon as he received his PhD, he was asked to return to India and appear for an interview for the position of a statistician in Forest Research Institute, Dehradun. So at FRI Dehradun, he began applying modern statistical method to forestry research. During that period, the great Professor J.N.K. Rao is known for the contribution to small area estimation, and Professor K.R. Shah, he's very eminent statistician, worked in almost all areas, but his contribution is well known in the area of optimal design theory. They came from University of Bombay to work under him after their MSc in statistics. So Professor Mahalanobis, however, wanted Professor Nair to play a big role at CSO rather than Central Statistical Organization, rather than working at then a smaller place like FRI. Accordingly, in 1959, Professor Nair left FRI and joined CSO as Joint Director. He continued his research at CSO, but there was much less time available for it due to inherent responsibility. That is evident from there is a decline in number of publications by Professor Nair after that period. So after he retired as Director of CSO in 1968, he worked at United Nations Economic Commission for Asia and Far East, now it is known as ESCAP, Bangkok, and Asian Statistical Institute until 1975. So he later moved to Bangalore, and he left for Heavenly Adobe in 1993. And coming to the Society of Indian Society of Agricultural Statistics and the linkage of Professor K.R. Nair with Indian Society of Agricultural Statistics, that's a very old, one of the old society, and where he was a regular active member of that society. And this is one paper he has presented during a joint symposium organized by International Biometric Society Indian region with the Indian Society of Agricultural Statistics, which was held in Dehradun. Held in New Delhi. So this paper, he explained several avenues or several unsolved problems in design of experiments. Now coming to his membership, he had occupied several positions in several professional societies and bodies, which include the Indian Society of Agricultural Statistics as a member, then Indian Standard Institution, then as a president in Indian Science Congress Association for a session on statistics, then as a member of the statistical committee constituted by Indian Council of Agriculture Research, then elected member in International Statistical Institute, then chairman subcommittee on methods of research in tropical forestry during the Fourth World Forestry Congress, Dehradun, 1954. Then he was a co-director, FAO International Seminar for Forest Research Workers. Then he is an elected fellow of Royal Statistical Society, London. Then fellow of American Statistical Association. Then president, Calcutta Statistical Association. Then National Institute of Science, India. Then Indian Statistical Institute as a joint honorary secretary. Then these are some of the selected publications by Professor K.R. Nair on the area of DE, design of experiments. The first one is the one which I was mentioning, and the one published in Sankhya on partially balancing complete block design. Then the second one in JRSS, confounding in asymmetrical factorial experiments, it's jointly with the Professor C.R. Rao. Then there are several related papers you can find mostly in CSAB and other journals. So to honor him, this session is being organized. So we are having five speakers, including the chair, and I am really thankful to all the speakers for agreeing to be a part of this session. And I think now I will give a brief about our session chair, even though Dr. Sangamitra has introduced the chair to all the audience, but it's my privilege and duty that Dr. Siniva, to introduce Siniva to all of you. She's having 25 years of teaching experience, and she has worked mostly in the area of construction analysis of statistical designs for various agricultural experimental situations. And she has guided several students in PhD as well as in MSc, and published around 170 research papers in theoretical statistics, which include journals like Metrica, Biometrics, then JSPI, then Metron. So many. I mean, if you start counting the number, I mean, the almost all sort of journals, which are mostly the papers on design of experiments being published, and immensely she has contributed and worked in the area of PBI-BD. And she has completed a project exclusively in the area of partially balanced complete block design. So I feel very privileged and honored that she agreed to be a part of this and agreed to chair the session. So I welcome her to this particular session. And also I'm really thankful to all the speakers, including Dr. Sauman Manna, Dr. Sayantini Karmakar, Dr. Mohammad Harun, and Dr. Vinay Kumar, and our chair herself. So thank you once again for giving us this opportunity. Thank all the organizing team for giving us a chance to organize a session. So with this brief, I would like to hand over the session to our respected Dr. Senior Verghese and inviting her to continue with the session. Thank you. Thank you all, and over to you.
Thank you, Dr. Eldo. Thank you so much. There is a saying, aim high, reach up to the stars. If you cannot reach up to the stars, you can get at least some stardust in your raised hands. We all try to grab that stardust. Eldo himself is a star, and I'm very proud to say that. Okay, he was our student at one point of time, and a teacher is most proud when the student reaches these heights. Okay, thank you, Dr. Eldo. And thank you, the organizers, and Dr. Satish, especially for giving us this opportunity. So keeping a session on design of experiments is very thoughtful, very insightful. And when we talk about Professor Nair, yeah, Dr. Eldo very well pointed out. We followed him like anything. And my first course seminar as a student was on partially balanced incomplete block designs, which led to that project which Eldo was mentioning. So we still work on PBIB designs and resolvable designs and whatnot. So after almost 90 years also, Professor Nair is a guiding force for us. So whenever we think about partially balanced incomplete block design, of course, Bose and Nair paper comes to our mind. So that is our guiding paper. That is the breakthrough. We are all very proud to have be a part of this particular session in his honor. Thank you, we are once again thanking the organizers. So as Dr. Eldo mentioned, we have 5 speakers with us: Dr. Sauman, Dr. Sayantini, Dr. Harun, Dr. Vinay, and I'll be adding something. Not my paper exactly, but a topic which we can think of working. Again, I think the maximum audience is students, so it will be helpful for them. So I have picked up such a topic where they can also work on later on. So first speaker is Dr. Sauman. Before starting, I think we can have 30 minutes roughly, Dr. Eldo. 25 minutes for presentation and 5 minutes for discussion. I would like to have a detailed discussion if students are active in this online program. If they are active, we will have at least 3 or 4 questions per talk. So that will help everybody. So I invite Dr. Sauman. Before that, I will give a very brief introduction about him. Dr. Sauman is currently working as Assistant Professor of Big Data Analytics at Goa Institute of Management. He earned his master's and PhD degrees from IIT Mumbai in Applied Statistics and Informatics. He has almost 12 plus years of service. He worked in different prestigious organizations like IIT Mumbai, Mumbai University, Ramayya University, VJTI Mumbai, etc. And he also has experience of MNCs. including Bisleri. So his areas of interest lie in statistics, optimization, choice experiments, machine learning, data science, and computer programming. We are very fortunate to have you here, Dr. Manna, and looking forward to listen to choice experiments. So that is a burning topic now. We are just eagerly waiting for your talk. Thank you, Dr. Manna. You can start now. You can please share your screen and start.
Thank you, ma'am. Let me first share my screen. Am I audible?
Yes, you are audible.
Yeah.
Very clear.
Choose what to share from Intel's.
Just
if the PPT is fully open already, then you can share the entire screen. That will help.
I think so. Let me check. Is my PPT visible?
It's fine.
Yes, yes.
It's visible, right? Okay, good.
Please make
okay,
it as full screen.
I have to make it full screen. Control F will work. Let's check. No. Okay, it's.
Yeah, it's fine. We are able to see it. No issue.
No, it won't work. Okay. So, once again, good afternoon to everyone. So today I will be talking about design and analysis of choice experiment. As ma'am said, it is relatively new topics in the area of design of experiment. Mostly maybe I can thought of 20 years, and most of the works are done right last 10 years, advanced results. So what I'll be doing, since we have only 25 minutes, so for the students, I'll just give an idea what is choice experiment, what is the applicability, how to build the model, and how to do the analysis. And at the end, I will just share some easy step how to build, how to make designs or optimal designs for main effects model, or maybe main effects and some factorial interaction effects model. So my agenda would be right. As I said, the basic choice model I'll discuss. I'll discuss a little bit about choice design, then how to find efficient choice designs. Okay. So to start with model, we need some basic. We need to know some basic idea how these models being used and what is the need and how it is developed. So imagine how you choose a product when you are in some some mall or somewhere in some shop, and you went for the shop or the mall for maybe for a soap or maybe for a mobile or something else. You will always find that there are not only one product, but there are more than one products display in the rack or the right or the place holder. So what happened? You just, in most of the cases, we always check, okay, what are the available products are there in the rack, and out of these products we try to take one. We first go through all its right list of whatever it is given in that list, that all its attributes, and somehow we make some decision including its price, that this product is best for us. So and we take it. So this way, right, we choose a product when we go for a marketing. Now what happened? This is the way people choose their product. But as a researcher, suppose you are researching from the outside, and you are finding that what is happening. People, there is a place and there are multiple products, and what happen, a person goes, he check all the products, and out of that this person take once, then the next person goes and again he check all the products, and out of those products he takes once. So this way the choice happens. It's applicable all around of our, right, different phases of our life. Whatever we, right, we need, actually we make a choice out of many options. So the researcher thought, okay, basically the marketing researchers, the ultimate goal of marketing research is how to, right, sell a product, and what characteristics should be there in my product so that people like it. That is the goal of, right, every companies who made the product. And as a researcher goal is that to understand what people like. Now, earlier, what happened? People used to write, suppose it's a product of mobile, and people used to write, okay, for mobile, these are my features. For each features, these are my labels, and let us check all combination of labels and ask people, right, okay, with this combination of labels, there is a product called mobile, and how much you rate it, maybe out of 10 scale. So this way they, right, basically, right, take all the ratings, and they try to build a basic linear models, and probably people know those models, now called as some types of, what it called, conjoint model. Now, other people thought that what happened, okay, that is fine, but when you are giving rating, there is a problem, because one person is not getting rating. It, the person is different. Different person gives different rating for the same product. So what happened? Maybe for me, when I goes there, I choose a product, right? Suppose out of 5 product, I choose a particular product, and I give this product, I really like that product, and I give this product a rating of 9 out of 10. But what happened? Other person also goes and he lost his mobile. He desperately need a mobile. What happened? He goes there and he find, okay, these many products are there, but actually what he needs, that is not there. But what happened? Out of these 5, he has to take a product. So what is taking? He is also taking the same product that the other person has taken. But when you ask them how much value you are giving in this product, this person will maybe giving a value of maybe 3 out of this, because 3 is highest for him, but the same product maybe 9 is highest for other people. Now you see the variation. Now in the real choice, what is happening? When you are asking the person how much value you are giving, so this value will differ a lot for the same product. And when you are going to build a model, that won't be a that much good model. But if you see in different sense from the producer point of view, both the cases the product is selling, the same product is selling. Now the researcher thought, the, right, what is important, selling of the product. To understand the market share, the selling of the product is important, and there are issues with general, with the linear models, and asking the ratings out of something. So then they come up with some model that is called the choice model. Here they are asking, okay, I won't ask how much value you are giving, because the value the person is giving is different for different persons. What will be checking? What is common between these people? So they are choosing a product. Why not we take, that is our output variable, that out of these many, right, product available, one person, right, what, how many people are choosing that particular product. So for each particular product, when they are together, how many times each of the product are chosen, those information let us collect and try to build a model. So basically, if you see, this idea is nothing but the multinomial choice or multinomial logistic model. So they are trying to build the multinomial logistic model out of this data, and it found that this data, right, this models really works well. Okay, so let us now first let us understand some notations. I just gave you some background. Notation is that suppose in the there is a choice set and we have to choose a product. So we denote that choice set by S, and this T1, T2, Tm means nothing but there are M product available where from where we can choose. And VI we denote that how much value the decision maker giving for that product. And we consider here that each product is a combination of various features, or each feature is a level, right? Each feature has many levels. That is the idea. And our idea would be for each feature, which combination would be better. And we also wanted to know that for each feature, when people are choosing, what is the effect of each feature for the choosing. So what we can write it as a decision maker points of view, we are writing that this decision maker giving a value VI to a product that is nothing but, right, beta dash xi, beta dash is the parameter, and xi are nothing but the feature levels, right? But if you see from the researcher, he is not, right, finding, or he is not asking the person how much value he has given. What he is checking, which product he is choosing. So if you see in the point of view of the researchers, he is from outside just noticing what this person is doing. So for him, the VI is unknown for that data. So what is saying that estimative value of the product for the person I is VI, whatever value he is giving, plus some epsilon, that is the error term. So when he is doing that, this way, this model is called a random utility model, and he wanted to build some types of model to understand what is the value of VI. So this way, now what is saying that okay, there are, right, in the choice set there are M product, and in the M product you are choosing one. So you are writing a product I because its utility is more than the others. So he is writing a, right, model, a probability equation, and is trying to calculate the probability, and after some derivation and assuming some probability distribution of this epsilon I, what we get the probability of Ti among the set S is nothing but exponential of beta dash xi divided by summation j equal to 1 to m exponential beta. This is nothing but your typical multinomial model. So let us understand this thing with the help of an example. So this example is nothing but example of a mobile, and in this mobile what is happening. So maybe the researcher wanted to know or wanted to understand, right, which feature is most responsible, right, for the right, for the market share, prediction of market share, or for the choosing capability of the mobiles, or which of the factors are the deciding factors for the preference of the customers. So what is taken, right, weight, color, screen, RAM, camera, battery, and then memory, processor. These 8 different feature he has taken, and is taken 2 levels. One level is 0, other one is 1. So what he wanted to know, right, he wanted to build some hypothetical some hypothetical mobiles to understand what would be the choice capacity. Now if you see in this case, right, how many hypothetical products are possible, because there are 8 features, so 2 to the power 8, So total 256 hypothetical products are possible. Now the problem is how you approach to the person, right? For asking question what the person looks like, because he wanted to estimate these features. So since that many hypothetical products are possible, one cannot choose a product from this big set of products, right? And it is not the normal market scenario. So in normal market, you will get at most maybe 10 different items for some particular things. So what is the idea? The idea is saying that okay, it's not possible somebody to right choose among these many things. So the idea is make small subset of the product and ask respondents which one they prefer from each. Now again the question is which product should be put together in a choice set for the investigation of the factorial effects of interest. So this is another problem, is that how to make the subset so that right we can estimate all the factors in the very less number of choice sets. That is the idea, and this thing is called nothing but the choice design. So design is nothing but you have lots of different products, and how to select very minimal products, and how to make this basket or the bucket of mobiles maybe 2 or 3 or 4 together, and maybe only 10 or 20 bucket, or maybe only 8 bucket, and ask people, okay, out of 8 I am giving you 1 bucket at a time. Maybe in that bucket 3 or 4 mobiles will be there, and I will ask which one you choose one, and this person will choose that one. So this bucket, this mobile is chosen, so I have right taken this information, and this is the data for me for my further analysis. Okay, so in this case, to understand, let us see, suppose even right to understand how it works, we are not taking 2 to the power 8 case. So we are taking a 2 square case, where suppose you have only two, right, two factors. One is called brand, other is price. So in the 2 square factorial, suppose brand is HP and Dell, and price is, I just written right 25,000 and 30,000. So how many hypothetical products are possible? There are 4 hypothetical products are possible like that. And what we'll be doing in this case, how many choice sets are possible? If you see in this case, total, right, 6 choice sets are possible. But what we are doing for, right, with somehow, maybe we are not taking all 6, maybe with some design, we find that, okay, these many sets of size 2 will be taken. Size 2 means here you are finding a design of size 2 is like that. Maybe I said that one bucket is right T1 and T3, right? So T1 is nothing but a product, T3 is a different product, like that. So here what we are doing, we are taking only 4 different bucket, and each bucket is a choice set of size 2. And right, in the coded form the design is looks like that. So if I say that level 0 and level 1, T1 nothing but 0 0, and T3 is nothing but 1 0. From here what we are taking that, okay, this is the coded level for the product, and this is the design. So design in choice sets, or right, looks like this way. So it's not a right a single array design. It's maybe multi-array design like that, and each, right, it's nothing. You can write it's in a matrix form. We write it like that, and you here 0 0 means one product, and 1 0 is one right another product, and the first row is nothing but a choice set, and we are showing this person this all these 4 choice set, and for each of the choice set means each of the row one will be chosen. So that is the idea of choice design. Now I'll spend some time how you estimate the values, right, of the factorial effects out of this. So in this case, what will be going? So basically, we take this combination. So first combination is laptop 1 and the second combination is laptop 2. And we ask people, okay, suppose you have to choose these two options, which one you will prefer? So you will take any one of them. So this way, for our this design, we'll ask each person to give their 4 choices, right, like that, and we'll collect this data. Now suppose after collecting, how the data set looks like, your data set will be looking like this way. So maybe we asked 10% to collect, right, that information, and for each of these 10% we are giving this all 4 choice set, and this is the right information that the respondents gave you, that from this set I choose this one, from this set I choose this T4, from this set, like that. So that information we have, and this is the data set for us. Now it's time for us to understand the effect of each factor. So what we can do, it's very simple. So we just write this is the probability values, and we say that when you are giving 2 product at a time, person is choosing I product, then the J, that means, right, what is that probability? So from that equation we find that this probability can be written like that. So what we are doing, from each, right, each of these person, we are collecting these things for each of the choice sets, and we are just writing a likelihood function. And right, for this case, what we are doing, we are just writing the likelihood function of the whole set, and it's just MLE to find out each of these parameter. This pi1, pi2, pi3 are nothing but coded one, that is exponential vi, we are writing as pi I. It's nothing but rewriting the parameters. So after solving iteratively, what we will be getting, you will be getting some values of pi1, pi2, pi3 and pi4, and from there by transforming you will be getting the values of v1, v2, v3 and v4. Now remember, these values v1, v2, v3, v4 are the right product level v1, v2, v3, v4. And those who know factorial design, we can easily, when we can understand the treatment level estimates, we can easily find the effect of each of the factors. So from there we can easily find out what is the effect of each of the factors, and when we have these things, we can easily understand that which factor is much more effective while people choose certain products. Of course, here we are assuming that right, these products are in the maybe same place or the same city, or maybe right, the people who are assuming this one, we are giving this output, in the survey, they are almost similar age or similar background, like that. So depending on all those things, ultimately what we are finding the effect of these things. Now, as I told, right, this way we can estimate the each of the product. But for us, since we are the person of right design, our aim is to make this experiment much more robust and fruitful. Okay, how much time I have? Maybe I have 5 or 10 minutes.
3 minutes more to be,
okay,
or 25 minutes.
Okay. So, okay, let me quickly. So I just give you an idea how this experiment can be done and how one can estimate the factorial effects. So I just show you, right, from a design perspective, how to find a best design for it. Because you understand that there are too many choice sets are possible if you take all these type of combinations, and I'm just leaving this. So what I'll be showing some result for optimal design, how to build an optimal design for this type of problems using some very simple way. So one way is, so this is one theorem, And in this theorem, the ultimate idea is like that. Suppose you are dealing with 8 factors. So how can you build a best design or right optimal main effect design for that? Suppose you are dealing with 8 factors. For 8 factors, what you have to take? You first take a Hadamard matrix of size 8. So Hadamard matrix of size 8 is a 8 cross 8 matrix. And this matrix, what you do, first change all the -1 to +1, because Hadamard matrix is a function, right? All the entries are +1 and -1. So what I am doing, all -1 I am changing to 0. Then now you have to ask, okay, if there are, right, choice, you are estimating maybe right 8 factors, what we are doing that, okay, 1 2 3, sorry, here what we are doing, we are estimating 7 factors. So even for 7 factors you have to take a Hadamard matrix of order 8, that it says that how much, what is the range of. So you give me a factor, and factor, how many factors you want to estimate, and try to find out what is the next Hadamard matrix exist. So from there you just take that Hadamard matrix, and what you do, you remove one of this row. So here I have taken 7 factor to investigate, remove one row. Suppose in your case you want to investigate 6 factors, remove 2 rows from that Hadamard matrix. Then transform that Hadamard matrix of -1 to +1. Now we have to ask, okay, when I am asking this question for each of the respondent, how many, right, choice in the choice said, how many product I want to show him. Is it 2 products at a time or 3 products at a time? So it is this decision you have to take. Maybe you say that 2 product is fine, somebody can think of right 4 products is fine. So this generation of the optimal design, whatever product you decide, but I will give you an optimal design. So here if you want 2 product in one choice set, what you have to do, you just take this Hadamard matrix and takes just its opposite Hadamard matrix, means the right all 1 you just change to 0, and all the 0 you change to 1, just complement of this Hadamard matrix. So these two together give you 8 choice sets design, and each choice set is combination of this. And if you are taking 3, what you have to do, you choose any one of them, right, out of these from 1 to 6, you just change, right, all of these factors. So what we are doing here, there is called something called generator. So in this generator I am taking 3. So what we are doing in this next step, I am doing for this first 3 column, I am adding this 1 under modular 2, or in different sense what we are doing, we are changing only these 3 columns, and others columns remains unchanged. So this 3 will tell you a choice design of size 3. Now if you want 4, what we are doing, we are taking the opposite of this, right, this third matrix, we are taking the opposite of this. So here I have taken G1 3, you can take 2, you can take 4, whatever you want, right? So this way you can propagate how many, right, how many different options, or what would be the choice set size you want to give to the respondent. So generally we always give something 3 4 up to 5. So if you give something more than 5, there are some problem of cognitive burden, and your estimates won't be correct. So right, this is the basic way of building a right optimal design. So since we don't have much time, I am I stop here. So right, so if anybody interested, I can share the other slides, so you can go through it, and you can explore the right design techniques. Okay, thank you.
Thank you, Dr. Soman. It was so interesting. We can go on hearing you, but we have to give time to all. So let us wind it up here. And we can have some quick questions, maybe 2 or 3 quick questions from the students or the researchers, please. Otherwise, I have one. You can unshare your this thing.
Okay.
Yeah. Students, please come forward. It's a very interesting topic, and last 4 or 5 years, this is a very burning topic, we can say, in the area of research. Nobody is having question? Dr.
Maybe
Aldo?
it is new to them. They are digesting.
Yeah, if you have one.
Dr. Salman? Yeah, you ask, please.
Actually, because we had several discussion on this topic several times. So, but still, I just want to have a clarification on regarding because we couldn't give him much time because otherwise, because when there are 2 levels, things are comparatively very easy to deal with.
Right.
But the moment levels increases, there may be higher order interactions also coming into the model that also create the model complex and estimation tedious. So in that case, any sort of fractional factorial kind of concept can be introduced, or any work is there with that?
Yes. So what I will suggest, it's a huge opportunities for the researcher and students. So till now, if you see this literature, what we can say that for 2-level designs, only main effects and some 2-factor interaction effects, people find optimal design for that. And for 3 levels only, we have design with main effects model, and that is with Professor Ashish Das and another colleague of mine. But beyond that, there are some design, but there are no design for general cases. Only people give some maybe 4x3 design and like that, and all these designs are only for some combinations, but no general things are available till now. And I just submitted one paper till now, that is even for 2-level design, main effects and some specified 2-factor interaction effects. Because you see, the complexity is the combinatorial here. Even it is 2, as I said, you have that many 2 to the power n different combinations, and out of that combinations, you are saying that I want a design for 8 choice set, and even in 8 choice set, you have the flexibility whether for 2 or 3 or 4. So many combinatorial things you have to parameters you have to decide. So because of that, it's a really difficult job, combinatorial, finding a good design. But yes, of course, people are working on that. Even I discussed with you in that time that partial design people are thinking. So another problem happens that it's this design not applicable to field. So maybe 10 factor, 20 factor is good, but you are applying this thing to the human mind, and human mind cannot process more factor together. So you have to again take care of, you cannot, maybe you want to investigate 20 factor, but you cannot ask the combination of 20 a person. You only check whatever, maybe 3 or 4 factors together. So there is another way that is called partial profile choice modeling. So this different way that at a time you won't show all, but eventually you will show all the things, but in different choices.
Yeah, thank you, Dr. Samaria. It is of course, we had during our last discussion that problem came to our mind, that partial choice sets, the concept of partial choice set. Yeah, of course, when there are more factors, the problem will become, again, it is not for not only with respect to construction, but with respect to getting information. The consumers may get confused if you allow them to keep giving them more choices. So how can we reduce that? So that will lead to that concept partial
Right.
choice. So thank you,
So
Dr.
I
Saman, once again for
also,
joining in.
yeah, I also just 1 minute, since people are talking about block design and other things, and yes, block design is very much applicable here to build the designs.
Yeah, we have paper in Statistica Sinica in the very area for
Right.
something like optimal paired choice block designs.
Right.
So
Right.
in 2019. So
Yes,
people are coming up with block designs as well.
Yes. Yes.
So
I think, yeah, you
one
have
of our
seen the
students
Professor Asito's
presented
paper,
this
right?
in a seminar. Okay. Thank you, Dr. Soman. Since we have to move on.
Yes.
So next speaker is Dr. Sayandini Karmakar. Probably Dr. Eldo has invited all young minds here to give more and more recent research problems.
That is a requirement. That is a requirement.
Yeah, Dr. Sayandini has recently completed her PhD from ICR-IARI. So she usually worked on M-part designs in row column designs with incomplete rows and columns, some T designs, etc. She has some good number of R packages published in CRAN as well, to her credit, compared to the experience she has. She's a recent pass out of PhD, fresh pass out in PhD. So she has 10 research papers in very good journals, and she's also having other conference experiences and other experiences. Now she is looking forward to work further in the area of design of experiments. So she will be speaking here on two-part designs. And Sayandini, next 25 minutes are all yours. You can share your slides and start.
Is my screen visible?
Yeah.
Good afternoon. I am Shantani Karmakar, and I am going to speak on two-part designs using incomplete block design. So this is a brief overview of my presentation. We know that heterogeneity in the experimental material is the major source of variability, apart from the variability arising from the application of treatment. Now, dividing the experimental material into homogeneous groups called blocks can account for this variability. And such designs, we term them as one-way elimination of heterogeneity or block design. As we all know, the most trivial of the block design is the randomized complete block design. But when large number of treatments are to be compared in agricultural field trials, these RCB designs become unsatisfactory. As in RCB designs, the experimenter has to accommodate all the treatments in every single block. Thus, the blocks becomes bigger in size, thus diminishing the chances of maintaining homogeneity within blocks. This contradicts the primary purpose of blocking and necessitates the use of incomplete block design. Now, incomplete block designs popularly play a vital role in bringing out useful information from agricultural experimentation with high precision, utilizing fewer resources. And generalizing these incomplete block designs give rise to an important family of statistical designs called T design. And fusion of one or more incomplete block design will result in obtaining some series of more composite designs to deal with more complex problems. When the number of treatments is large, requiring large number of experimental units, this may give rise to two sources of variability in the experimental material. This is where the requirement of row column design comes. Further, when the number of levels of row blocking factor and the column blocking factor are less than the number of treatments, then incomplete row column designs are useful. Already existing incomplete row column designs were obtained using balanced incomplete block designs or Latin squares or Uden square designs. Incomplete block designs like partially balanced incomplete block designs as well as T designs can be advantageously used to obtain this new series of incomplete row column designs. Further, in case of block designs or row column designs, certain experimental units may not be available for the application of treatments. Such designs are called as structurally incomplete block designs or structurally incomplete row column designs. And fusion of two incomplete block designs in a systematic manner can also yield these two parts structurally incomplete designs. Now, I am going to define the incomplete block designs for B treatments, which can be defined as an arrangement of B blocks where at least one block is of size K and each of the treatments occur in R blocks. The layout of two designs has been shown here for the same number of treatments. The left one is for a complete block design where every block contains a complete set of treatments, and the right one is for an incomplete block design where the block size is less than the number of treatments. Further, generalizing these incomplete block design give rise to an important family, as I mentioned, called the T design. T design is defined as an incomplete block design having B treatments allocated to B blocks, each of size K, where the condition of 1 less than K less than B should be satisfied so that each of the treatment occurs in R blocks and any T tuple of B treatments occurs together in exactly delta blocks. Now, when T is equal to 2, we call them as the balanced incomplete block designs. And when 3 design with T is equal to 3 is also called a doubly balanced incomplete block design. These incomplete block design can control variability in the experimental material if the variability is only in one direction. But many a times, nature of the experiment is such that they are needed to be planned by considering multiple sources of variability present in the material. Even if the number of treatments is reasonably low, row column designs are especially helpful for such experiments. Now, a row column design is a rectangular array whose entries are members of some set of treatments with no repetitions in any row or column. Now, this is a simple situation of a complete row column design where the heterogeneity is present in two cross-classified sources, where the experimental unit is a single leaf, the number of lesions produced per leaf are the observation, and a plant and the position of the leaf on the plant are the two sources of variability. But there may be situations where the experimenter can't afford to have so many rows and columns as that of the treatments. So suppose we consider an animal experiment where there are 10 feeds to be compared and 6 age groups and 5 observers are only available for the purpose. For this situation, a complete row column design will require 10 age groups, which is not logically feasible, as we can see, and 10 observers, which is also not practically feasible. So, an incomplete row column design for 10 treatments in 6 rows and 5 columns would be the most appropriate for this type of trials. These are some incomplete row column designs where the treatment number is greater than the maximum number of rows and columns. Here the condition on this number of treatments greater than is equal to maximum of the number of rows and columns separates these designs from the Latin squares and Uden square designs. So keeping in view the condition on that number of treatments that should be greater than maximum of the number of rows and columns, some incomplete row column designs like double arrays, triple arrays, and sesqui arrays has been proposed by different authors. Double array is an R by C array on V symbols arranged so that no symbol occurs more than once in any row or column that satisfies the following 3 conditions. Each symbol occurs k times, that is, it should be equireplicate. Any 2 distinct rows have the same number of common elements, and any 2 distinct columns have the same number of common elements. So these are 2 examples of a double array. And further, adding another condition that any row and any column have a constant number of treatments in common will give a triple array. So these 2 arrays are triple arrays with parameters like V is equal to 10, K is equal to 3, lambda RR is 3, and lambda CC is 3, and lambda RC is 3. So how we are getting. So now if we consider the array in the left, the blue one, so and consider two rows, then we see that there are like I am considering row 2 and row 3. So there are three treatments are common. So lambda RR will be 3. Similarly, if we consider two columns like column 2 and column 3, then we see that there are two treatments formed. And so lambda CC will be 3. And when we take one row and one column, say R1 and C1, and then we see that the three treatments, that is 1, 2 and 4, is common. These arrays are these triple arrays are also double arrays with the following parameters. So basically double array is a generalized triple array, but every double array may not be a triple array, but every double array may not be a triple array. And this is the example of a double array. This example is given by Max Orley 2005. And sesquiarrays was given by Bailey 2018, which satisfies the same conditions as that of the triple arrays, except that the condition of lambda CC is generalized here. Here, if we see this example, in this example, if we take the first and column and the second column, then we see that there are 0 points are common. And in first and fourth,
sorry to intervene. You please hide that sharing bar. Click that hide button on the sharing bar.
Is it okay, sir?
Thank you. Thank you. Okay.
So as I was telling, if we consider the first and the fourth column, there are 3 points common. And if likewise, if we consider the second and the seventh column, there is 1 point common. So if we check every pairwise combination, then the number of concurrences will be either 0, 1 or 3, and nothing in between that. So these three numbers will be fixed. Next. Now, this Agarwal 1966 also gave two methods of constructing these IRC designs for two-way elimination of heterogeneity, where he used two balanced incomplete block designs to construct an incomplete row column design. But this method of construction given by Agarwal 1966 for constructing the new series of incomplete row column design is little complex. So to avoid this complexity, a well-defined algorithm has been proposed for generating this design. I am explaining the steps involved in the construction procedure with the help of this algorithm. The algorithm takes two incomplete block designs, say D1 and D2 as inputs, and generates a new incomplete row column design. The two input designs may be balanced incomplete block designs, or any partially balanced incomplete block design, or T design. So let me consider an example to explain this algorithm. So let us consider a balanced incomplete block design, which is D1 with the following parameters, and an appropriate design D2. It is a 3 design with the parameters as mentioned here. And we have to verify the condition that V2 is equal to R1, that is 5 year, and B1 is equal to B2 is equal to 10 year, and K1 is equal to K2 is equal to 3. So these three conditions must be satisfied in order to move forward. So then we obtain the incidence matrix of the first design, that is D1, the balanced incomplete block design that we have considered. Now, by replacing the unity position of in the columns of the incidence matrix with the block contents of D2, the second design, we obtain a matrix A as shown here. Now, we have to check if each row of matrix A contains all the V2 treatments exactly once. Else, we have to rearrange the column items of the matrix A to make each row of A unique in terms of V2 treatments. So the matrix shown in the third matrix is the rearranged matrix. So the final design is obtained by taking the column numbers corresponding to each treatment in matrix A as the entries of the columns of the final design. And like if we take treatment 1, we see that 1 occurs in the column numbers 4, 3, 6, 7, 1 and 8 in the matrix A. So 4, 3, 6, 7, 1 and 8 will form the first column of the resultant incomplete row column design. Similarly, for the rest of the treatments, we will do likewise, and we will obtain the final design as shown here. And the parameters are mentioned here, where we see that B will be equal to B and R will be equal to K, and the number of rows, that is P, will be equal to V1, and the number of columns will be equal to V2. So the C matrix of this design is given, and the association, the treatments follow a 2 associate class triangular association scheme, and possible arrangement of the association scheme is shown here. Here the two treatments, the triangular association scheme is that the two treatments are first associate if they appear in the same row or column in this arrangement, else they are second associate. Moreover, both the row component and the column component of the design is also triangular, also follow triangular association scheme. And the canonical efficiency factor of this design is 81.44%, which is also quite high. So the experimental model for incomplete row column designs for V treatments, each replicated R times and arranged in P rows and Q columns, can be represented as by the model shown here. And here I have shown the X matrix and the theta vector, and X matrix is partitioned like X1 and X2, and theta is also partitioned as theta 1 and theta 2. Then for finding out the C matrix, the information matrix, we have to find the generalized inverse of x1, x2 prime, x2, where x prime x is also partitioned, and we get the final form as the final form is obtained as shown here. SAS code has been developed to compute the canonical efficiency factors of the designs, and we see here that the canonical efficiency factor is 81.44. A package named IRO-code has been developed for the generation of the new series of two-part incomplete row column designs with incomplete rows and incomplete columns, and a snapshot of the package for 10 treatments is shown here. So a list consisting of various parameters of input block designs and output incomplete row column designs for B less than equal to 20 has been prepared, and the list also reflects that the nature of the row as well as column component designs are also reflected here in the list. This work has been published in the Journal of Statistical Planning and Inference, and now we are moving forward. Let us take another situation, like let us consider the study of the effect of different feeds on animals in an animal experimentation, where the feeds comprise the treatments, the breeds and housing conditions are the two sources of variation. But the constraint here is that all breeds cannot be kept in all the housing conditions. So here we can see that at least one row column intersection does not receive any treatment, and such a design under two-way blocking structure is called a structurally incomplete row column design. So a two-part structurally incomplete row column design, I'm defining it before only, can be defined on V treatment combinations with P rows and Q columns such that each treatment combination appears in each row at most once. All treatment combinations appear in each column equally frequently. All rows involve same number, that is K1 of treatment combinations. All columns contain same number of treatment combination, and every component in the combination of size K2 from V2 treatments must appear in each column equally frequently. So these designs are structurally incomplete, as we have seen that if at least one experimental unit in the design does not receive any treatment combination. So fusion of the IBDs may result in a systematic manner, as I have already mentioned before, helps us in obtaining these two-part structurally incomplete designs, both two-part structurally incomplete row column design and two-part structurally incomplete block designs for testing a set of treatment combinations. So the method of construction for these two-part structural incomplete designs. First, I will talk about the structural incomplete row column design, where we start with two incomplete block designs, D1 and D2, satisfying the conditions like B1 is equal to B2 is equal to B. That is the constant. There should be equal number of blocks for both the designs. Then the B1 blocks, each of size K1, are to be filled with the block contents of the second design, that is D2. After this, we have to rearrange the block contents of the second design such that not a single treatment combination occur more than once in a given row. Each treatment combination occurs at most once in any given column, and each individual component of treatment combination must occur equally frequently in each column. Sometimes we have to repeat the blocks of this D1 and D2 so as to satisfy the frequency conditions. Thus, the resultant design will be a structurally incomplete row column designs with the parameters as mentioned here. I have also derived the information matrix considering a normal row column model, and we find the generalized matrix of x2 prime x2, and then the final form is obtained as shown. Now let us consider another nutritional experiment where different types of mango juices are given to 10 different age groups, and the objective is to identify the most nutritive juice for each of the age groups. Now 4 different varieties of mangoes are available, suppose, and the juice given to each of the age groups is a mixture of only 2 of the 4 available varieties. So there will be 4C2, that will be 6 types of 2 variety combination of juices, and it is assured that all the age groups receive all the 6 types of juices. For this, we consider 2 designs, D1 and D2. D1 is a triangular for PBIB design and for 10 age groups, and D2 is a balanced incomplete block design for 4 varieties. Now, since D1 has block size 5, any 5 out of the 6 variety combinations are to be given to the particular age groups present in block 1 of this first design. So, for the first block, I am talking about the first block of the first design, that is age groups 1, 3, 4, 5 and 9 will receive the varietal combinations, will receive any 5 of the varietal combinations from the second design, that is D2. Similarly, for the other blocks, we will move on in a similar manner, and it should be noted that all the age groups may not be available in every location. So, depending on the availability of age groups, we may arrange the blocks of D1. The resultant design will be V is equal to 6 treatment combinations with P, that is the number of rows, is equal to 12, number of columns is 10, and 10 replications. So using the derived expression, the C matrix for the design for the given example is shown here, and the treatment combinations follow a rectangular association scheme over here. And the rectangular association scheme is that the treatment combination in the same row are first associate, in the same column are second associates, and the rest are third associate.
Sandhini, you have to wind up in 2 to 3 minutes. Huh?
Okay. A SAS code has also been developed for studying the properties of the design and computing the canonical efficiency factor, and we can see that the canonical efficiency of this design is quite high. So sometimes it may be possible that not to obtain 12 rows and 10 columns, a design of 12 rows and 10 columns. So we can also have a design with 6 treatments but with lesser number of rows and columns. So here is an example of such a design. So the C matrix of this design is shown, and here the treatment combinations follow a group divisible association scheme, and we can see that the efficiency factor of this design is also quite high. Now, if we consider another experimental situation of integrated farming system, where considering field crops and dairy as compulsory components in all the systems, there may be more components to be added to the integrated farming system, depending on location. So here, if we consider 5 components shown here to find out the best combination that will yield maximum profit. Suppose there are 5C3 combinations that can be allotted to 10 households in each of the locations, and every location may not have resources for every combination. So comparison of households is not of interest here. So locations can be treated as blocks and a design can be developed for such a situation. A two-part structurally incomplete block design will be suitable for such as a situation where sometimes due to unavoidable constraints, as I've told, we may have to allot the same treatment to either rows or columns, thereby making one of the blocking factors ineffective. Hence, one may apply the same treatment combination in all the K1 positions such that the component treatment occurs equally frequently in each of the blocks. This gives rise to a two-part structurally incomplete block design. So one such situation was considered by Bailey and Cameron in 2019, where they have considered a design with 10 medical centers with 6 cancer types, 5 drugs, and each medical center is having 3 cancer types and 2 drugs. And for each medical for each cancer type at that medical center, each patient will be allocated to one of the drugs at that medical center. The aim being that the number of such patients on each drug is nearly equal. So there is no interaction within the drug. So they have developed a two-part 2 design. And two-part structurally incomplete block design can be defined accordingly, as shown, as I have mentioned the point here. And the method of construction for this structurally incomplete block designs are same as that of I have discussed in for the structurally incomplete row column design. But the only difference is that the K1 positions in each block of the D1 are filled by the contents any one block content of D2. And here is an example of a structurally incomplete, two-part structurally incomplete block design, and the C matrix and the association scheme I have shown. And here also a SAS code has been developed for computing the efficiency and studying the properties. The work has been published in a few major publications related to this work, one in Current Science, Journal of Current Science, and the other in Journal of Indian Journal of Animal Sciences. So to summarize, I can say two-part incomplete row column designs are economical and efficient, but constructing these designs through the algorithm is lengthy and complex. So our package developed helps in easy generation of these incomplete row column designs that saves a lot of time. And two-part structurally incomplete row column designs have been developed to identify the best combination of treatments. And imposing a further constraint, a two-part structurally incomplete block design have been developed to find out the best combination of treatments. And plenty of incomplete block designs are available in literature, and these two-part designs can be obtained very easily by fusion of any two compatible incomplete block designs. So these designs also show good efficiencies and also have high application potential. So these are my references. Thank you.
Yeah, Dr. Sayandini, what a commendable journey from sample surveys to design of experiments. Huh? Now you are, what we can say, expert in design of experiments. So we can have a quick discussion. It's open for discussion. Anyone? Yeah, I know Dr. Eldo will surely have a question.
It's actually a doubt, a clarification I needed. That's why, not a question to her, because she has done a lot of work in that area. I just want to know, because you have shown that paper by Dr. Agarwal, that 1966 paper, it was in JASA, I suppose. No?
Yes, sir.
JASA. So in that paper, he has listed several designs, incomplete rock column designs. So you also attempted to generate designs in a similar manner. I mean, not the method I'm not talking about, but you want to get incomplete rock column designs for those parameters, especially the if you keep number of parameters into consideration, number of treatments into consideration. So have you, because there are some entry gaps we can see if we go through that paper by Dr. Agarwal. So could you fill up all those missing entries there? Because not all treatments, I think the designs were not available there in Agarwal's paper. So could you get all the designs? I mean, that all those missing entries, could you generate designs through your package
Yes, sir.
or through your algorithm?
Yes, sir. I have generated means the algorithm developed generates all the designs means for all parametric combinations that were missing in Agarwal's search paper, and the designs available in Agarwal's search paper is also forms a particular case of this of the designs I have generated.
To how you can
Okay, so
ensure
what
all
about
the
the efficiency?
designs?
Whether
Means a lot of parametric combinations are achieved with this generalized. We can say a generalized form of the Agarwal's designs is the designs I have developed.
Yeah, it may be a bigger superset, but you cannot ensure all because you also have some restrictions like B1 equal to B2, something like that, no?
Yes.
So there may be still scope, like Dr. Eldo is asking.
Yes, sir. Yes, ma'am.
Another concern was with regard to the efficiency, whether the designs you have generated for the same number of treatments what Dr. Agarwal has given, is there any difference in efficiencies or any difference or is it the same?
No, sir, there was slight difference in very minimal difference was there.
Okay, it's minor. Okay. Another just again one more, if our chair permit, regarding your that structurally incomplete designs you have mentioned. I think there is a paper, whether I don't know whether you have mentioned it there or not, by Rita Sahare in Statistica Sinica,
yes, sir.
1996 paper. So could you generate any design? I mean, in a similar line, in the sense that any like you attempted in case of Agarwal 1966. Could you try to get a similar sort of set of designs for structurally incomplete category? What is missing in Rita Sahare 1996?
Yes, sir. Sure, sir. I will try.
Sahare's paper was basically for unequal block size. I recollect. I don't know. I'm not sure.
It was structurally incomplete in general. Okay. Then that I'm also not sure about.
There is a paper by Sahare.
Yes, sir.
Very good paper. What advice you will be giving to the junior students who are listening? What is the future scope of your work?
Future scope is that like in incomplete block designs, incomplete row column designs that I have generated, there may be a further scope of improving that designs. So they may try for that, and these two-part designs can be further expanded to multi-part designs.
Okay, fine. Thank you, Dr. Sayandini, for a very nice presentation. Now we call on. Yeah. Any other questions? Yeah, you can unshare your screen. Now we call the third speaker, Dr. Harun. Dr. Harun is working as a scientist in ICRISRI. How many years experience, Harun? 6, 7? I think 6 to 7 years of experience. I didn't get his bio sketch. He has almost 30 to 40 good publications and many packages, software and SaaS macros under his belt. And he's basically today he is going to present a paper on experimental designs for higher order crosses. So he might be covering all higher order crosses like partial trial and tetrallel, I believe. So that is altogether a different area he is going to discuss. I hope this will be of interest to the students listening. Thank you, Dr. Harun. You can start your presentation.
Thank you very much, ma'am. Let me share the screen.
He's also an award winner, Young Scientist Award winner. So all Young Scientist performance will come up now.
Ma'am, is my screen visible?
Yes, it is visible.
It is full screen?
Yes, you can start.
Okay, ma'am. Okay. Welcome everyone. And today I will be presenting work on the topic experimental designs involving higher order process. And in this I will be covering the higher order process like three-way and four-way that are also known as the trial process or tetrahedral process. And sometimes the tetrahedral process or the four-way process are also referred to as double process. So first of all, let us, since it is an application of design of experiments in the breeding sector, so we have to understand its importance and application, how much it is important and where it is applied. So let us have first understand that the breeding techniques which are generally employed for the purpose of commercial hybrids with the potential phenotype, and for this a major objective is to raise the genetic potential, and for this we have to acquire the information regarding the general combining ability effects of the individual lines and as well as the specific combining ability effects of the process. And these two effects and these two information which is collected, this forms the basis for the breeders to select the best parental line precisely. So all these mating experiments which are done, the basic motto is to attain information on general combining ability effects and the specific combining ability effects. Now when we are talking about mating designs, the oldest and rigorously used breeding technique is the diallel, which is also known as the single cross or the two-way cross, and it is the simplest in terms of ease of management, where only two lines are crossed to get a hybrid or get a cross. So let us understand by how these crosses can be categorized. So a mating design can be of two-way cross, three-way cross, or four-way cross. A two-way cross, which is also known as single cross or diallel cross, three-way cross are also known as triallel cross, and four-way crosses are also known as tetrallel cross. So as the name indicates, in two-way crosses, two lines are involved to give the offspring. In three-way cross, three lines are involved to give the offspring, and same in the four-way cross. Now, I want to tell that these crosses can be these three types of crosses or the mating designs can be further divided into two types, that is complete and partial. What is a complete? Suppose that if you are taking two-way cross or diallel cross, so what is a complete diallel? It means if you are taking all the possible diallels that can be made for a given number of lines, then it will be known as complete diallel cross. And due to some reason, due to some restrictions or unavailability of or restriction of resources, if we are taking a sample from this total possible crosses, then it is known as partial diallel cross. Similarly, the term partial triallel crosses and partial four-way crosses or partial tetrallel crosses. And here, since we are taking a fraction, so the concept of sampling fraction, that is also known as degree of fractionation, also comes into the picture, which can be calculated as the number of cross in the partial one divided by the total number of crosses possible. So now the problem comes, the main thing which I want to tell here is that since the diallel crosses are the mostly adopted and the ease due to the ease of management, but if we consider them, the model if we consider the model of a diallel process, and we can see that the higher FCA effects are not estimable, but in case of the higher order process like double process, then we can estimate the higher order effects. Now, why it is important to estimate the higher order effects also? So, higher order crosses that can be used to improve the quantitative traits which are of economical as well as nutritional importance in crops and animals by providing more information regarding the specific combining ability effects. Besides this, it is very important to note that the hybrids which are based on the higher order process like double process or the trial process, they are genetically more viable, stable and consistent in performance as compared to the lower order process, that is the single cross. Also, the higher order cross hybrids have wider genetic base, and these due to this wider genetic base, strong buffering mechanism is there. Whether it is we are considering it as an individual or whether we are taking it as a population. Now let us see some of the areas where it is used. So we can see that the commercial hybrids of corn are double cross based. Similarly, in case of piggery, we can find higher order crosses to be applied, and which gives the outcome having the fast growth rate, good feed efficiency, and having better carcass quality. Similarly, in case of silkworm production, also higher order crosses are exploited. Now there are many examples in the system, in the ICR system, where we can find that these are being used or these are being continued for the purpose of commercial hybrid production. So some of the examples which I have taken from different ICR institutes are in case of poultry, we can find that in case of poultry we have three-way process and four-way process, and in case of corn, as I have already told. Now, with an example of double cross, I want to tell. So you can see for the number of lines n is equal to 5. Here is example of complete double cross and partial double cross. So we can see how a double cross is made. Suppose for a double cross we require 4 lines, 4 different lines. The first 2 lines are crossed like 1 cross 2, and then 3 cross 4 is already done, and then again these 2 crosses are crossed to give a 4 cross. And if we take all the possible crosses, here we can see all the 15 crosses if taken, then it gives a complete double crosses. But suppose if you are taking a sample from this, here for example, here it is a double cross where there are only 10 crosses. So the partial the degree of fractionation will be 10 by 15, that is 2 by 3. Now before moving to the different designing and analysis aspect, I want to tell what are the main purpose of these type of designs, mating designs. Generally 3 types of situations we handle here. The first one is design for test line comparisons. So here we have, suppose we have some test lines, we are newly developed test lines, and our main objective is to check which of the test line is performing better by having a comparison between them. The second situation is design for test versus control comparison. Here we have 2 types of line. We have test lines and we have control lines. So what are the control lines? Control lines are those type of lines means which are already established and which are already being commercialized or and giving better performance, and test lines are the newly developed lines. So our objective is always to have a have a comparison of test lines with control lines, so that we can get the result about which of the newly developed lines are performing better than the control lines. So the main objective is test versus control comparison, and at the same time we are also interested in test versus test comparison also. Now there may be a third type of situations which I am dealing with the example of 4-way crosses. Suppose that we have 2 set of lines. The first lines are named as primary lines, and the second set is known as secondary lines. So in terms of importance, the primary lines are having more importance, and the secondary line set is having less importance. So what is our interest of comparison here? So the first, since the primary lines are of more importance, so our most interested, we are morely interested in the comparison of primary lines within themselves. Then we are also interested in comparison of primary lines with secondary line, and our least preference will be the comparison of secondary lines within themselves. Now whenever we are talking about preferences, what does it mean? Preference means those having highest preference, they must be compared with highest precision. When we are connecting this to a design, highest preference means highest precision. So we have to develop designs in such a manner that those having higher interest must be compared with higher efficiencies or higher precision. Now let us start with a double cross. So here the model of a double cross, suppose that a cross given by I cross J cross K cross L. So the cross effect can be shown in this manner, where tau IJKL is the cross effect, double cross effect, and tau bar is the general mean. Here we can see that the GI, GJ, GK, and GL, these are the GCA of the lines, say IJKL. Similarly, SI, SIJ, SIK, SIL, and up to SKL, these are the specific combining ability of first order. That means those involving two lines. Similarly, we have second order interaction, that's at or second order SCA effects, and we have the third order interaction effect. Now this the model can be written in the form of matrix notation. For in order to write this model in matrix notation, we have to consider, we have to a matrix W matrix of order n by t, whose rows are indexed by line numberings, say 1 to n, and the columns by the crosses, and the entries there takes value 1 if suppose that a line is coming in a particular cross, then it will take value 1, and if that line is not present in a particular cross, then it will take value 0. And similarly we can have these results. Now these are the model under a block setup, or this and in case of row column setup. So here we can see that besides the cross effect, we have block effect also in the block setup model, and in case of row column setup, we have the cross effect, we have the row effect, and we have the column effect. So these are the models and for the block setup and the row column setup. Now let us see some of the designs, how they are constructed, and some of the method of construction of design. So first of all, I want to tell the method of construction of optimal four-way cross design. So these designs are basically based on mutually orthogonal Latin square. For this, and the parameters will be, there will be capital N number of crosses, and T, that here capital N represents the number of lines, and capital T for the number of crosses, that is n into n minus 1 by 2, and the block size K is equal to n, and the number of blocks will be n minus 1 by 2. Now let us understand by an example. Suppose that we have to construct for number of lines n equal to 7. For 7 number of lines, what we have to do is that we have to take n minus 1 by 2 number of moles, that is 7 minus 1 by 2, that is 3 moles, and for that here these 3 are not the full moles, but we have taken the upper 4, any 4 of the rows, any 4 rows of the moles. So we can see that we have 3 moles and only 3 rows are there. Now what we have to do is that just take each column as a tetrahedral or the 4-way cross. So in block 1 we will be having the 7 columns as the 7 crosses. Similarly, the other blocks are also constructed. So this is the design having a design for 4-way crosses having a 7 number of lines. Total number of crosses are 21 in 3 blocks of size 7 each. Now similarly, let us see for the 3-way cross. For the 3-way cross, what we have to understand that there are 2 types of lines involved in a cross. For example, 1 cross, 2 cross, 3. Whenever we are saying a cross, then there are 2 types of parents are there, because first we have to cross 1 cross 2, and whatever the progeny is coming, it has to be crossed with the another line, that is 3. So here 1 and 2 are known as half parent, and 3 is known as full parent. Since there are 2 types of parents involved, so there is some complexity involved in the model as well as while deriving the estimates. So here what is the main changes in the model is that we have to include 2 types of GCA effect, that is for GCA effect regarding the half parents as well as GCA effect regarding the full parent, and rest all the derivations and the derivations of information matrix and the efficiency all follows it. Now let us see an example for the method of construction of 3-way cross. So this method is based on 2 associate triangular association scheme with total number of lines given by n into n minus 1 by 2, and with total number of crosses t equal to n into n minus 1 into n minus 2 by 2, and blocks is equal to n, and k, the size of blocks is n minus 1 into n minus 2 by 2, and RH denotes the number of replication of half parents as a lines, and RF denotes the replication of full parents as lines. Now let us see through an example. It can be easily understood. So this is an example for n equal to 15. We can see here how in a triangular association scheme the symbols are arranged in the upper diagonal and the lower diagonal positions with the diagonals being empty. So suppose that how a cross will be made. So block 1, let us see block 1. So for block 1, let us consider the row 1. So from row 1, how many pairs can be obtained? So there are 5 symbols, so 5 C2 pairs can be obtained. So 5 C2 pairs means 10 crosses, 10 3-way crosses will be there in block 1. So consider a pair A and constituting A and B. So what we have to do is that we have to take the row constituting A and we have to take the column constituting B, or vice versa. So we will get F at the intersection of this. So the cross will be A cross B cross F. Here A and B are half parents and F is full parent. So in this way, from each row, the 3-way crosses can be obtained, and since there are 6 rows, so there will be 6 blocks, and with having 5 C2, that is 10 number of crosses in each. Now these are the information matrices. Here this I want to show because there the information matrices needs to be bifurcated in 2 parts, that is the information matrix pertaining to the half parents as well as the information matrices pertaining to the full parent. Similarly, all the derivations have to be done for both. Now the second method is based on the lattice design. So this is a very easy method where what we have to do is that any lattice design with standard parameters B, B star, R star, K star, S is considered, and the block contents are taken as lines. So let us see example. So here is a square lattice design, and this can be used for here we are taking K is equal to 3. So all these block contents, if you are taken as, we just take as crosses, three-way crosses, then we can have a PTC design in 4 blocks. Similarly, the other type of lattice designs, that is rectangular, circular, and cubic, all those can be used or exploited for constructing partial triangular cross designs in the similar pattern.
Dr. Harun, you will have 3
Now
minutes.
another
3 more minutes.
Okay, ma'am. Similarly, we can have much more of methods, but let us go for the different type of comparison. That is, for example, test versus control comparison. So till now we were dealing with test versus test comparison. Now we have one example for test versus control comparison. Here also a very simple method I have illustrated. Any incomplete block design with parameters P, B, R and K is equal to 2. So our block size is 2, and lambda I, what we have to do, we have to add a control treatment, say 0 to each, and then we will make three-way crosses from each of the element. For example, you can see it is a BIBD. We have added 0 to each of the block content, and then we have made a parallel cross, and it is a parallel cross for test versus control comparison with having 4 test treatments and 1 control treatment. Now let us see another example, that is I want to tell with respect to the 4-way crosses, that is augmented partial 4-way crosses. You know 4-way crosses, you know partial, and now we will be dealing about the situation that is augmented situation. So in case of augmented situation, let us see with an example. For example, consider a maize breeding experiment in which we have started with 100 new lines. Okay, then but at last in the while dealing with various type of laboratory experiments, we have from 100 lines, what we are doing, that we want to have 2 types of resistant varieties, that is which are having high yielding as well as drought resistant varieties. Now comparing these 100 lines with already developed test lines, we come across with 9 lines in which 4 are high yielding as well as drought resistant, and the rest 5 were moderately drought resistant. So of course the first 4 lines are of prime importance, and the second are of secondary importance. So let us see how a design can be obtained. So we have 4 primary lines and we have 5 secondary lines. So here what I want to show is that the primary lines will be crossed with each of the primary lines and as well as each of the secondary lines. But in case of secondary lines, we will be taking a fraction. That is, we will not be crossing all the secondary lines with all the secondary lines. Here by lines I am referring to a hybrid, which is a diagonal hybrid, because it is augmented partial 4-way crosses. So in the rows and columns we can see these are not lines, but these are already the diagonal crosses. Now let us see an example how. So I have tried to construct a general method of augmented partial 4-way cross construction, which can be used for construction of any type of augmented partial 4-way cross plan. And all the C matrices, inverted form, and the efficiencies have been derived. And now let us see the construction. So there are 3 steps. In the first step, we have to take a complete four-way crosses based on primary lines. Then we have to prepare two complete diagonal crosses based on primary and secondary lines, and we have to cross them all as I have shown in the figure. And in the step 3, which is the main process, in which we have to use some newly constructed partial four-way crosses. So when all these 3 steps will be combined, it will give a series of augmented partial four-way cross plans with total number of crosses as this and degree of approximation given by these formula. Now some of the SAS codes have been written now, and lists have been also prepared, but I would like to invite some questions for better understanding.
The topic is open for discussion. It's a beautiful blend of statistical genetics and design of experiments. So if any student is working in either of the area, they can ask questions and get clarification. Dr. Harun has worked in MSc and PhD from ICAR IRI on related topics. So he will be able to answer any of your queries. Please come up with some queries. If not Harun, I would like to ask whether any of your designs have been implemented in any live situation. If yes, which type of design?
Ma'am, please repeat the question.
Any of your designs like this with low fractionation, you have you have developed many designs. Any of them have been actually used to anywhere?
Yeah, ma'am. Actually, I have worked in 2 stages. In the first, I have tried to develop the methods of construction. In the second, we have just coordinated with the those working in these areas, and in 2 live situations and low live experiments, I have given one is for poultry experiments and one for maize experiment. In both situations, I have recommended and given a design for four-way crosses, and for maize experiment, it has been already done, and the data is being processed. And for poultry experiment, it is under the screening process, and it will be
Why four-way crosses? Why not three-way cross?
Actually, three-way crosses also, because of four-way crosses. Why I have taken four-way crosses? If you are taking four-way crosses, then in the meantime or in the course of experiment, we can also get three-way crosses as well as diagonal crosses. And I have requested them also for three-way and for diagonal data also.
Okay, what will be the recommendation for future scope, future work?
Same, it can be, the work can be, since whatever designs are available, they are generally requires large resources. So it is very much important to have designs which are highly efficient as well as require much lower resources. And besides this, if someone is working in the area of biotechnology or in, so combining these mating design experiments along with biotechnology, it will be having a very high future, and it will be very much accepted in the field of breeding and genetics if we can combine those two.
Yeah, but after that also they will come back to a phenotypic trial, right?
Yes, ma'am.
Okay, thank you, Dr. Harun. Anybody has any questions, please? If not, we can move on to the next topic. This topic was on designs for breeding experiments, any type of crosses, diallel, tetraallel, or triallel. But we all know that before these crossing trials, we have many stages in a breeding program. that is early generation breeding program, late generation breeding programs are there. So for screening out the best lines for these breeding trials, we have next topic here, that is partially replicated designs. So I invite Dr. Vinay Kumar LN, who has just completed his PhD from ICR IARI, who has 8 papers to his credit, and he's an expert programmer, so many packages are there under his name, published packages. So he'll be talking on partially replicated designs. Vinay, you have 25 minutes. Kindly sum up in 25 minutes.
Thank you, ma'am.
Share your screen.
Is it visible, ma'am?
Really? I'm not able to see. You share the entire screen and share this and repeat. That mirror image thing was happening. No.
Now, ma'am?
Yeah. Full screen, please.
Good afternoon, everyone. I am Vinay Kumar LN, PhD Agricultural Statistics from PG School, IRI, New Delhi. First of all, I would like to thank you all organizers for providing me this great opportunity to talk on partially replicated designs. This is the overview of my talk. We all know that farmers, national institutes like ICR, non-ICR, individual plant breeders, private seed companies, they are need the development of new plant and animal materials such as pure lines, hybrids, composites, synthetics, etc. This development of new material are from different plant breeding methodologies. After development of this new material that are gone through identification and testing by annual workshops or group meetings of All India Coordinated Crop Improvement Projects, then these new lines are tested in multi-environmental breeding trials to screen out the best performing lines from the large number of lines. After that, this developed new lines are coming to the multiplication chain system. Here, the entries such as breeding lines of interest and check varieties for the screening purpose that are gone through the selection process. In that selection process are classified as a preliminary stage of selection and advanced stages of selection. In preliminary stages of selection, the main selection criteria is disease and pest tolerance, phenology type, and functional quality of yield. In case of advanced stages of selection, the key selection trait is the quantity of yield. These advanced stages of selection are again classified into EGBTs, that is early generation breeding trials, and LGBTs, that is late generation breeding trials. In case of early generation breeding trials, the number of entries evaluated is more than 1,000. The resource and seed limitations reduce the number of environments and plots for each breeding line. In EGBTs, the replication within an environment is often less than 2, and the number of environments is usually less than 4. In nowadays, to conduct these early generation breeding trials, the partially replicated designs are have high application potential. The partially replicated designs are also known as peer-rep designs, which are particularly useful when trials are repeated across environments. When there are E environments, one can replicate 1 by each of the entries at each environment such that each entry is tested with 2 replicates in one of the E environments. These designs can be seen as a design intermediate between a replicated and unreplicated design. Williams et al. In 2011, he has developed a peer-rep design with the help of alpha designs. So the construction procedure given by Williams et al. is majorly involved in the 2 steps. In step 1 is to construction of alpha design. For example, for V is equal to 20 lines, we will obtain alpha design in 4 replications. These 4 replications are mainly obtained from this generating alpha array. So each column of this generating alpha array will form the each of the replication of alpha design. After the development of this alpha design, the Williams et al. Associate this replication 1 and replication 2 to the environment 1 and replication 3 and replication 4 to the environment 2 by deleting the entries which are corresponding to the off diagonal entries of this alpha array. In this alpha array, the off diagonal entries are 0, 2, 2, 0. So the corresponding entries of this off diagonal entries are removed. Then we will obtain he obtained the period design. This is the example for alpha design in case of V number of treatments. Here C1 is indicating the first column of the alpha array. In this first column, the off diagonal entry is 0, so its corresponding entries are removed. Similarly, from replication 2, the off diagonal corresponding entries are removed. Then associate this replication 1 and replication 2 to the environment 1. In similar way, they associated replication 3 and replication 4 to the environment 2, so such that this will give the period design for V is equal to 20 treatments in 2 environments. Here it is observed that in case of environment 1, the 1 to 10 treatments are replicated twice, and in case of environment 2, the remaining treatments are replicated twice. So these are some important review of literature related to the period designs and also their application in early generation building trials. In Williams et al. In 2011 and also he worked in 2014, they give 2 series of period designs. They obtained that series of period design mainly by alpha designs. So that underlying construction procedure is also complex, and whatever the designs are available in literature, they are only for in case of equal block design setup, and there is no period designs are available to comparing the 2 distinct sets of lines. So these are the major findings of our research in studying the partially replicated designs. Here we have developed 3 different series of higher associate resolvable PBAB designs for different treatment structure. These resolvable PBAB designs have promising application in construction of partially replicated designs. So then we have developed different 3 series of partially replicated designs for different treatment structure. This is the outline of method of construction of PBAB designs for the treatment structure V is equal to PQ. The resultant designs are affine resolved PBAB 3 designs with affine resolvability constant K1 K2 by V equal to 1. I will explain this construction procedure with the help of an example. This is the corresponding association scheme of this method of construction, and also for the developed designs, we obtain the information matrix that is C, and its inverse is C inverse, and also we obtain average variance factor that is AVF, canonical efficiency factor that is CAF, and also we obtain the variance estimated variance between the different treatment contrast, that is V1, V2, V3. Now coming to the example, here we consider P is equal to 6 and Q is equal to 4, that give rise to the V is equal to 24 treatments. Here P is indicating the number of sets and Q is indicating the size of the each of the set. Here there are 6 sets, size of the each of set is 4. Each block of the replication 1 are obtained by considering the entries of each of the sets. For example, block 1 of replication 1 is obtained by the entries of the first set. Similarly, each block of the replication 2 are obtained by considering the different positions of the all sets. For example, the block 7 of the replication 2 is obtained by the considering the first positions of the all 6 sets. Similarly, remaining 3 blocks are obtained. Now coming to the association scheme, the within sets entries are the first associates. The entries which are in different positions of the other sets are second associates. Remaining entries are the third associates, and their affine resolvability constant is 1. Now coming to the another series of PBAB designs for the treatment structure V is equal to SPQ. Here also the resulted designs are affine resolvable, hence they are optimal in the class of design. I will explain with the help of an example. This is the corresponding association scheme. These are some important properties related to the developer designs we have computed. Now coming to the example, here we considering S. Here S is indicating the number of subarrays, P is indicating P and Q are indicating the rows and columns of each of the subarray. So here we consider S is equal to 4, P is equal to 3, and Q is equal to 2. That gives rise to the V is equal to 24 treatments. Then these 24 treatments are arranged in 4 subarrays, each of the size 3 cross 2. Then each block of the replication 1 are obtained by considering the first row of the all subarrays, and also each block of the replication 2 are considering the columns of the all subarrays. For example, the block 1 of the replication 1 is obtained by considering the first row. Similarly, second and third rows entries are considered to obtain the block 2 and block 3 of replication 1. Then in a similar way, the column entries are considered to form the block 4 and block 5. Now coming to the association scheme, the entries which are in the same positions of the different subarrays are the first associates. The entries are in same rows of different subarrays are the second associates. In same columns are third associate, and remaining entries are the fourth associates. Here the canonical efficiency factor of this design is 0.88, and average variance factor is 1.13, and affine resolvability constant is 4. Now coming to the particular case of this design, if you consider P equal to Q, then the treatment structure is reduced to V is equal to SP square. Then the resulted PBAB 4 designs are reduced to PBAB 3 designs. Now coming to the comparison with the existing designs, for the treatment structure V is equal to SPQ, there are two well-known classes of designs are there in literature. That is 4 associate right angular designs and 3 associate nested group reusable designs. But the existing designs are non-resolvable and they are available in only equal block sizes. But whatever the designs we have proposed under V is equal to SPQ treatment structures that are resolvable, mainly affine resolvable, and they are available in unequal block sizes. For example, for V is equal to 24 treatments, the right angular designs is available in 12 number of replications with efficiency factor 0.90. But our design is available only 2 replications with efficiency factor 0.88. Now coming to the series 3 PBAB designs, which are resolvable designs, we have developed for the treatment structure V is equal to 2P minus 1 into P. This is the corresponding association scheme of these designs. They have some important properties of these designs. Now coming to the example, here we are considering P is equal to 4 that give rise to the V is equal to 24 treatments. These 24 treatments are arranged in 2 sets, that is R and S, each set consisting of P minus 1 subset, that is each set consisting of 3 subsets. In this method, we obtain the 3 different sets of blocks. From the first set, that is R, we considering the all combination of these subsets, that is R1 and R2 entries are from the one block, R1 with R3 entries are from the another block, and R2 and R3 will form the another block. So in similar, in this case, we will obtain 3 blocks. So another 3 blocks are obtained by all possible combination of this S1, S2, S3 subsets. Then the third set of blocks are obtained by merging the entries of R1 with S1 and R2 with S2 and R3 with S3. Now coming to the association scheme, the entries in the suppose the treatment 1 is appear in the R1 subset, though so the entries in the same set of R1 are first associates, and in the same set of different sets, that is S1 entries are the second associates, and the remaining entries of the R set are the third associate, and remaining entries of the S set are the fourth associates. Here for this design, the canonical efficiency factor is 0.83 and average variance factor is 0.79. This is the catalog we made for the two affine resolvable series of designs for the treatment structure V equal to PQ and V equal to SPQ. Here, as observed that as the number of treatments are increases, the canonical efficiency factor is also increases. Here we frame the definition for partially balanced P-RIP designs. A partially balanced P-RIP design is an arrangement of V lines in B blocks, each of size kW, distributed over E environments such that each environment consists of B by E block. Each line is replicated E plus 1 times. E distinct sets of V by E lines can be formed from V lines. In each environment, V by E lines are replicated twice, and the rest 1 minus 1 by E into V lines occurs once, and 2 lines that are mutually ith associates occur together in exactly lambda I blocks. Am I audible, ma'am?
Very well audible. Continue.
This is the construction procedure for the series 1 P-RIP designs. I will explain with the help of an example. Here the treatment structure is V equal to 2ms into S minus 1. In different subarrays, we are arranged a treatment like this. This is the corresponding association scheme of this series of design. These are the some important properties such as information matrix, average variance factor, chemical efficiency factor of developed series of design. Here, coming to the example, here S is indicating the number of rows and M is indicating the number of columns of each of the subarray. So here M is equal to 2, we are considering M equal to 2 and S equal to 3. It gives rise to the V is equal to 24 treatments. These 24 treatments are arranged in four subarrays, each subarray consisting of 3 rows and 2 columns. Here, each block of the replication 1 is obtained by considering the each entry of the subarrays. For example, the block 1 is obtained by considering the all entries of the first subarray. Similarly, the block 2, block 3, block 4 are obtained by considering the all entries of the second, third, and fourth subarray. Each block of the replication 2 are obtained by considering the rows of the all subarrays. The block 5 is obtained by considering the first row of the all subarrays. Similarly, block 6 and block 7 are obtained. After obtaining these PVAB designs, we associate the half of this replication 1 block to the environment 1 and remaining half of this replication 1 block to the environment 2, and by keeping the blocks of the replication 2 common to the both the environments, it will give the PRIP design in 2 environments. In similar way, we can obtain this PRIP design in 4 environments and also in 3 environments. The average variance factor of this design is 0.8 and canonical efficiency factor is also 0.80. Now coming to the another series of PRIP designs, here we consider the treatment structure as V equal to 10S, where S is greater than or equal to 2. These 10S treatments are arranged in 2 rows and 5 columns. So it consisting of total 10 cells. Each cell is indicated by the X H dot G, where H is running from 1 to 2 and G is running from 1 to 5. Here H is indicating the rows and G is indicating the columns. Then we generalize the block entries through the cells for the environment 1, that is Gth block. If we simply give the values of the simply give values to the G, we will obtain the entries for the different blocks. Similarly, for environment 2 also, we generalize the block structure. This is the corresponding association scheme of this series of design. Here it is observed that here we consider S equal to 2. It will give rise to the V equal to 20 lines. These 20 lines are arranged in 2 rows and 5 columns. Each cell size is 2. Under environment 1, the Gth block structure is X1.G, 2.G, and 2.G plus 4. If we give G equal to 1, that will give the first block entries. That is, cells are for G is equal to 1. The cell entries, the cells are X1.1, 2.1, 2.5. The corresponding entries of these cells are will give the entries of the block 1. Similarly, the remaining block entries are obtained. Now coming to the association scheme, for the treatment 1, the same cell entry is the first associate. The entries corresponding to this generalized cell structure are second associates. Remaining are the third associate. The average variance factor of this design is 0.8 and canonical efficiency factor is 0.83. This is the third series of PRIP design. For the treatment structure, V is equal to 6S lines. These 6S lines are arranged in 2 rows and 3 columns. So here also each cell is indicated by the X H dot T, where H is running from 1 to 2 and G is running from 1 to 3. Then this is the corresponding association scheme of this design. Here for S is equal to 2, it will give the PRIP design for V is equal to 12 lines. These 12 lines are arranged in 2 rows and 3 columns, each cell consisting of 2 entries. Here the blocks are formed by considering corner and mid cells. The block 1 of environment 1 is obtained by considering the entries of first corner cell along with immediate neighbors in same row, same column entries. That is 1, 2, 3, 4 and 7, 8 will form the first block. Similarly, second block of the environment will formed by the considering the second corner cell of the first row, that is 5, 6, along with entries in immediate neighbors present in same row and same column. So 3, 4, 5, 6, 11, 12 will form the entries of block 2. Similarly, block 3 is obtained by considering the mid cell of the second row. So mid cell of the second row and current cells of the first row, that is 1, 2, 9, 10 and 5, 6. In opposite way, the blocks of the environment 2 are obtained. Now coming to the associates of the line 1, the same cell entries are the first associates, and the entries in the same row are second associates, and the opposite corner entries are the fourth associate, remaining are the third associates. This is the catalog we made for the series 1 period designs for the treatment structure V equal to 2ms into S minus 1. Here we listed the different designs for different parameters. Here it is observed that as the number of lines increases, the efficiency factor is also goes on increases. This is the catalog for the series 2 and series 3 designs. Here we obtain the information matrix for the period design under the test versus control setup. Here the information matrix is given here. Now coming to the construction methodology, first we develop a series of first series of period design for test versus control through the reinforcement method. Here the series 1, as I discussed earlier, the series 1 PVAB3 designs are considered here. Then using these designs to form a period designs, then we simply augment the V plus 1 as a control treatment to the environment 1 and V plus 2 as a control to the environment 2. Then another series of period design for V equal to 2ms into S minus 1 treatment structure is considered. Then we augment the V plus 1 control treatment to the blocks which have lesser size. Then this is the period design in case of single control. Similarly, this is the period designs in case of multiple controls. Then we develop another series of period designs through the replacement method for test versus control. Here first we construct the S minus 1 designs using complete set of moles. Then out of S square treatments, we replace the last S treatments by the controls. That is, here it is the L3 PVAB designs. Here the last entries of the first blocks of first replication is replaced by the control 13. Similarly, the last entries of the blocks of replication 2 and replication 3 are replaced by the control 14 and 15. Then rearrange all the blocks to obtain the period designs in 2 environments. Then we have developed an R package called as RES PVABD designs. It is published in CRAN. This package has been developed for the to generate the proposed resolvable PVAB designs. Here we simply give the treatment structure as an input. This will generate the design parameter, design layout along with their efficiency and variance factors. Similarly, another R package called as period designs we have developed for the generation of developed period designs. It is also published in CRAN. It is also give the output consisting of design parameters and design layout along with efficiency and variance factors. So these are the R code we have developed to study the properties of this period design setup under the test versus control. Now coming to the discussion, here we have developed 3 series of higher associate resolvable PVAB designs, out of which first 2 series are affine resolvable designs, and affine resolvable designs, they are optimal in the class of resolvable designs, and third series is resolvable, and the first 2 series are available in both available in unequal block sizes. Then this developed higher associate resolvable PVAB designs have a promising application in the construction of period designs, and also further we have developed 3 new series of period designs for early generation breeding trials, both in equal and unequal block sizes, and also we developed few series of period designs to compare the 2 distinct sets of lines. The efficiency factor of developed period designs are fairly high and shows an increasing trend with increasing number of lines. The developed designs are cost effective in terms of resources as they require lesser applications and hence they possess high applications potential in multi-environmental trials. And the R packages so developed are helps in easy generation of proposed designs along with their efficiency and variance factors. Considering increasing in popularity of period designs among the breeders, there is need to obtain the more classes of period design for early generation breeding traits. The R packages are need to be strengthened by adding more series of designs. These are my references.
Yeah.
Thank you.
And Dr. Vinay, you are well on time. We can open it for discussion. Any queries? You can unshare the slides if you want. Any queries? Well, Vinay, you were showing some ARC again and again while you were discussing with the partially balanced incomplete block designs.
Yes,
What do you mean by this ARC?
Ma'am, that is affine resolvability constant, ma'am.
So the designs were affine resolvable. What would be the advantage of an affine resolvable design?
In the class of resolvable designs, the affine resolvable designs are optimal, ma'am, as per it has been discussed.
So you are using those affine resolvable designs basically for constructing these PREP designs?
For constructing PREP designs, ma'am.
So those designs also is expected to have good efficiency. Or resolvability also might be contributing a bit. Okay. Okay. Can we think of constructing some row column designs for partially replicated designs, because the number of screening trials, the number of treatments would be quite high? How long we can go on with the partial block design?
Yes, ma'am. We can construct using that row column design.
No, I couldn't see that in your future scope. That's I am asking you. I do not know. No, I don't know.
There are a lot of scope, ma'am. We can construct.
Okay.
When I have one
yes, sir.
One doubt. I mean, because the augmented designs are so popular
Yes,
for such kind of screening trials,
Yes,
where we do have replications for some of the control varieties which are already existing or where replication is feasible, and rest all are as a single replicatory layout. So, have you attempted to? Seen any attempted to have any comparison between your PREP designs with augmented designs, or can you suggest the advantage of yours in comparison to augmented ones?
Sir, advantage is that in case of a multiple environment with lesser number of applications, we can go through this partially replicated design, sir. Compared to
but the augmented design, Dr. Eldo is mentioning, they may be unreplicated designs. Is that augmented design you are mentioning, Dr. Eldo? Means only test treatments are unreplicated totally?
Yes, absolutely.
So what will be your design's advantages? Your all treatments are replicated somewhere or other, right?
In all the locations, some portion of the treatments are replicated.
So it could be like some unreplicated and replicated intermediate solution.
Intermediate solution between replicated and
that you mentioned in the beginning, but that could be the answer. Means augmented design, if there is a missing observation, we can't retrieve anything. Right?
Yes.
Okay. So that's a good discussion, and it was thoroughly based on Dr. Nair's, Professor Nair's contributions. So block design also we can consider one full topic on that. In fact, the earlier 3 presentations, except the first one, is closely related to Professor Nair's contributions. So now it's my turn. So let me share. Is my screen visible?
Yes, ma'am.
Okay. Okay. So I'll be talking about nutrosophic data analysis. So this is the structure of my talk. When our data is not a crisp data, how to go ahead with that, and fuzzy to neurosophic, how the development happened, and how we represent neurosophic data, and how the distributions are influenced when our data is neurosophic in nature, and hypothesis testing, a brief about that, when the data is neurosophic in nature, rules to follow, brief review of the related literature, and handling data obtained through designed experiments, just a short review or an update on that, we can say how to approach for designed experiments data analysis when the data is neurosophic in that nature, and how to go about, means path ahead, we can see, and references. So basically I have planned the talk as an introduction to this particular topic which is going on nowadays, so we can think about all angles, all other angles as well, but I am basically focusing how to develop the theory of design of experiments when our data is not crisp in nature. So in real life situations, in many of the, especially when we are working in agricultural scenario, when real life situations, it may not be always necessary to get crisp data when we measure the data. So data has some degree of indeterminacy. Maybe data is unclear, maybe it is vague, partially unknown, contradictory nature of the data, or data may be sometimes incomplete. So ignoring the range or vague values and taking the mid value is not always appropriate. For example, if our data set is like 2, 3, then 3 to 5, 7 to 10, like this. If you're just taking the mid value and going ahead with the calculation, it may lead to wrong interpretation. So to deal with such situations, fuzzy logic is introduced. So now the word fuzzy indicates vagueness or ambiguity. Vagueness is that the boundary of a piece of information is not clear, where the analyst is unable to clearly differentiate between two different classes. Ambiguity is a form of uncertainty where even the possible outcomes have unclear meanings or interpretations. For example, this crop is profitable. That could be a statement. This statement is very ambiguous because we don't know what kind of profit is being made. Or if we say he is a businessman, unless and otherwise, if we say what particular business he is doing, we cannot say, we cannot infer anything from that particular statement. It's an ambiguous statement. So now coming about the representation of fuzzy set. A fuzzy set can be defined on the universal set U in the given manner, that is A. Here mu A is representing the membership function of the set A, and it indicates the degree of membership of X in A. For example, if you consider sweetness of a particular fruit, say mango, A could have the contents like always sweet, sweet usually, sweet at times, not sweet, taking values say 1, 0.8, 0.3, and 0. So A could be a set like this. A fuzzy set could be like this. So now a little more generalization, or to bring in more clarity, intuitionalistic fuzzy set is defined, IFS. So here the membership function mu is already there, and we have another component added to it, that is non-membership function. So obviously the membership function and non-membership function, as they are ranging between 0 and 1, so their sum is also ranging between 0 and 1. We can estimate the range of or margin of hesitation also by subtracting mu and nu from 1. So again, that will range between 0 and 1. That is represented by pi here. For an example, suppose we have a universal set 18 years and above population. From that, we have two bifurcations. So in the left and right, you can see 18 to 40 years of age, they are considered as young and membership degree is given. 50 years and above is considered as old and non-membership degree is given. Now, what about the range 40 to 50 years of age? There is a degree of hesitancy here. So that is covered in IFS. Now, what is neurosophic? Fuzzy logic concept is then further generalized into neurosophic logic. This is coming from a Greek word neutrosophia, constituted by two words, neutros and sophia. Neutros meaning neutral, sophia means wisdom. So neutral sophic logic do not ignore the indeterminacy in the data. Every logical variable x is described by an ordered triplet here, t, I, and f, where t is the degree of truth, f is the degree of false, and I is the level of indeterminacy. So now, if we take an example here, it is the scale of infestation represented here. So here t is taking value that is completely safe, that is 0.4, completely damaged 0.3, by represented by f, and in between portion we can say it is the degree of indeterminacy. So that is represented by I here, which is taking value 0.3. So the degree of indeterminacy represents the uncertainty associated with the infestation level due to factors such as variation in pest behavior or difficulty in accurately measuring the level of infestation. So if we quickly compare the differences between fuzzy set, inducionistic fuzzy set, and neutrosophic fuzzy set, we already we have seen that mu is present everywhere, membership function is available everywhere. Non-membership function is, it can be calculated in fuzzy set simply by subtracting from 1. But since we have non-membership function well defined here in IFS, so we can determine the degree of hesitation by subtracting from 1 minus degree of membership and degree of non-membership. And similarly in NFS also, non-membership value f is well defined, so degree of indeterminacy can be obtained easily. That is also well defined here. So here we represent by x and mu. Here x, mu, and nu are there. Here t, f, and I are there. And we can use the NFS for inconsistent data as well. That is the added advantage of NFS. So like the usual data representation, your classification, we can classify the neutrosophic data also into two classes, discrete and continuous, depending upon the component I. If I is taking discrete values in the interval, then we tell the neutrosophic data is also discrete in nature. But if I is taking the decimal values, also continuous values, then we say the neutrosophic data is continuous in nature. Again, we can divide the neutrosophic data into quantitative and qualitative also, like the usual data, CRISP data. So if we have the interval 2 and 5 for the I part, then we say it is quantitative in nature. We don't know exactly the value. It is not a CRISP value. But if it is like pink or magenta, we don't know exactly which color it is, then we can say the data is qualitative in nature. Again, now coming to the data representation, usually a neutrosophic statistical number n is represented by d plus I, where d is the determinate part of n and I is the indeterminate part of n. We are not sure about the part I. For example, if we write a is equal to 5 plus I is taking value 0 to 0.4. It is equivalent to saying a is belonging to 5 to 5.4. So for sure, a is greater than or equal to 5. Meaning that the determinate part of A is 5, while the indeterminate part is I is belonging to the range 0 to 0.4. So possibility that A is to be little bigger than 5. So in general, we represent it by A plus BI, where I square will be equal to I and 0 into I equal to 0. That are the conditions. So now, if we talk about the distribution part, for example, if you consider the normal distribution, a random variable x that has a neutrosophic normal distribution is called a neutrosophic normal variable. So the distribution we know for the CRISP data, here we are just adding the superscript, that is n, capital N, to it. Otherwise, it is more or less the same. Mean or variance both could be ambiguous here. So instead of one bell-shaped curve, we may end up with 2 or more bell-shaped curves that are common and uncommon regions between them and are above the x-axis. So here we can see in the first case, left-hand side, mu is fixed, that is crisp, and sigma is in the interval or range. So we have 3 curves. If it would have been the mid value, then the red curve will represent the crisp value. And in the right hand side, mu is also in a range and sigma is also in a range. So we can see that the mean and variance both are shifting with 3 curves. In a similar way, we can go ahead with other distributions by considering one or more distribution parameters by a set or by a range. We can extend it to other distributions as well. So now coming to the hypothesis testing, before the ANOVA, we need how to test the hypothesis. So a neutropsophy hypothesis is defined in a very similar manner to the normal CRISP data hypothesis. So we have there is no much difference, only the representation is NH0 and NHA here, but the decision rules are highly varying. So let us see, let us take an example here. A normally distributed random variable x can be standardized as z is equal to x minus mu by sigma c. So if the neutropsophic null hypothesis about the variable x is, suppose NH0 is equal to NH0 mu belonging to the interval AB, where AB with A less than or equal to B is the hypothesized interval. Now the alternate hypothesis could be mu greater than B, mu less than A, both are one-sided, and mu not belonging to AB. So now the decision rule is that reject NH0 if minimum of Z is greater than Z critical, that is upper tailed test. Maximum of Z is less than minus Z critical, that is the lower tailed test, or reject NH0 if either minimum of Z is greater than Z critical value or maximum of Z is less than minus Z critical value, that's a two-tailed test. So these are the decision rules to be followed. Some related literature I am showing here. So these papers you can, this is a very recent area of development. So we can see papers starting from 2019 onwards. These are some of the papers. This soft computing paper is about NANCOVA, neutropsophic analysis of covariance. We can find papers in split plot designs and RCBD setup, two-way and NANOVA, everything we can see. So some work is already happening. Now coming to, let us take one experimental situation. The for one-way ANOVA situation, neutropsophic analysis of variance, the electric properties of conducting material are studied mostly by analyzing the resistance variation. Generally, it is seen that the change in resistance variation of conducting material depends on temperature variation. So with an increase in temperature, the vibrational motion of the atoms and molecules of conducting material increases, which becomes the reason for electronic and atomic collision. As a result, the resistance of the conducting material increases. Here you can see the setup for the experiment. So here is a heating chamber where the sample is kept. We have a thermometer to adjust the temperature, and here is the LCR meter to give the observations. So for fixed temperature, we are measuring the temperature in a range which is represented here. This is an experimental situation where the neutropsophic data is possible as an outcome. Another situation for a two-way ANOVA situation could be, often it is important to see the effect of many types of veterinary drugs on animals, and sometimes the effect of these drugs differ between male and female. For example, if you would like to see which of the drugs A, B, or C is better to control blood glucose, and would also like to see if these drugs affect males more than females or vice versa. So we could consider a two-way ANOVA situation. And but we know that the glucose itself is not certain for each animal. So to deal with the neutropsophic data, glucose level will range that XL to XU, and ANOVA can be used effectively. So let us consider a hypothetical data and see how the analysis is affecting the actual analysis. If we take the mid values and do the CRISP data analysis in the usual practice, which is being carried out in the usual practice, and if we use the neutropsophic data range values as such and do the analysis, how the inference is getting affected, let us take using a hypothetical data set. So here a sample of 18 diabetic animals were treated with 6 types of medicines, that is A, B, C, D, E, and F. They were divided according to different age groups, or it could be breeds. So for each one, a range of glucose measures was recorded, and which made the measuring more reliable. Now, before going to the ANOVA, we have to carefully observe that the rules to be followed while handling the nutrosophic numbers. There are certain simple rules to be followed for addition, multiplication, subtraction, and division. So suppose N1 is a range data A, B, represented by A and B, and N2 is another range data represented by C and D. So N1 plus N2 is very simple, A plus C, comma, B plus D. That will be the range of N1 plus N2. But when it comes to N1 minus N2, we have to see D is subtracted from A and B is subtracted from C. And this has to be used as the lower and upper bound for the after operation interval. N1 into N2, we have to take all permutations and combinations from the all combinations from two different groups, and minimum of those combinations, those multiplied, those products should be used as lower bound, and maximum of that combination should be used as the upper bound. N1 by N2 is A by D, comma, B by C. So first one is divided by the last one and vice versa. So it's like so that we can ensure the lower bound will be smaller than the upper bound and we will get a range. And root N1 is also having its own normal rule. So now we go to the ANOVA calculation. We have to calculate the grand mean. We have to calculate the correction factor, total sum of square, treatment sum of square, block sum of square, total sum of square, error sum of square, and means everywhere we have to use this summation, addition, multiplication, subtraction, and division only. So nothing else is to be done. And finally, our F values are here, and for F calculation and decision making, we already have well developed rules, so we can follow that rules and we can come to the decision. Here you can see that the treatments as well as the age group, both are treatments are significant, both upper and lower limits, but for the age group it is not significant at 5% level. The decision rule here is if FL is less than F critical value, then reject H0. If upper limit is less than F critical, then do not reject H0. If lower limit is less than F critical and if upper limit is greater than F critical, then the decision is indeterminate decision. So here we have seen that treatments are significantly different and there is no significant difference in glucose between age group. That is the decision taken here. But suppose if we are calculating using the mid values and finally calculating the usual ANOVA, take the mid values and take the calculate the ANOVA, the decision rule here is different. So here we can see that the age groups are also significantly different at 5% level. So this is the danger we are foreseeing if instead of crisp data, instead of interval data, we forcibly use the mid values and do the analysis using crisp data. So the entire inference is changed. This could have happened with the treatments as well. In the particular hypothetical data, it happened with the age groups, but it could have happened with the treatments as well. And we could have given a different interpretation altogether. So to summarize, observations recorded in designed experiments may be nutrosophic in nature and analytical procedures are not well developed for most of the design setup. Before nutrosophic logic, the experimental situation mentioned were solved by ignoring the indeterminacy, taking midpoint of the range, which might have led to wrong decisions. So where are we now? Some very important works are being attempted in CRD setup, RCBD setup, split plot setup, ANOVA methodology. These are already attempted. So there are so much to attempt. So it is a pressing priority to make progress in this very key area of research and very practical area of research, and thus continue to remain useful to the research system. So it could be developed for incomplete block design setup, T designs, resolvable like lattice or alpha design setup, or row column setup. It is totally untouched. So there are generalized row column setup, Sudoku setup, incomplete row column design, incomplete on both sides. So there are designs involving indirect effects like crossover designs, neighbor balance design. There are many more multi-factor experiments like strip plot is untouched, symmetric and asymmetric factorial is untouched, And there is no methodology developed for pooled analysis or combined analysis. MANOVA procedure is not available, and a particular web solution is highly required, or R package is highly required to deal with the analysis very easily. Otherwise, it is a complicated procedure. At each step we have to check for the lower bound and upper bound. Many times we have to interchange them as well. So these are the some of the important references I have used for this particular talk. I invite questions from you all.
Anybody would like to ask anything? But I have seen a couple of papers on that there, because which have shown even in that Journal of Statistical Computation and Simulation. There also, whether they have not mentioned anything about the analysis part. I mean, just theoretical results they have provided.
Yeah, there
so
is
anything is available on the analysis.
Yeah, there is a long way to go. I think only RCBD setup and split plot and ANCOVA is covered till now. ANCOVA is also not beautifully covered. We cannot say every situation of ANCOVA is covered. All other situations are open for research, and but it is fastly developing. So if anybody is planning to do research, you have to do it really fast, because papers are coming up very fast now. But
it started with a paper in Lancet, then end up completely to, I mean, statistical journals. So they are building on theory now, and maybe soon, I mean, it's really a hot area where people should start working on to come up with some analytical tools, because now it's a problem not with the biology or the experimental side, it's a problem for a statistician. So we should start working on it and should come up with some solutions.
Otherwise, we are forcibly using the mid values and doing the analysis. They have done for Butler's test and some other tests also. It is not only design, in all other areas also it is required. It is required to be developed methodology, because the data is never crisp now, any more crisp now. But I'm very sad to see the audience or whatever, means all the 5 presentations or 6 presentations here, they are not actively asking questions. Why it is so, even in online mode, I don't know.
I have a question.
Yeah, sure.
Thank you for an interesting presentation. My question is, do you think that there is crisp data at all in reality? Or do you always have this type of problem in every analysis?
See, I deal with agricultural data, agricultural experimentation data. So there we see often the chances of non-crisp data, we can say, is always there, like range data. Even if we think of some fertilizer dose application, this could be the growth expected. So that may not be the exact growth expected, or any other body weight or anything. It could be in range. So finding crisp data, we are forcibly making the data into crisp form and handling actually. If we allow the agricultural experimenter to measure the data in a range, they'll be more happy. But we don't have an analysis method. So we ask them to get the mid value and we are handling that. Mostly that is the situation. So, but maybe in other situations as well, like I have just shown a physics experiment, we can say, where resistance is being measured, that is in interval. That's a range data. So.
Okay, thank you very much.
Thank you, sir.
Anybody would like to comment on anything? Any questions?
We have 4 minutes left. If some discussion is required, if not on this talk, any of the talk, if anybody wants to ask any question to any of the speakers, please come forward. Otherwise, we can wind up. It's almost a 3-hour long session. If no questions, let me finally thank all the speakers including Aldo, to beautifully introducing Dr. Nair's contribution to us. And yes, we really honor him on this particular day. And we all are some or other way related to his work. We are doing research on his work after nine decades or so. So that is the level of work he has started and opened for us. So similar way, we all have to work really hard to open work for other future generation as well. So very excellent presentations by all the speakers, and I think it will be an eye opener for the students working in this area, if at all anybody is working in design of experiments. So thank you once again, and I again thank the organizers once again.
Thank you, madam, for meticulously conducting this session. I am really thankful to you for agreeing to be a part of this session as a chair. And as I told in the beginning, that I was having that feeling in mind, that because it is this session is exclusively for honoring Professor K.R. Nair, who started the concept of partially balancing on the block design. So most of the presentation should be, or I mean, more or less related to that aspect, and the chair should be a person who has extensively worked in that area. So I'm happy for that. You agreed to be a chair for this session. And even I forgot to mention few things, like you also contributed a lot to the theoretical aspect of partially balancing block design. You also proposed a couple of new association schemes for the construction of design. So that actually that area is still alive. And what Dr. Nair has, Professor Nair has started in 1939, still several people, not only in India and abroad too, a lot of people are working on it. And with regard to this session, particularly the speakers, all, including our Dr. Soman Manna, because if you see in one of the papers, Professor Nair has shown a concurrence with PBIBD with the factorial experiment. So we cannot simply, say a factorial experiment is bit away from PBIBD, or it should be dealt independently. So there is a close linkage that also he has explained in one of his papers. So overall, all the presentations were good, and I deliberately didn't don't wanted to make a presentation, because I want to listen from all my younger colleagues, like Dr. Harun, Dr. Shantini, and Dr. Vinay, including Dr. Soman, what they are doing nowadays, and what is their area of interest, and to make them familiar with and introducing their topics to the scholars there, those who are attending. So with that, I feel it was a great session. Thank you all the speakers, the session chair, and most importantly the organizer and the team leader, Professor C. Satish Kumar, for giving us this chance. Thank you, sir. Thank you so much. Thank you all the speakers and all the listeners, and especially the chair of the session, Madam Dr. Sini Varghese. Thank you all. Thank you all once again.
Thank you all.
Thank you, sir.
Thank you, sir.
In fact, we are very much thankful to you, each one of you, and grateful to you, especially to Professor Aldo Varghese, for organizing a session on design of experiments. Even though Professor D.K. Ghosh also organized a session on the design of experiments, and this session we have devoted for for honoring our great Professor K.R. Nair. In fact, we are your topics are also related to that, and Professor Aldo Varghese has given a outline of or K.R. Nair, about K.R. Nair. We are very much thankful to you for organizing and making this session a very wonderful session. In fact, a day of the design of experiments, 2 sessions mainly on design of experiments. Very good, very good. You are all working hard in a very attractive and vibrant way to the international level. So that I'm very much proud of you people, especially from ICAR, the You are most of them. And, I think one of them, except one of them, all are from ICAR.
Yes, sir. Yes, sir.
Isn't it? I think Thailand from Goa and others from ICAR. So let us give a big clap to each one of the speakers, and and in particular, Professor Eldor Verghese for organizing the session, and Professor Sini Verghese for chairing the session in a very attractive way. So, in fact, thank you so much. Thank you. We are always grateful to you, and we expect your support and these types of deliberations in future also.
Always, sir. Anytime for Kerala.
Yeah. Okay. All. Thank you so much.
Thank you, sir. Thank you all.
Thank you, everyone. Thank you so much. Now let us move to the next session. At 5:20 is the time, in 2 minutes. So this earlier session concluded in time. And next session to chair, I hope Darba Bhattacharya, Dr. Darba Bhattacharya also joined here. We have to check. And speakers, Professor Sarojamma and isn't it?
Yes, sir. Joined, sir.
Yeah, joined. Okay. What about Eliam Mehmet? Professor Dr. Eliam Mehmet is not. Let us remind them once again, and let us start the session without having any delay.
Sir, can I start my session, sir?
Yeah, in just a minute. I have to check whether the chair.
Okay, sir. Okay.
Dr. Darba Bhattacharya is trying to join. There is some network issue. That's why he will join. Hello, Professor Lohmander. How are you, Professor? Fine.
Thank you. I'm fine. We have summer now in Sweden also.
Oh, okay, Professor.
So, in the winter it's cold here, but now it's warm.
Yeah. Okay.
It's very nice to see you.
Nice to see you. Bye. Bhagyalakshmi?
Yes, sir. Yes, sir.
Please introduce the chair and support her to continue the session in a smooth.
Yes, sir. Am I audible?
Audible. Let us start the session.
Hello, everyone. Now we are moving on to the 28th technical session of WSTA 2023, which is a special invited session that shall be chaired by Dr. Darba Bhattacharya. Now, Dr. Darba Bhattacharya is a faculty to the Department of Statistics, St. Xavier's Autonomous College, Kolkata. She obtained her PhD in statistics from Indian Statistical Institute, Kolkata. Her areas of interest include Bayesian non-parametric modeling, statistical genetics, Bayesian computation, biostatistics, multi-objective optimization, and machine learning. She has a lot of publications including effects of gene, environment, and gene-gene interactions in case control studies, a novel Bayesian semi-parametric approach in Brazilian Journal of Publications and Statistics, and hierarchical multi-objective route optimization for solving carpooling problem in Proceedings of the Global AI Congress 2019. Also, she has been an invited speaker for various national and international conferences. With great pleasure and honor that I invite you, ma'am, to chair the session. Over to you, ma'am.
Hello.
Hello, sir. Can you hear me?
Yeah, please.
Yeah. Dr. Dr. B. Sarojamma. Sorry, I had this technical glitch. She will be speaking on small area estimation models under demographic data measured with error. So you may start the presentation, please. Thank you.
Thank you, madam. Madam, is it visible, madam?
Yes, it is visible.
Thank you, madam. Today's topic is small area estimation models under demographic data measured with error. I am Dr. B. Sarojamma, Head Department of Statistics, SU University. Objectives of my present study is we are calculated direct methods for calculating means in small area estimation and different approaches of various methods. And second one is interpretation of missing domain level estimates in different regions across India using auxiliary data. And third objective is assessing an appropriate small area logistic models for calculating proportions for domain having zero sample area sizes. And fourth objective is assessing an appropriate small area using the models of Poisson regressions. And here in this presentation we have 7 subtopics: introduction, review of literature, methodology, data, results, interpretation, and references. First, we are going with the introduction. Small area estimation is a survey sampling technique useful to estimate the population counts for small area or region from the large-scale surveys or census. The data received from SAEs are brought to strengthen from secondary data surveys followed by auxiliary data to obtain reliable estimates. And small area estimates procedures can be used as a ready to fill the gaps between official statistics and local municipalities for data requests for immediate policy making or setting up a business based on population count. The goal of small area estimation is to estimate a parameter with a minimum of standard errors and main summary statistics in the average with MSC, that is mean square error values. Small area estimation or statistics is a widely used technology in survey modeling due to the growing demand from reliable small area estimates from public and private sectors to find spatial segmentation and obtain domains, subdomains, regions, or national level estimates. And why small area estimates are required is the reason for using SAE methods is due to the poor performance of traditional population sample surveys designed for national estimate that did not provide large enough samples to produce reliable estimates for small areas. And second reason is the reason behind the evaluation of SAE is the policy decisions, funding allocation, and intervention of often depend on the measurable requirements. Where small area estimations are required is demographic events geostatistical events, epidemiology events, business, property events, and agriculture sectors, and examining the criminal records to produce reliable estimates and picture analysis. Next thing is review of literature. The small area models are generally has two types of cases, that is general linear models and regression based models. Small area models are first evaluated by Harvard Thompson estimator and then used ratio estimator, that is they are also called design-based models. The design-based models combined with weights, then it from generalized regression estimates is also called model assessed estimators. Further, generalized regression estimator was linked with auxiliary data to form a regression synthetic estimator. Later, the synthetic regression estimator was used in unit-based and area-based model for further research. The below flowchart gives brief note about the small area estimation methods. The small area estimation method, Rao and Villari in 2015, has divided into the two groups. One is direct method and second one is indirect method.
Excuse me, ma'am. Are you changing the slides?
Yes, madam.
Yeah, I can't see the slides changing.
Okay, madam. I will once again show you, madam. Madam, is it visible now, madam?
No, ma'am, it's not visible.
1 second.
I can't see. I'm not sure if others can see it.
No, not visible.
Madam, is it visible, madam?
No, it's coming.
It's coming. It's coming. Yes, the flowchart is visible now.
Madam, if I go for the slideshow, it is not visible to you, madam.
Yeah,
Can I
then,
go
you can
like
skip
this
the
only? No
slideshow.
problem.
Yes, you can skip the slideshow. You can do it, ma'am.
Okay, madam. Now, small area based estimation is divided into two groups. One is area level estimation and the second one is unit level estimation, which having area level estimation is again having direct and indirect methods, and unit level estimation is also direct and indirect methods. And indirect method having univariate fly-ferret model from 1979, and it having the software packages in R with SAE, SMAE, and SAERE, and all these things. And this univariate model is again divided into two types, with unweighted least square approach and approximation of second order MSE, and third one is robust small area estimation in overview. And another is univariate is having the univariated least square approach, approximation of second order, and robust small area, whereas multivariate is having the sub-area level models and an adjusted maximum likelihood method for the Far-Hertz small area models, and software of SAE, MSAE packages in R is available. Whereas univariate level estimation direct model having the SAE of proportion is in business surveys, and indirect having the nested error component model and domain level as an unit level model, and two level models EBL UP using survey weights. And these indirect levels is upon divided into three groups, which is spiritual EBUL models and M quantile method and empirical Bayes methods. Next is it having procedure of SAE is we have to first define the variable of interest. After that, we have to define the small area of interest, and then accrue auxiliary data. After that, we have to select sampling design scheme, and after that, select SAE technique. What is the methodology we are using is for first object 1, the study aimed to evaluate reliable small area direct method estimates and compared with direct estimates. In this chapter, it contains information regarding direct methods of calculating means in small area estimation and different approaches for variance method. And data gathering, management, and analysis using R for Harvey-Thompson estimator with its interpretation is second step. Third step is producing state-level fact sheets for mean age at marriage, mean age at first birth, and represented in error bars using ggplot package. Fourth step is producing district-level fact sheets for mean age at marriage, mean age at first birth, and plotting that estimates on map using ggplot package. Why we choose small area direct method is, in general, the direct estimation parameters for survey data has larger variance for small domains. In large picture, if the standard error is above 20%, then the results may be misleading and the interpretations are not possible. While we're using small area direct Harvey-Thompson method estimator and combines with weight, it will increase granularity. Further, these direct estimators are also used in the indirect method of small area estimation, both in unit level and area level models. And this is an Harvey-Thompson method, and the variance and if the I is the direct number of units in the sample, the Harvey-Thompson estimated does not depend upon the number of times a unit may be supplied. Each distinct unit of the sample is utilized only once, and the variance of that Harvey-Thompson method is listed here as variance of y cap is equal to 1 by n square summation j is equal to 1 to n summation k is equal to 1 to n pi I comma k minus pi I pi k by yi divided by pi I yk divided by pi k. And small area methods can be adaptable taking amount of secondary data. We now consider we are taken data from National Family and Household Survey data sets. And state level, we are collected married women data from 15 to 49 years. That data set is formed in the SPSS, and we imported that data set into R by using foreign languages. Then we clean the data set with PLYR and DPLYR and all these packages. Next, we go through insights and did glimpse and summary statistics. Then we choose the variable for our concern to fulfill the objective. Further, we create data frame for states with respondent age at marriage and respondent age at first birth. And we are denoted with variable 118 and variable 121 from women data set. Here, we include districts in the states to get output. Later, we calculate sample weights using survey data and samples they chosen from state population in this data set. The weight they choose is around 1%. Further, we make a data frame with response vectors using age at marriage, age at first birth, sample weight. We adapt Harvard-Thompson direct method of estimation to calculate mean age at marriage and mean age at first birth with respect to variances. Finally, we create an error bars for the state level means and variances using ggplot2 package. District level, we are like state level data management process. We choose individual districts in that states. We consider the required accept and do summary statistics gives. Further, we create a data frame for individual districts with respect to states, correspondent age at marriage, and respondent age at birth from married women's data test. We are calculated sample weights using survey data and samples they had chosen from state population. In this data set, the weight chosen is around 1%. Further, we make a data frame with response vector for district and state. We adopt the Harvard-Thompson direct method for district level also. Finally, we gone for plot by using ggplot2 package. And this is the results according to districts, according to states for mean age at marriage, variance, mean age at first birth, and variances are listed here. For each and every state in India, Jammu Kashmir to all the states. Jammu Kashmir, Himachal Pradesh, Punjab, Chhattisgarh, Bihar, Meghalaya, Assam, and it continues with West Bengal, Maharashtra, Kerala, Tamil Nadu, all these things. Next, mean age at marriage, we use Harvard-Thompson estimator, variance estimator to calculate means and variances for our variable interest. The above shows explained that early marriages were taken place in India are at Rajasthan, Uttar Pradesh, Madhya Pradesh, Bihar, and mean age of these states are in between 15 to 16 years. Around 15 to 16 years, these states are getting the, women are getting the marriage. Here, the variances for these states have not much differ within that regions. This shows that the data are more tightly grouped around the average. Mean age at first birth. In another context, the late marriages are taken place in Goa, Manipur, Pondicherry, Kerala, and mean age of marriages are 20 to 22 years. Here the variance for this not much differ within that region. This shows that the data are more tightly grouped around the average. And on an average, the West Bengal, Bihar, Rajasthan, Uttar Pradesh, Chhattisgarh, and Andhra Pradesh, women are getting marriage in between 18 to 20 years. Here, the variances for these states have not much differ within that region. This shows that the data are more tightly grouped. And this is the flow chart, bar chart for the errors. In the above bar chart, age at first birth in Goa and compared to other states, it shows most of the data collected are significantly different from other regions. The early varying started in state of Andhra Pradesh. This shows Most of data in this region are differ from another, but it is inconclusive. Session, we would look explain about the district level patient using high-confidence direct estimates, state maps using shape. And here also we are taken the variables and we are considering here this district level respondents of respondent age at marriage and respondent age at first birth from married women data set. And here also we are taking in this data set the weights they chosen is around 1% only, and Harvey-Thompson direct method for estimation to calculate mean age at marriage and mean age at first birth with respect to variances, and plots are produced by using the ggplot 2. Here, for district level mapping of means in states, we use mapping to visualize district level means for the particular state. In that context, we would like to show India map for mean age at marriage, early marriage district, and late marriage district. And here we are shown the India map with years of age marriage in between 15 to 16 years and 17 to 18 years is with green, and blue with 19 to 20, and with purple color is 21 to 22 years. Next objective is to study seeks to find out the demographic factors like mean age at marriage and first birth for particular region having unsampled domain with the combination of auxiliary data. In this chapter, information regarding indirect method of estimating means in small area estimation.
Excuse
and
me,
also finding
another 3 to 4 minutes. Yeah, thank you.
Okay, madam, I will conclude. And here, in this method, we are computing and we are using here estimation method. And here we are using 500 model method for indirect estimation methods, and data we are collected is for different districts is as follows. And auxiliary information for female literacy rate, mean average at is 0.42 and poverty rate is minus 0.2 and mean age at first birth is 0.7 and for incidence poverty rate is 0.05 and per capita income for mean age at women is 0.07 and mean age at first birth is 0.2. Synthetic dataset creations, and we are using R language for SMAE method. Here it generates the results for mean age of marriage and birth and variance and female literacy rate and poverty rate and square error for female literacy rate and mean square error for per capita income is listed here. And here the results mean at age for death. Here, for different models, number is representation and HT is Harvey-Thompson direct survey method and A is mean age at marriage with first birth with female literacy rate. Like that, we are distinguished G categories, and it is noted in the table form. Different area. And this is the plot for the error plots for mean age at marriage with respect to female literacy rate, incidence of poverty rate, and per capita income. Mean age at first birth for different areas for A to G category is listed here, and graph for the mean age at first birth with respect to female literacy rate, incidence of poverty rate, and per capita income is listed here. And this is objective 3. By using the Poisson regression model, we are estimated small area estimations. Logistic regression is also used. For the different domains, we are estimated direct estimated marital mortality rates, coding according to national estimates, and logistic regression estimating codings, and predictor proportions and standard errors are listed here. For different domains, here the Poisson regression estimates were listed out. Why we need estimation methods? Sample size is less than 100. We will go with small area estimation methods, and these are the appropriate methods. If you take the sample size less than 100. Here we are given the conclusions. Small area estimation handles perfect for planned and unplanned domain data. The direct estimates are constructed based on the survey data and design weights for the area of estimates. If the sizes are too finite, this leads to huge variability, whereas in small area estimates uses direct and auxiliary data, they will produce better estimate even for too finite to interpret. Small area can deal the problem that the area are not compatible due to zero sample sizes. Small area estimates helps us dealing problems like sampled areas having are determined, unsampled domains information both for planned and unplanned. Yes, these are some of the references we are used for this paper writing. Thank you.
Thank you, Dr. Saroja. So we can take one or two questions.
There is a typographical error, that is the estimated age at marriage in Kerala. It was given as 205, might be 20.5.
No, madam, that is a mistake. 20.5, madam.
I think so.
It is a typing mistake.
Right, yeah.
So, if there aren't any more questions, I would like to just ask this, that what is the source of the data which you have used?
We are collected data from secondary data, madam.
So from which database?
1 second, madam.
It's okay, madam. You can later write in the chat box. Yeah, you can write in the chat box.
Okay, I will send the chat box.
Thank you. Thank you so much. Thank you.
Okay.
Our next speaker is Dr. Aliama Matthew. She is Professor and Head Division of Cancer Epidemiology and Biostatistics, Regional Cancer Research Center, Trivandrum. She has 32 years of experience in the field of cancer epidemiology and biostatistics. And she will be presenting on application of autoregressive integrated moving average modeling for forecasting cancer incidence. You may start now.
My topic is not autoregressive moving average forecasting cancer incidence. My today's topic is forecasting lung cancer incidence in India. Is it visible?
Yeah.
Yes, it is visible.
Okay. So, lung cancer incidence, in fact, cancer data we obtain from population-based cancer registry. In India, there are, this program started in 1982. When it started, there were only 3 cancer registries. At present, more than nearly, I think 38 cancer registries, population-based cancer registries, covering cancer patient information from the respective area, not hospital-based. This is area-based cancer registry data. In fact, this area-based cancer registry data, the case ascertainment method is in a cancer registry, we collect the cancer data from the various hospitals. There are 28 RCCs, regional cancer centers in India. Other than from these cancer registry, these regional cancer centers, we collect data from the respective medical college hospitals, radiotherapy centers, private hospitals where cancer patient treatment is managed, and pathology departments, other government hospitals. From all these sources, we collect cancer cases, and then one patient, it is generally one patient may go to multiple hospitals. So there will be, when we collect data from all hospitals, several information we get, but multiple patients may go to multiple hospitals. So duplicate cases are recorded. So we eliminate these duplicates, and after eliminating all these duplicates, we estimate the cancer incidence and mortality rates in the respective areas. So in fact, population-based cancer registry, this is the case ascertainment method to give you an awareness about the case ascertainment method in a population-based cancer registry. So in fact, I will presently talk about the lung cancer. In lung cancer is in 1990, lung cancer, that was the leading cancer. Now also lung cancer is the leading cancer among males. And in females, we can see that in 2020, 2% lung cancer, and slightly the percentage increase lung cancer among females. This is females. Males, not very high increase, but in females, this lung cancer is proportion, this 3% proportion means it is thousands of cancer cases increased at present.
And the various cancer registries I have shown earlier slides, I have shown that there are 38 cancer registries in various parts of the country. In the north, at present Delhi, Patiala, in south Kerala, then Hyderabad, Bangalore, Chennai. So we can see that in all these areas, lung cancer is the predominant cancer site. So among males, so 1, 2, 3 rank that if it is not first leading cancer, it comes as a second leading cancer in most of the regions in India. In females, in fact, it comes as the first within 10 leading cancer sites. So we can see that this is the crude and age standardized incidence rates. Crude means age is not considered. Here, we know that different states have different age structure. So in Kerala, the life expectancy is highest in the country. So age is a confounding factor for estimating the cancer incidence rate. So then to assess the real incidence rates in various parts of the country, I mean to compare the cancer incidence in various parts of the country, we use age standardized incidence rate, a standard population. World standard, this crude incidence rate, age specific incidence rate is compared with the world standard population, and that is the way we standardize the rates and estimate the age standardized incidence rates. And this is the various regions: northeast, south, east, north, central, and west. Various cancer registries. We can see that in northeast area, and of course in Kolkata, including in northeast area, this is the incidence rate. We can see that highest in northeast area among males, as well as in females also in northeast area. This is a common cancer. Surprisingly, we can see that in south also this is the commonest cancer, even though the tobacco prevalence is slightly lower in southern states, but still lung cancer incidence is slightly second. It comes second after in northeast areas. And that is we can see that these rates are female rates. Then this is the age-specific incidence rate. In each age group, cancer incidence rates are calculated. That is total number of cases in each age group divided by the population in the respective area. So we can see that this is among the age-specific rates among males. So the rates are, the peak incidence rates comes in 60 to 65 to 74 years, and that is almost similar in all the regions in India. This is the age-specific incidence rate among females. So this we have observed that slightly younger age predominance in among females, the age-specific incidence rates. So the various regions are, we have grouped north, south, west, central, northeast, and east. This is the way we check the rates in the various parts of the country. So coming to the cancer registry program in Kerala, in fact, RCC Trivandrum, we provide reliable and high quality cancer data through hospital and population-based cancer registries. These programs, in fact, play an essential role in the healthcare programs healthcare programs of national and state cancer control activities. The cancer registry is working in RCC, hospital-based cancer registry, started in 1982 under the National Cancer Registry Program of Government of India, ICMR, and then these Thiruvananthapuram district, Kollam district, Palappuzha, Pathanamthitta district, and Kottayam district. These are our population-based cancer registry. So population-based cancer registry, what I have already mentioned that the data is not from the hospital cancer-based registry, not only from the RCC, from all the hospitals located in these districts, as well as from several other major hospitals where cancer patients go for treatment from these regions. Then only we obtain complete cancer data in these defined region. So these are the 5 districts. In fact, this Kottayam district we started only in 2021. In Thiruvananthapuram and Kollam district program started in 2006 onwards. Alappuzha, and we require a lot of funding support for doing this work. So in fact, all these programs, funding support we obtain from the Government of India through ICMR. So we can see that the leading cancer in South Kerala, of course, lung cancer is the leading cancer, and in Thiruvananthapuram, Kollam, Alappuzha and Pathanamthitta districts, lung cancer slightly higher. In fact, we have noticed slightly the crude rate, CR is crude rate and ASR is age standardized rate. I have already mentioned the difference between crude and age standardized rate. We can see that in Kerala, this is one of the observation we have noticed that in Kerala the crude rate is higher than the age standardized rate because our life expectancy is higher, the highest in the country. That is why where it is compared, if it is higher than the national average, or always crude rate will be higher. This is the real magnitude of our disease problem. So then crude rate, it is in Alappuzha, the highest noticed. Alappuzha and Pathanamthitta district cancer registry program only started in 2-3 years ago. So that is the reason, that might be the reason we need to at least 5 years is required to get a stable data. So otherwise, this Kollam district data, these 2 district data are much more reliable, and incidence rate, this is mainly urban population, and this is mainly rural population. So this disease is higher in rural population than urban population. And among females also, this is not first leading cancer. Of course, breast cancer is the leading cancer. In Thiruvananthapuram, this is 7th leading cancer. In Kollam, it is among females 8th leading cancer. In Alappuzha, it is 5th leading cancer. And in Pathanamthitta district, it is 9th leading cancer. So when we all know that tobacco use is the common risk factor associated with the development of this disease. So then region-wise tobacco use, using these cards to survey data, we have observed that the highest, as expected, highest incident prevalence is in Northeast region. But lung cancer incidence in South, we have observed incidence rates are high, but tobacco prevalence is not as high as we noticed in Northeast region. Then, so Northeast region, these are we can see that it is prevalence is, this is tobacco use percentage, prevalence is more than 30%. So this is our RCC data. We can see that 80th lung cancer prevalence of habits among lung cancer cases. It is we can see that nearly 84% of lung cancer cases smoking. Females, it is very low. Chewing also another, and alcohol consumption 53%, and many people have both smoking and alcohol consumption. So then, in fact, this is another point which we have noticed. Tobacco prevalence is declining, but lung cancer incidence is not that much declining. So this is among females. It is, we have noticed. That is why we have been continuously assessing this cancer registry data. So we need this kind of information. We will get a lot of clue for generating hypothesis. Another point which we have noticed, this is by type of histology, that is microscopic diagnosis. This cancer, adenocarcinoma, this is much more common among females than this squamous cell carcinoma. In fact, studies have shown that squamous cell carcinoma are more associated with the lung cancer. The tobacco prevalence is more than that. Could be the reason. This prevalence is higher among males, but whereas among females, the adenocarcinomas are common. And this is the clinical extent, that is stage at a diagnosis. This disease is almost very less proportion of cases are detected in the localized stage, that is at the early stage. The disease, when it is spread to neighboring organ or distant organ, at that time only this disease is diagnosed mostly. Then we have observed that educational status it is in fact we have taken a bivariate table, education and this lung cancer proportion. This is quite common among illiterate and literate group. And we have, this is, in fact, you can see that this is Trivandrum data, Trivandrum district data, education versus stage at diagnosis, or no difference by education. And this is the survival data. So even if it is detected in early stage, it doesn't benefit, the survival is not, there no significant difference in survival. So that is the pathetic part of this disease. Then coming to the topic, statistical models for forecasting lung cancer incidence. So there are several techniques. Commonly used technique is regression models, that is linear regression and joint point regression, and another time series models are also commonly used. These various techniques, exponential smoothing method, ARIMA and ARIMAX method, these are used. Linear regression model, we know that this is the cancer incidence rate is considered as the outcome variable or response variable, and calendar time is considered as the independent variable. And then since cancer is a rare disease, in fact, so we transform into logarithmic logarithm, and the cancer incidence log linear regression model is estimated. Another model, joint point regression model, that is again to identify the changes of cancer incidence by connecting series of joined straight lines over time periods. Here also we assume linearity between each time point. So this is the model, beta 1, beta 0, beta 1, gamma 1, gamma 2, gamma n are regression coefficients where the k is equal to 1, 2, 3 up to n. And here also this there is a program, and this Kim et al. Developed a software, and using that software we can identify the join points and annual percent change. So in the previous model also, we calculate the annual percent change in the entire time period. Here, annual percent change in each time point, each join point are calculated, estimated. Then coming to the time series model, exponential smoothing, it is again assigning an exponential decreasing weights for previous values. There are mainly single, double and triple exponential smoothing. In fact, single means here trend and seasonal patterns are absent. Double means trend is there, but seasonal pattern is absent. In fact, for forecasting cancer incidence, seasonal pattern is not considered. Triple means when both all the three, trend and the seasonal pattern are considered. Then in such situation, we use triple exponential smoothing method. So this is the single exponential smoothing method. As I mentioned, exponential decreasing weights. Here, forecast equation and smoothing equation both are same. That means here trend and seasonality are absent. These parameters are estimated using this sum of squared errors method. Then double exponential smoothing model is here incidence rate with the time period are represented both the forecast equation and the smoothing equation, and there are 4 different models can be used, linear or exponential model. In linear trend model, this is the linear trend model, forecast equation and smoothing equation. This is damped linear model, trend model. Here error is also considered. That then exponential trend model, this is the exponential trend model, and damped exponential trend model. Here also these values are used, the estimated, this same sum of squares of errors. Then coming to the autoregressive integrated moving average, ARIMA, it is a linear combination of past values, that is autoregressive values, and previous errors moving average values along with the difference for non-stationarity data. And this is the equation for ARIMA, where phi b is equal to this and theta b is equal to this. Here b is backshift operator, and then here this estimates are parameters are estimated using maximum likelihood method. Then these are the various the statistical tests which we use for normality, homogeneity, and autocorrelation. So, and then we use maximum mean absolute error, mean absolute percentage error, and root mean square error. Based on these values, we choose the best predicted model. So, in fact, using this simple linear regression model, this is a national program. We have this data is obtained from the national report, annual percent APC. Simply, they used log linear model and average percent change values. You have estimated various registries. We can see that this value, it is very high, everywhere it is positive value, which shows that this disease is increasing everywhere. 7.2 is highest in Kamrup urban, means it is in Assam. And similarly, in females also, this in fact, these annual percentage change values are higher among females. On the basis of that APC values, they have forecasted these lung cancer incidence, number of lung cancer cases, and this 5-year period compared to in 2016, it is observed that 25% decrease. This is the value. This we have taken from their report, National Cancer NCRP of ICMR report. We have taken this 25% increase among males and slightly higher proportion of increase among females. This forecasting is on the basis of the log linear regression model. So we have, and this forecasting is the age-specific incidence rates forecasted for the year. This publication is taken from Nath et al. 2022. In Thiruvananthapuram, using this lung cancer, we have data, as I have already mentioned, from 2005 to 20, this 16-year data. Using this 15-year data, we checked this normality, homogeneity of variance, and autocorrelation, and we have observed normality assumption satisfied. And this is, in fact, more details I have provided here. This is one of my students' PhD work. He is working on it. Just I will show you the clippings of a few results. Then this here we have checked normality assumption and homogeneity of variance. It is satisfied. And then autocorrelation, no autocorrelation observed. And these various MAE and mean absolute error, mean absolute percentage error, and root mean square error. Here we can see that these MAE, MAPE and the least value was observed for joint point regression model with 2 joint points. We can choose several of each model. We can choose 2 or 2, 3. Likewise, we can choose. Here it is observed. The least value was observed for these 2 joint points. Joint point regression model with 2 joint points. And this is the forecast incidence rate. This is the 2015-5 incidence rate was 13.3 per males per 100,000 males, and in 2020 this is the rate. And using this observed data, we have used 4 different models, and this is the best model, joint point regression model with 2 joint points. We have already seen the least error was observed, and then here see this difference 39, the least value. If we have used this log linear model, then there is in fact 39 here, least value was 29. So in fact in forecasting will be underestimated, would have been underestimated. So in this presentation, what I wanted to, the key information is we have to check the assumption, whether it assumption satisfy, and the appropriate model needs to be checked. So these are the references we have used for making this presentation. Thank you. I thank Professor Satish Kumar for inviting me for this presentation. Thank you.
Thank you, Dr. Matthew. It was a wonderful presentation. So if there are questions, we can take 1 or 2 questions. Professor Jose, are you saying something?
I'm ready. I am ready. Yes, I am ready. Hello, you can hear me? Professor Jose.
Yes, sir. Yes, sir. We can hear you.
Hello, Dr. Satish.
Satish sir, I can't hear you.
Sorry. So, in fact, I mentioned about you. You are asking whether Professor Jose has some questions or anything like that. So
Yes, sir.
But in the next session, he has to chair. Before that.
Okay.
He was a student. Professor Eliam is also a student of, isn't it, Professor Jose?
Yes, I have heard the topic by the discussion by Dr. Eliama, and that is on epidemiology and statistical work they are doing in RCC, Trivandrum. So it was very informative.
Okay, let us conclude this session.
Thank you, sir.
Thank you. Thank you, sir.
In fact, we are very much grateful to you. Yeah.
Thank you.
Professor Eliam Matthew and Professor Sarojamma for your excellent presentations. And also, we are grateful to you, Professor Darba Bhattacharya, for nicely chair the session and concluded in time. Thank you so much.
Thank you to the speakers. Thank you, Satish sir.
Thanks, sir. Thank you, madam. Now let us move to the next session. Now it is 5:20, 6:20. Oh, sorry, 6:30 is there is time.
Yes.
Yeah. No problem. let us have some more time. What about the speakers of the session, whether they joined or not? I have to check. Professor Indranil Ghosh and Professor Sushmita Datta, whether they have joined or not, because
they have not yet.
they are not there outside. So the timing. Yeah, Professor Indranil Ghosh has already joined. I hope so.
Professor Indranil has joined.
Yeah. Okay, Professor, welcome.
Good evening, Professor Kumar and Professor Ursi. Thank you for the invitation. And
thank you.
And can I?
You're most welcome. In fact, before starting this session, we have to just 2-3 minutes. We have to wait because some people may wait for the particular sessions or try to join for particular sessions. So just wait. Yeah, please.
Professor Kumar, can I quickly check if I can share the slides properly?
Okay.
Let me try. So this is the present.
Yeah.
Oh, okay. Okay. Is it visible, Professor Kumar?
Yeah, it's visible. It's fine. I hope it is whether is it possible to enlarge?
Oh, okay. Let me see.
It is okay, but if possible.
Okay. How can I make this large?
There is some. Yeah, there is a sign. Zoom out.
Oh, full screen.
Yeah, full screen.
Is it better now?
Not much change. Slightly once again. Sometimes that button will not work.
Okay. Somehow it's I cannot move from one to the other. But let me.
Yeah, no problem. There is a zoom out and zoom in, but whether it is working or not, that's what. In the upper line, there is.
Okay. But the only thing is I cannot move with this.
Okay. Okay. The movement will become difficult in that case. Then it's okay. We can move with this one.
Let me again refresh it and see.
Yeah, that's fine.
Window. Let me see. Is it fine, Professor?
No, it is fine.
Yeah. It's okay. It's not much change, but it is okay.
But the only thing is, it seems like I cannot move from
okay
slides to the other.
Yeah, this is.
I don't know why.
The scrolling button, you are using the scrolling, that isn't it? Oh. Probably.
I'm trying to figure out this.
Oh, it's okay. Don't worry. It's okay. Now let us. Yeah.
If I cannot move, then it's a problem.
Okay.
Let me.
It can be reading. It's used not
Yeah.
much difficult to read.
I'm just trying to share the tab. Audio enters.
Hi, Indranil, how are you?
Hi, Professor Sengupta. I'm doing fine. How are you?
Okay, good to see you.
Good to see you virtually as well.
Yeah, so we had a problem here. There's a lot of rain going on in Calcutta right now.
Oh.
So now we lost the connection. So I was
okay.
scared that I'll miss your talk.
Connection, okay.
Yeah, but now it has come back. I was worried that I'll miss Indranil's talk. I didn't want to do that. So it has come back, fortunately.
Okay, well, it is a pleasure that you are interested in my talk.
Oh, no, that's good. Looking forward.
And sorry, Professor Kumar, I have friends that came up in my place, so I may not be able to join in the period of time. I have to take care of.
It's great.
It's a long weekend, isn't it? 4th of July weekend.
Yeah,
yes.
Let us start the session. You can, Sabna, please introduce the chair.
Professor Kumar, I mean, is it fine? I can scroll them.
Yeah. That's fine,
okay.
Okay,
okay.
It's okay, bro.
Okay. Right.
Sabna, please introduce the chair and do the needful for helping this chair to proceed the sessions.
Sure. Sir, am I audible?
Yeah, audible.
Hello, everyone. We are moving on to the 29th technical session of WSTA 2023, which is a special invited session that shall be chaired by Professor K.K. Jose. Now, Professor K.K. Jose is a faculty at the School of Mathematics and Statistics and Data Analytics at Mahatma Gandhi University, Kottayam. Dr. Jose is an elected member of the International Statistical Institute, Netherlands, and a fellow of the Royal Statistics Society, UK. Dr. Jose is an eminent academician who had rendered more than 40 years of meritorious service as a reputed principal, professor, and head to the department, teacher, researcher, and organizer. His areas of interest include statistical modeling, stochastic process, time series modeling, and so on. Dr. Jose has successfully guided more than 25 research scholars in their PhD work and published more than 50 research papers in reputed national and international journals. He is a member of various professional societies and had been an organizing secretary for international conferences and workshops in connection with the annual conference of Indian Society for Probability and Statistics, etc. We are fortunate to have such an eminent person with us sharing the session today. Without delaying you further, I once again extend a warm welcome to you on behalf of the organizing committee and kindly request you to take over the session. Over to you, sir.
Okay, thank you very much for the nice introduction. So I am extremely thankful to Professor Satish Kumar, the chief organizer of this IWSTA. And today, so in this session, we are having two eminent speakers. One is the first speaker is Professor Indranil Ghosh, then the second speaker is Professor Susmita Datta. And regarding Professor Indranil Ghosh, he is a full professor of statistics in the University of North Carolina, Wilmington, United States. And he had his research from University of California, Riverside, then University of Calcutta. And his areas of research are wide: statistical analysis, statistical modeling, and he is very much interested in developing new families of discrete and continuous distributions and their applications and their inference, especially using hidden truncation models, then compatible conditional distributions, etc. And he is also an expert in R programming also. So today he will be talking on a new class of discrete distributions arising as an analog of gamma Lomax distribution and its properties and applications. I request Professor Indranil Ghosh to deliver the talk. Sir.
Thank you, Professor.
Professor Ghosh.
Thank you, Professor Kumar, for inviting me for this wonderful conference online. And I also want to thank all the members of the organizing committee of this wonderful conference. I think since 2020 December, I became a part of this different initiatives by your institution. And I very much look forward to visiting in person in Kerala. I mean, if I get a chance, it's a wonderful place, I know, and I'm not only me, but I am compelled to say that my wife is also looking forward to visit Kerala. And I hope to engage in collaboration within my expertise if I can be. Today, I'm going to talk about a new class of discrete distribution arising as a sort of continuous analog of gamma-Lomax distribution. So this is a joint work with two of my collaborators, Ayman and Hamedani Gigi, and this has been published as a book chapter in G Families of Distribution, a book edited by Professor Ali. There are actually two Alis, MM Ali, Irfan Ali, and Haitham Yusuf, and another editor. I can't recall right now his name. So the purpose, I mean, in terms of motivation, well, I must say that because I also work in distribution theory area, these days probably based on my experience on reviewing many journal articles, that almost on a daily basis a new distribution comes in the continuous domain with some structural properties. Sometimes they may appear mundane in nature, and as my thesis advisor, Professor Arnold, Dr. Arnold would say that, well, sometimes they came up with some cooked up data sets to show that the model is really good. So that should not be the case. Ideally, we should look for a scenario, and then we can think of whether there is a need in the existing literature for a new distribution. So when we started with this, so that's the outline of my talk with why we get into this discrete version of gamma Lomax distribution. And by the way, Lomax is alternatively or equivalently or better known as Pareto type 2. So it is in the big Pareto family of 4 distributions, Pareto type 4 being the big umbrella. So Pareto type 2 is a particular case of Pareto type 4. And then I'll talk about some structural properties which might be interesting to some of you. And then, of course, the major motivation that we got is in the context of modeling certain types of industrial strike data. And then I will wrap up my talk with some concluding remarks. Now, so as I was mentioning earlier, when we first submitted this article, it's not much of motivation. The big question that was sent to us that why you need this? I mean, there is a bunch of other distributions. This is like a usual strategy. So we are not inventing a brand new line of theory to generate a new continuous or a discrete distribution, so to say. So then I looked at different articles, journal papers, and other works that might have some resemblance with the work that we are thinking. And with the result, I mean, of course, it is the references that I got is in the public domain these days. So it is particularly in the UK, United Kingdom, on different types of strike data, and people who are very much aware of this knowledge of how strike could be difficult and undaunting. There was a coal mining industry strike strike. That incident happened. It was a big thing at that time when I think Margaret Thatcher was the prime minister. And then, well, I'm not getting into the political debates now, but just trying to, give you a scenario, I mean, in terms of what was the reason. So there were not only on the coal mining industry, but there were several other industries that Britain has suffered from time to time with strikes. Now, one argument could be that, well, in most of the cases, we depend on the past data. based on statistical methodology, we try to predict the future. So, and these are effectively time-dependent data. So, why you are so much into this coming off with a new distribution with some properties? So there were several earlier research work that has discussed, explored on the different aspect of this strike data. There was the work of Bach in 1984 that looked at the strike frequency in Great Britain. There were works of Belden and Stills and McGrath, Enley, and so on. Now, what those researchers have done, they focused mostly on establishing a regression type modeling in search for a causal relation. Now, of course, strike data is not just dependent on only one factor. So there is a combination of categorical explanatory variables, quantitative explanatory variables, and so on. So that part has been done. So what else we can do? So what we looked at carefully is that very few of these models search for an appropriate discrete probability model that might discuss the behavior and pattern. Now, when I say behavior and pattern, mostly I am only interested with the distributional side aspect, is that can this be well fitted, this phenomena, by a discrete version. So, of course, we only look at the number of strikes that has happened. And that is the reason, and it's count data. Yeah, I mean, of course, if it is infinite, then it will be trouble. So it's countably finite data. So it belongs to our discrete modeling. Now, that was the one reason, or I would say a compelling reason to find some support in terms of this new discrete probability model. Now comes the situation, why this particular discrete model? Now, what we know, of course, from distribution theory, that Poisson distribution is useful for modeling rare events. Now, strike data, or the number of strikes, one might argue that, well, this doesn't happen quite often. I mean, if it happens like a regular pattern, then it's a doomsday for any industry or any community or any country in a larger perspective. But when we looked at the based on the public domain available data, and also I was reading some of these old news articles on The Guardian, the leading newspaper, there was situations that they talked about at great length on this strike data. So it was not like a really small event to say, but it is not that a regular pattern. So we only focused on how we can create and that with a discrete probability model. So now the situation is that, well, according to Hedge and his co-authors, there are several situations in which modeling extreme value events. Now, extreme values, extreme events like earthquake, flood, I mean, these are not like happening quite regularly. These are extreme events. Now, even to some extent, one might say that these are, I mean, if the strike, if it is happening for a really great length of time over a even a short period, I mean, intensity, then it's definitely an extreme scenario, because it's like creating a lot of trouble. But then how do we appropriately model that? So what we found that in most of the cases, in the univariate case in particular, an approach that often works quite well is to model observation above a large threshold with a parametric family of distributions for count data. And the limiting distribution appears to behave like a generalized Pareto. So that was another thing, that, okay, if the limiting behavior is like a generalized Pareto, can we come up with a discrete probability model that would consider a Pareto as it inside? So This was done for the continuous, but then not much has been done on the discrete. So we conjecture in the beginning that, well, we assume that such type of data could be reasonably modeled with a discrete Lomax or Pareto type 2 distribution. And maybe one can study the asymptotic behavior to now, it will be useful for even income modeling, of course, if the data is, which is cross-sectional over time, involves a mixture of discrete and continuous. And for the discrete portion, this our proposal discrete model, discrete gamma Lomax distribution, in short DGLD, developed in this article, may be a natural candidate distribution. Now, the main objective of this article is to establish that the industrial strike data from various domains, so not only the coal mining, from transport industry, from another particular section of the industry, they can be well modeled with this distribution. Now, of course, we haven't explored in all types of industrial strike data for not only, I mean, for UK, but maybe for others, South Asian countries, or even in the United States or something. We only focus on that to justify. So there are a lot of room for improvement, I would say. There are a lot of open questions that you might have. But this is, at least, we found that something to say in terms of as a supporting point to explore this new discrete model. And of course, the editors and reviewer were happy with this motivation. So the idea was like this. So if fx be the CDF for a random variable, and small ft be the probability density function of a random variable r, they're both, that R is defined on the positive part of the real line, then the CDF of a gamma generated gamma x is the gamma is the baseline distribution, and x is any other specific probability model that you can think of, is defined by Ayman Alzatra and his co-author, I think Felix Pamoy and Carl Lee. They're from Central Michigan University. So they came up with this model. So as you can see, it's creating like a shell, and then you could substitute any random variable probability distribution like the CDF and PDF into that shell. The only condition is that it is defined on the positive part. Now, of course, the Pareto type 2 or the Lomax distribution, we took this particular form. By the way, this K is the sort of the index of inequality. Then if you substitute that, then the gamma Lomax distribution would look like in as given in equation 2. And then the corresponding CDF, it can be obtained without much trouble. And this distribution involves, in terms of only the incomplete gamma function, which can easily be handled by any statistical software, be it R, be it Mathematica, or even in SAS. Now, of course, indeed, there are a sizable number of articles that has focused on Lomax distribution under the continuous aspect. For example, the gamma Lomax distribution was studied by Cordero and his co-authors as a particular case of Zographos Balakrishnan family of distribution, where G is any baseline continuous distribution. Lemonte and Cordero, they proposed another version, McDonald Lomax distribution, which is an extension of the classical Lomax distribution. So a lot of research works have been conducted to find, with the Lomax distribution, a mixture. Now, discrete Lomax type models, we didn't find that many references. There was only one reference it was in the works of Prieto, and I think Sarabia is one of the co-author for that article. And it's accidents prevention and analysis. Is Elsevier journal, and that's really good. So we found this reference of the works where the authors discussed at great length the discrete generalized Pareto model mixing with a zero inflated Poisson distribution, and they suggested the use on the modeling road accidents of black spots data. Now, of course, it was found that their discrete model is unimodal, and the PMF is always a decreasing function. So since the PMF was a decreasing function, it is somehow restricted in nature. It doesn't give you a lot of flexibility. Now, in our article, we propose discrete gamma Lomax distribution that is not always decreasing. So we claim that it has a greater flexibility. So here is the form of the discrete DGLD distribution, which is defined involving incomplete gamma function. And then one can, for the sake of mathematical or closed form expression for the CDF and the survival function that involves the floor function. Now, so this is our distribution in nature. Well, it's not very nice looking. But coming back to this scenario, I mean, in the article, we had quite a few other pictures or the shapes. So here is a representative scenario of the PMF plots or the DGLD when we put the scale parameter. So C and alpha is the shape parameter, and theta is the scale parameter. So we put theta equals to 1, and then what we observe is that when alpha is equal to C, that is, and they are very small, like alpha 0.8, C is 0.8, then it is showing you a positively skewed shape. But as we increase the value of alpha, let's say alpha 20 or alpha 30, but the values of C are really small compared to alpha, then it shows like approximately symmetric and other shapes. So it was found that for corresponding to different choices of the parameters, one could obtain like a positively skewed, symmetric, reverse J-shape, and so on. Now, in terms of structural properties, well, these are like a very simple type results that we found that if the random variable that is given in lemma 1, if the random variable y has the gamma Lomax distribution, then the floor function x, which is defined as y as the floor function, that will follow DGLD with parameters alpha and theta. And then the hazard function associated with the DGLD is given by equation 5. And discrete hazard rate has a lot of applications in reliability theory, in which the clock time is not the best scale on to describe the lifetime. So there are several scenarios in which discrete hazard rate would be useful. In terms of other useful structural properties, we are able to show that it has a decreasing probability mass function and decreasing failure rate when alpha is less or equal to 1. And of course, this distribution is unimodal, and it has modes at different points, which is defined in theorem 1. Okay, I do see. And the other result that we have here is that the discrete gamma Lomax PMF can be written as linear combinations of discrete Pareto PMFs, which is given in this result. Of course, one can find the moments of discrete DGLD. The rth moment is given in this expression, and it is not like analytically tractable in a way, but we found this scenario that if C is less than 1 over R, then the rth moment of the DGLD exists.
Excuse me.
Yes, Professor Kumar.
Yeah, the slides while Professor Sushmita Datta, Professor Indranil Ghosh is presenting these slides. So please stop sharing from your side. So please share it once again, Professor Indranil.
Do I need to share again afresh?
Yeah, it is okay.
Oh, okay. Okay. Is it okay now?
Now it is. But Susmita...
Now it is fine, Professor. Now it is fine.
Okay. Okay. Thank you.
Please.
Yeah. So we were able to show that if the C, one of the shape parameter is less than 1 over R, then the rth raw moment of DGLD exists. So if expected value of x square will exist if C is less than 1 over 2 and so on. Now that also, it's a little restriction, one might say, and as a result, we did not proceed with the method of moments estimation because then you have to make sure that C is less than half. Now, from a real data application perspective, how you can be so sure or guarantee that C will be less than half? So in terms of estimation, we followed the usual under the classical approach, the method of maximum likelihood. But what we observed is that for fixed value of C, the mean and variance and the mode of DGLD are non-decreasing functions of alpha. The skewness, DGLD is always positively skewed. And the kurtosis value shows that the DGLD possesses a heavy T characteristic, which I didn't include in this presentation for. So in terms of estimation, well, this is the log likelihood function. And then this can, of course, be solved using any statistical software. And in fact, this portion has been done by my collaborator, Ayman. So if you have any question, I'll definitely share with him. So he particularly used this proc SAS NL mix. And of course, interval estimation hypothesis test, one may consider the standard likelihood ratio technique, Fisher information matrix, because it is almost difficult to get the expected value of the Fisher information matrix. So a simulation study to exhibit whether it is reasonable or not. A total of 18 parameter combinations was selected for C, alpha, and theta, and the process was repeated 3,000 times. We consider different sample sizes, and we report the bias and the root mean square that are presented in a table that I'll show in a moment. And what we observe is that the bias and the RMSE for the parameter C are in most cases slightly larger than the bias and RMSE for alpha and theta. We don't know whether this is an anomaly or is it the usual pattern. There has to be an extensive simulation study, which we plan to do later on in a separate article. But of course, one thing we observe that as the sample size increases, there is a reduction in bias for all of them. So that's a desirable property. So for example, when for particular parameter combination under N100, the bias was for estimation of C 0.143, that goes down to 0.0357. And you can figure out that even the RMSE's values are also decreasing as the sample size increases. Like this one for N500, it is 0.0237. It's definitely smaller than what we had for 200 and 100. So that being said, now we focus on the application, which is the major motivation for this work. So these data sets are actually taken from console, and 3 data sets we have considered that represent the observed frequencies in the number of outbreaks of strike in 3 leading industries in the UK from the interval 1949, coal mining, vehicle manufacture, and transport. Console actually fitted those 3 strike data with a generalized Poisson distribution. But when we checked with that, it doesn't provide an adequate fit to the coal mining industry as well as even for transport as well. And when we fit this data with our DGLD, and even with the 2-parameter DGLD, when we set the scale parameter to be 1, it appears to be better performing. So here is the thing. And in terms of the goodness of fit, Arnold and Emerson, they came up with a non-parametric goodness of fit for discrete metals, and discrete analog of Kramer, von Mises, and Kolmogorov goodness of fit. So as we can see here, for the coal mining industry, the 3-parameter DGLD, that has a value of chi-square 0.1887, where the GPD is smallest, but with the 2-parameter DGLD, it is better. So even 3-parameter and 2-parameter DGLD is performing better than this particular difference. Then for the vehicle manufacturing industry, this is where our model didn't perform that. I mean, 2-parameter DGLD is not much different, but GPD was found to be really good. So we also reported that. But it's not really, I mean, it's not that worse compared to the GPD. But then for transport industry, it appears to be the 2-parameter DGLD appears to be the performing uniformly better than the GPD, which is really small. Like it's not a good fit at all. So this is so what we found is that based on this data application, that based on chi-square p-value, that GPD does provide an adequate feed to the vehicle manufacturing industry strike data, but doesn't provide adequate feed to the coal mining and transport industry strike data. Now, of course, one might say that, well, we haven't discussed with other discrete distribution, we tried with other popular discrete probability models, but those results were not even worthy of mentioning. So that's why we didn't include them. And then, of course, it was found that the DGLD fits the left and right tails of the 3 data sets as well. So that reaffirms the fact that DGLD can provide an adequate feed to the industrial strike data sets, and it could be considered as a baseline distribution for modeling the number of strikes industries. So overall, I mean, to wrap up this thing, so we discussed and studied a discrete analog of a continuous distribution of gamma Lomax or gamma Pareto type 2. And then we represent with the graphs that it has better flexibilities. The real application section, we focused only on industrial strike data, and it appears that it is performing really well in among the 3 different industries, only except for only one of them is performing uniformly well to others, 2 types of strike data. Now, of course, as an extension, this univariate, one may think of a bivariate or even multivariate extension. But first and foremost is we need to figure out real life scenarios where there will be a necessity for such an extension, albeit computational difficulty. And also, we haven't explored how to estimate efficiently the model parameters under the Bayesian paradigm. That is our another future work, and we are still exploring it. Haven't got there yet. And so this is actually, this article came up in this particular book, in chapter 11 in particular. And here are some of my references. And that's all I have for this short presentation. Thank you for your attention.
Thank you. Thank you, Professor Ghosh. So now we have 2-3 minutes for questions. Any questions? If any of the patient audience, you can ask questions for clarifications. Dr. Sadish, you may be having some questions. Dr. Sadish may be having some questions.
Yeah, no, sir. It's at the right time. We finished the right time. That is what I'm talking.
So, Professor Ghosh has illustrated his the applications of discrete gamma Lomax distribution using strike data, then some transportation data, and other things, and the presentation was very beautiful. Any more questions? Any questions? So
a short one about transportation.
Professor David.
Thank you so much. This isn't directly on your talk, Professor Ghosh, but in the United States, there's much conversation about autonomous vehicles and the impact that they will have on transportation. And I just don't know what sort of conversations are happening around the world about that. Do you have any insight?
Professor Banks, thank you for your wonderful comment. Well, we, Professor, looked at the count data in terms of which are strike data occurrences. And of course, I mean, that brings us to our new line of thought. We honestly haven't explored on these autonomous vehicle and other types of scenarios, not only just the strike data, but what if other scenarios that is that has the potential of behaving like a not so regular pattern.
Yes.
Can we model that? So definitely we are looking into this, and we are exploring public domain data and also trying to access other data with due permission so that we can think of where this model or this type of development would find a greater flexibility. So we haven't explored up to that point, Professor. Thank you for your comment.
So thank you, Professor Ghosh, Indranil Ghosh, for your nice presentation with illustrations. So on behalf of the organizers, I thank you, and I hope we can move to the next speaker. So thank you, Professor Ghosh. So shall we move to the next speaker?
Yeah.
Professor? Oh. So our next speaker is Professor Susmita Datta. Susmita Datta is available here. Okay. So I will just introduce. She is actually the co-director of Biostatistics and Epidemiology Division in the University of Florida. And she had an illustrious past. She had her teaching from Georgia State University, then University of Louisville, and then presently at the University of Florida. And she was president of Caucus for Women Statisticians. And she is a fellow of International Statistical Institute, American Statistical Association, American Association for Advancement of Science, etc., for her distinguished contributions to biostatistics, epidemiology, bioinformatics, computational biology, and so on. And she has been in the forefront of promoting women in STEM research. And today, she is going on, she will be presenting her paper on adaptive sparse multi-block partial least squares for survival prediction using multi-omics data. I even invite Professor Susmita Datta for her talk actually. Professor Susmita? Hello? Hello?
No, there is a message from Dr. Susmita Datta. Just see that. We see that. There is a message. See that.
See that?
Just click that message and you can see that.
What happened?
I have stopped sharing my slides long ago. Susmita.
She started earlier, but she closed it. No. Sadish sir, you may just contact.
She has just attempted to try to present for checking. And that is the time we have someone has you have mentioned that please close the slides. So that is the answer to that. Because your comment that Susmita Datta, please close the slides. The answer to that, I have stopped sharing my slides long ago. But I think she has some network issues, probably. That may be the reason to join. She will join soon. If
you can call her if you have a
make a call.
Phone number, yeah, someone will. Would you please? You have no phone number. We can check whether it is possible to contact her. via mail or otherwise. Probably there may be network issues
Hi,
earlier.
Susmita.
Yeah. Hi.
You seem to be muted.
Hello? Do you
We
hear
can
me?
hear you.
Good.
Okay. So it's your time. So please share.
Okay, now, I'm sorry I joined earlier. I didn't know that it's not over yet. Let me figure out how to now do it. Google Meet I don't use, so I'm kind of new. Let's see. Could you, okay. Share screen. Okay.
Yeah. Just you can use
Actually, we have introduced you already. So should I?
Yeah, no problem.
Should I introduce once again?
I don't know. That's fine.
I think it is fine. So she is a co-director of the Biostatistics and Epidemiology Division of the University of Florida. And she is a fellow of International Statistical Institute, American Statistical Association, and the Association for Advancement of Sciences, American Association for Advancement of Sciences. And she had made distinguished contributions in biostatistics, epidemiology, bioinformatics, computational biology, etc. And she is promoting women in STEM research. So now I invite Professor Susmita.
Okay. Thank you.
Welcome.
Most welcome.
Okay. Let's see if the slide shows up.
Okay.
Do you see? Okay.
It's coming. Okay. It's very well.
Okay.
Okay.
Great. Wonderful. So let me make it full screen.
Okay.
Or otherwise you can move in that way, no problem. But it is better to make full screen if possible.
Yes, I'm trying to. Sorry, I'm taking a little long because I've never used Google.
Yeah, there is a cup type symbol there in the upward or F5, or you can just click F5.
Okay.
Shift F5. Yeah.
Let's see. Do you see it at all?
Oh, we can see.
It is. It's okay. Can continue. No problem.
Okay. Which button to make it full screen? I don't see that.
Okay, you proceed.
Okay.
Okay, ma'am.
Okay. Well. Sorry for all the inconveniences. Today I'm going to talk about something different from many of the other presentations, as I work in omics data most of the time. So I will be talking about applications of that using ASMB-PLS partial least square, adaptive sparse multi-block partial least square. So what is the first? I will talk about the motivation. Oh, okay. Oh, I think if I don't use the full screen, it's not going to let me go from one slide to the other.
Just one comment. It's very easy to go to full screen. You see in the row at the bottom of the page. The bottom of the page. There is a row, and you see one symbol is marked. Just go to 3 points to the right, then you get full screen.
Okay, let's see. You are presenting. No. Oh, which symbol? How does it look like?
The third one. There is one symbol that's marked. That's a bit darker than the other ones right now. But select the one that is 3 positions to the right.
Yeah, that's what I have done.
Click on that. And then you should have full screen.
Somehow it is not doing it.
The symbol, that's a cup type symbol, cup type symbol. Not you are clicking on the other symbol. Right, the first, second, third, fourth symbol, yeah, next. It is not moving.
No, send a reaction. Somehow it's not working for me.
Okay, don't, no problem.
No, but it's not moving. That's why. Okay, let me.
If it is not moving, you please share it once again. Stop sharing and start it once again.
Okay.
And now, whether it is moving now?
Is it moving?
No,
it's not moving now. Sorry, it's not moving. I don't know how to fix it.
So better stop sharing and once again share.
It says it is in full screen, but it's not.
Share screen.
Yeah. No. I'm trying. Sorry. It's delayed. So I have done everything. I don't know.
Maybe you have a PDF copy that's easy to show.
You try with that square button on the top. Just to click that square button on the top. The top red portion, you see a square at the end.
Okay. Slide show button.
Slide is showing. It's not just moving, or it is not giving the full screen. That's the issue. Maybe some interaction is there with my system and that. That's okay. Let's see if I can somehow make it work. I don't know.
It is in the companion mode, I think so. That's why.
Oh, companion mode will not work.
In that case, it is not possible to make it like this. Probably.
But there is one more option, and that is to make a PDF copy of this and show the PDF. That way you can show it PDF on the full
PDF.
page.
Okay. Let me try that. It will take some time. I'm sorry.
1 minute. Okay.
Okay, I guess. I'll try with PowerPoint one more time, and then if it doesn't work, then I will get back to the other thing. Okay. Do you guys see the slide at all?
No, it is not seen. No, it is not seen.
It is?
It is not visible.
It's not visible. Okay. It's.
Please share it.
Now is
Please
it?
share it.
Do you see it now or no?
You have to share the screen.
Or if there is
I did that.
difficulty, still there is difficulty, you can send to me so that we can share it from here.
Yeah, maybe that's a better option. I'm not. I don't know. I'm not able to do it.
Please send the PDF copy to me. Okay. Or PPT, no problem. Anyway.
Okay. I really am sorry.
Yeah.
I can see it from here that it is showing, but you are not seeing
Okay.
it. That's the problem.
Okay. Doesn't matter. Let us share it from here, please.
Do you see it now?
Now it is okay, but the same problem is there.
Now it is okay. A little bit more better, I think.
If it moves, then okay, no problem.
Yeah.
Okay, it is moving.
Yeah, it is fine. Now it is
Okay.
moving.
No, okay. Oh,
Okay, please.
thank God.
Okay, proceed.
So, yeah. So first I will give some background and then we will talk about our method and then I will talk about the art package a little bit and the conclusions, etc., etc. So what is happening over here that we have the multi-omics data. Let's say we have transcriptomics data, proteomics, epigenomics, genomics data, and all of these are not similar. They can be related, but the nature of the data may not be similar. The dimension is not similar. So you cannot really merge all this data and have a huge matrix and cannot go in analyzing like that. So you have to have the block structure preserved. So, and then you want to use all this data because you want to have a system biological view of the data in order to predict any phenotype of a person, let's say. So the idea is that you somehow concatenate all these data, preserve the block structure, and then you predict some phenotype of a person, let's say. So the problem in this setup is each of these blocks, they are structured and they have high dimensionality. It has lot of sparsity and they are correlated within a block and between different blocks. So a lot of issues analyzing this data. So, and the use of these things, they have shown it in cancer, infectious disease modeling, and mostly in personalized medicine. So because when a patient comes for the same cancer, they cannot be treated similarly. So they have to, their genetic structure, genomic configuration, proteomic configuration, they are there, it's very different. So one medication may not work for all. So naturally, this kind of data, they are coming these days. So what we aim, we want to develop methods by integrating all multi-omics data and then predict or classify the patients accordingly. So what are the methods available till now? There are methods like sparse group lasso. Just simple lasso will not work because there is the group structure in the data. So sparse group lasso works in there. So what is it? Take the group information or the block information into consideration, and then that has a penalty term, and then incorporate a convex combination of the standard lasso penalty and the group lasso penalty. So another one is that integrative lasso with penalty factors. This is that consider the group structure and then assign a penalty factor for each group. So that's how it works. Priority lasso is similar, but you kind of identify which one is the most important block and sequentially add the penalties like that. So those are the lasso techniques. Lasso is, all of us know that they're feature selection techniques, basically. There are other things in the context of classification that you can use, which is random forest, the version of random forest, which is called block forest, which preserves the block structure of the data. And then there is a relatively recent work of data integration analysis for biomarker discovery using latent components. So Diablo, it uses the sparse generalized canonical correlation analysis, but again, it is a supervised method. Now, those were that we have talked about, mostly all these lassos we have talked about, they are all feature selection methods, but there are another ways of analyzing the data by dimension reduction. And as we know, dimension reduction is possible by principal component analysis or partial least square analysis. Somehow, I have been working with partial least square for a long time, and that works like a magic, but it did not come up from the stack group. It came from the chemometrics group. So, however, the extensions of partial least square is possible, which is the multi-block partial least square, where this group structure is taken into consideration. Sparse and multi-block partial least square, where the sparsity of the data is, sparsity is rampant in this kind of data. And day by day, we have single cell data, which is very, very sparse. So these kind of methods are very useful. And sequential MBPLS method is also there. Hello?
Nothing.
Hello? Is there anything? Hello? Do you hear me?
It is okay. It is okay. Please continue. Please go ahead.
Okay. Then this is our method, the adaptive sparse multi-block partial square. For the phenotype we consider is the survival time prediction using this kind of data. Okay, so for partial least square regression, multi-block partial least square regression, what we do, the goal is to construct a set of partial least square components. Just like principal components, we have these latent components, which are basically the linear combinations of all these covariates. But the difference between principal component and partial least square regression is that where the response is also taken into account, principal components response has no value there. So what we do is that we have, let's say, J many components. J's are 1, 2, 3 all the way, but most of the cases, I will show it later, just 1 or 2 components is good enough. And then the PLS component finds the maximum covariance between the linear combination partial least square terms and the response variable. The response is also, you can consider it part of the data that you have. So covariance between the response and the linear components of the original covariance. So but I have UJ here. What is UJ? They are that mean, corrected, and scaled responses. And then XBs are the data for block B. WJB contains the block variable weights, which is there. So you need the weights to construct those latent components. And then MXB is the number of variables in a particular block B. And so TJ is the most important term. We construct it in such a way that ultimately we get, I will show you the pseudocode or the algorithm, how you can make the maximum covariance of this latent variable terms and then the response. So after doing that, you get a super score. Of course, it is very, I mean, I'm not giving you the entire expression of PLS, but this is good enough for the presentation. TJ super is the score of TJ, where this TJ is consists of all the block variable latent components, and then your final score is capital TJ times WJ. Superb. Superb is the best weight for the blocks. Okay, so that's how it is done. The pseudocode for this algorithmic, it is, of course, we haven't done the theory. I suppose we can do the theory with the envelope model structure. PLS has the envelope model structure, but we haven't done the asymptotics for this. It's very algorithmic. So first you transform, center and scale the covariates and also the response. For J PLS component, let's say J equals 1. So take the response variable as is and then transform it. Loop until convergence that you get the TJ super score. And WJ, the weights for each block is constructed this way. And then we get the scores for this iteration. And finally, we get the TJ super, WJ super score, which helps us to construct this super T score for this iteration and update all the other variables. Now, once you get, so this will get you the first PLS component. Once you get it, you have to deflate it. So we construct something PJB, which is given over here. And for the covariates, you now subtract the first PLS component from there. So you do it for even for YJ, you subtract the first iteration, whatever the value is, TJ times QJ, which is related to the response. You deflate that too and keep going until it converges. That's the idea. Now, once you have this maximal covariance score, then you use the MBPLS model is built. We can predict the outcome for new samples, specifically given the new data. Now that you have the new data, your X is new now. We can calculate all these TJs and the WJs, so on and so forth. Then Y prediction is going to be, the predicted Y is going to be calculated like this. Okay. Now the problem is that L1 regularization is applied on feature weights. So that's, again, it is a tuning parameter. If the feature weights, the block weights, and it's really, lambda B is the weight for there, and if it is really big, the feature weight, if it is really big, and then let's talk about this. Feature weight is greater than B, then it will shrink to very small values, okay? And if the feature weight is less than lambda B, it will shrink to 0. So you have to be very careful in selecting lambda B. However, given, we have to have some ways of choosing this penalty parameter. So that's what we have done, that how to choose the penalty parameter really carefully, given the data, because we are talking about 50,000 proteins, 40,000 genes. It's not possible to look at the data and then just visually inspect the data and figure out what is going to be the penalty parameter. So we are doing it in a way that we construct a weight which is called lambda JB. B stands for every block of data, like genes or proteins. If it is B is protein, so that block of data, lambda JB, which is the penalty parameter. How do we construct it? We take the quantile of the weights that we figure out. The weights, it's calculated from the algorithm itself, and then you take the quantiles of the weights and you tell the process to take the 80th percentile or 90th percentile of the data. If you know that the data is really, really small, then you take only the 80-90% of the data. Or if it is very big, you can say the lower weights, so on and so forth. So the weights, let's say, of course, these are regular, these are not rational number, just for the explanation part of it. Look at the data. If it is like this, what we do, we take the WJB, let's say these are given over here. You take the absolute value, and then let's take the 80th percentile, then lambda becomes 4. And then you take the sparse function. Sparse function is nothing but sine of x mod x minus lambda. So you calculate. So updated weights are formed this way, like 0 minus 4, so on so forth. That's how you do it. Finally, only this one will give you the value 1. So that's how we construct the this W lambda JB. So that's the beauty of this method. It does it very well. However, the method has so many tuning parameters, so you have to kind of figure out a model, do the model selection. How do we do that? With k-fold cross validation. Let's say we have 2 blocks of data. Let's say just 2 blocks of data. It's a horrendous method in terms of computation because we have huge blocks of data. Let's say we have just 2 blocks of data, and number of PLS components is just 3 of them. So what are the quantiles of block 1? Let's say we have the block 1 quantiles are given over here, block 2 quantiles are given over there here. So this goes up to 8th quantile, this one goes up to B8th quantile. Of course, you cannot take the same quantiles because it depends on the dimension of the data. So you have A times B combinations of quantiles. You have to take them into consideration, and then you have to check the MSE of the data, MSE of this folds of data, and then figure out which one minimizes this lowest MSE. And that's how you determine what is going to be the value. So fix the combination. So first fix the combination for Lth PLS component, and then if you need, go to L+1 PLS component. So how do you decide? if the MSE, by taking one component, let's say just MSE for component 1, you go to MSE component plus 1 if it really improves, decreases the MSE by 5%. So that's how you do it. Otherwise, stick to the minimal number of PLS components. Okay, so that's how we do it. Now, how does it work in applications? Let's say we are using multi-omics data to predict patient survival. We are using accelerated failure time because that's Cox proportional hazard assumptions with all these kinds of data together. That will be really difficult. So we are taking a T model, which is log survival time. And of course, in survival time, we know that it has a delta built in it because censoring is involved. So TI, the actual observed time, is minimum of actual observation and the censored time. Okay, and delta is the parameter whether the survival time is censored or not. So, and then we use mean imputation for carrying the censored data. And so the simulation we do, so this is the structure for the survival data analysis. And so that's your Y variable, and X's could be microbiome data, proteomics data, and some clinical measures data. So we are doing the similar things in simulation setup. We have taken microbiome and metabolome data and predict survival. In real data, we have an outcome is progression-free survival time, and we have microbiome, proteomics, and clinical data, all of them together. So this is the structure of the simulation model. We have multiple samples. In many samples, these are operational taxonomic units of microbiome data, and these are many metabolites there, and these are multiple samples. And then you have the patient survival there. So that's the structure of simulated data. Now we have varied so many parameters over here that it's hard to explain the simulation model. In this short time, we have changed the distribution of the survival, so on and so forth, and then calculate the MSE, predicted MSE, which is given over here. One thing, just take-home message is that what we have plotted the proportion of that variation explained by the PLS components. The red one is component 1, green one is component 2, deep green one is component 3, so on and so forth. But if you look at the data, you will see that most of the time, the first partial least square component takes care of all the variabilities in the data. And if you have just the first and second, that's it. You don't need third and fourth. That is, these other colors are almost non-significant. So if you have the first two PLS terms, it's all right, which we have seen it time and again, that you don't need. Why? Because partial least square, if you have too many components there, it overfits the data. So you have to have the minimalist attitude here. Now, this one is also the simulation result. This is area under the curve for ROC curve. Again, these have different structures of the simulation parameters. So these are different methods. Red one is our method. This is IPF lasso, priority lasso, and SGL lasso. All of them are lassos. But the take-home message from here, if you increase the noise and if you compare the AUC, area under the curve, all the time, the red one, most of the time, I would say, most of the time, ours is beating other methods. Sometimes the SGL is comparable. And these are different effect scales. So either a triangle or a dot is there. Most of the time for us, it does not make much difference. So it is all right. Doesn't matter what you take to be the effect size. It's always good. In terms of computational efficiency, of course, I work in bioinformatics where if you don't have a fast method, nobody uses it. But this is the average computational time for different methods. Priority lasso is the best one. Note that these times are all in seconds, so it's really not that bad. So 0.5 seconds, but priority lasso does not work well in terms of MSE or MSCP, nothing. So ours is not that bad at all. MBPLS is the best, but MBPLS is not the best method. Ours is one of the good ones in terms of computational time, and also it minimizes the errors. So this is really, really good. The SGL, another comparable one, takes a long time. It's more than in seconds. So in terms of real data, we take it from the database, TCGA database. It's a progression-free survival time for 89 samples, 55 events, and censuring rate is 38%. And we have microbiome data for 225 microbiome features, proteomics data about 6,000 features, and we have clinical variables, which is 17 clinical variables. If you use just simple linear regression for each of these blocks of data and regress it with the survival, and then you have the FDR adjusted beta's significance for each block, then the results are, if you get 0 significant microbial features, 0 significant proteins, and 2 significant clinical variables. So that's not really good. Now, if you run our method and all the other methods that I have talked about, then you can see that the optimal number of PLS components for our method is 2. Okay, and these are the quantile informations that we have used. Of course, one can vary it, but this is we have done what is the best model, and that way we have determined the MSE. So for the best model, for our case, MS fit is 0.674, and then a prediction is 0.674. The only comparable ones again is sparse group lasso. It's 0.698, 0.778, which is little above ours. So we are still doing the best over here. And as far as feature selection goes, you have our method is note that the microbial taxa, if you do this usual regression, it picks up only 0 microbial taxa, but for us it is 6 microbial taxa. It considers in other methods 0 proteins, ours is 21 proteins, and for clinical variables it picks up 2 out of 2 clinical variables. Remember that a regular regression had only 2 clinical variables, so here it takes 2 also out of 17. So block weights, these are for block weights for microbiome, proteins, and clinical. So the clinical ones are very important. It had 17 of them, but it plays an important role. Of course, these have been tested time and again. That's why they use these clinical variables. IPF lasso, opposed to that, it does not take any microbiome data, microbial taxa into consideration. Takes only 1 protein and 1 out of 2 clinical variables. SGL again does not take any microbial taxa, no proteins, only but 3 clinical variables out of 17. Priority lasso the same way, so it is not basically using the information for the microbial taxa or proteins, anything. Basically they consider it to be just insignificant. That's the problem with the feature selection methods opposed to latent variable methods. Latent variable methods usually takes adjust the weights, but takes many variables into consideration. So although we have used through the weight and percentiles, we have chopped off some variables, but even then it works much better that you are getting some information from the data from all the covariates. So the super score that we have calculated from our method, not only it predicts the data well, it classifies the patients into 2 groups, that high risk, low risk, very properly. I'm not telling you the details of it, but we have done some other additional analysis with 2 PLS components, the model fitting and prediction performance for different methods without the clinical block. So we did not have the clinical block here.
Excuse me, madam. So you have only 1 or 2 minutes. So
yeah,
try to. So we are out of time. We are out of time.
No, that's fine.
Okay.
So the R package, if anyone wants to, I'm done almost.
Okay.
Yeah. So if anyone has any interest, ASMBPLS is already there. It is there in CRAN. It is there in Bioconductor. And the classification part of the work has been published in Genes. The other one is under review, but we have it on bioRxiv. So the conclusion is, using both the simulated and real data, identify key biomarkers. The method has good prediction and classification performance, and the package is there. It's good for visualization as well as classifying the samples and phenotype prediction. So it would be a very valuable tool for multi-omics research, and this is done mostly by my student Runzi Zhang, who has just graduated, and these are the committee members, and this one was we did a lot of research meetings through Zoom, and this one was always there. So the cat, and that's it. Thank you.
Thank you. Congratulations, Professor Susmita, for your nice presentation. Very challenging area.
That's true.
Genomics data, what types of genomics data you have done very well. So your illustration also very well. So it was very informative. I think many of the audiences may be having some questions, but due to lack of time. So what should we do? Dr. Satish Kumar may please.
Yeah, I mean,
Professor
I can respond to.
Since we are out of time, one question can be permitted if anyone is. Yeah.
If anyone is interested in having some questions, please ask. Any clarifications are needed?
No question.
Or prospective researchers may contact here. Actually.
Okay, yeah, that's better.
No problem. No problem.
That may be good. That may
can
be good.
contact via email or online other way. Anyway.
So very many thanks. Many thanks.
You are very welcome. Sorry, I was not familiar. It took some time for me to. I'm familiar with Zoom, but not this one.
Thank you, professors.
Okay.
Thank you, Professor Indranil Ghosh and Susmita Datta for your nice presentations. and very informative presentations. And we are very much grateful to you, professors, for supporting WSTA 2023 through your deliberations. Also, we wish to extend our thanks to Professor K.K. Jose. Sir, please, we are very thankful to you, sir, for chairing this session.
Thank you very much.
Thank you.
Thank you for everything and being patient and for the invitation as well.
We wish to get your support in future also.
Absolutely.
This time,
absolutely. Thank you.
Welcome. Now let us move to the next session. It was a little bit late. Sorry for the sorry, extremely sorry. Bhagyalakshmi, please share briefly and support him for further proceeding to the session.
Yes, sir. Am I audible?
Yeah, audible.
Yeah, you are audible.
Hello, everyone. Now we are moving on to the technical session 30 of WSTA 2023 that shall be chaired by Dr. Rajaratnam Arunachalam. Dr. Rajaratnam Arunachalam is a
Professor Bhagyalakshmi, it is changed. Is Professor B.K. Panda.
KB Panda.
KB Panda is chairing this session.
Should I start?
Yeah, Professor K.B. Panda is great. In fact, very Namaste, Professor. Namaste, Professor. Is Professor and head of the Department of Statistics. He was the Professor and head of the Department of Statistics of University of Odisha. University of
Now I am in Central University of Jharkhand.
Yeah, now he is the Central University of Jharkhand. Thank you, Professor, for your support as to chair this session. In fact, there is a lot of things we have to say about you. In fact, I hope that the time is, since there is little bit time is out of time. So please introduce the speaker and please carry over.
Thank you, Professor Satish Kumar. A very good evening to one and all present on this occasion. Namaskar to all. I, KB Panda, Professor of Statistics, Central University of Jharkhand, Ranchi, on behalf of the Department of Statistics, School of Physical and Mathematical Sciences, University of Kerala, on behalf of Indian Society for Probability and Statistics, and on my behalf, extend a warm and cordial welcome to you all to this special invited lecture. That's a technical session number 30, plenary session 8 of the 8th International Webinar on Recent Trends in Statistical Theory, WSTA 2023, which is being organized in conjunction with 7th Annual Convention of Statistical Fraternity, Kerala, SFK, and National Statistics Day Celebrations 2023. At the outset, I must thank Professor Satish Kumar, Chairman of WSTA 2023, for giving me this opportunity to chair this session. Thank you, sir. Our session is technical session number 30. This is special invited lecture, and our esteemed speaker is Professor Michael Evans. Let me introduce him. I will give a brief introduction. Michael Evans is a professor of statistics at the University of Toronto, a PhD from the same university way back in 1977. Professor Evans started his career also in 77 in the same university, with leaves spent at the Stanford University and Carnegie Mellon University. He is a fellow of the American Statistical Association. He was an associate editor of JASA, Theory and Methods, 1991-2005, an associate editor of the Canadian Journal of Statistics, 1999 to 2006, and from 2007 till date, an associate editor of Journal of Bayesian Analysis 2005 to 2015, and as editor from 2015 onwards. He is a subject matter editor for the online journal Facets, F-A-C-E-T-S. He became the president of the Statistical Society of Canada in 2013-2014. His research areas include multivariate statistical methodology, computational statistics, and foundations of statistics. He has co-authored and authored many research papers and also books being published by Oxford in 2000, W.H. Freeman in 2004 and 2010, and CRC Press, Chapman and Hill in 2015. With this brief introduction, may I now invite Professor Michael Evans kindly to deliver his talk entitled How to Measure Evidence-Based Factors or Relative Belief Ratios. Over to Professor Evans.
Well, thank you. Can you hear me okay?
Yeah, you are audible.
Okay, yeah. Great. So thank you for that kind introduction. And now the hard part of making sure that my screen can be shared. So how do I do that from my end? Do I have to do anything? I can just start my presentation or what?
Yeah, Professor, we can share it from here.
So sharing it, I have to tell the, sorry, as with the previous speaker, I'm not that experienced with Google.
Yeah.
How do I share this?
Yeah, Professor, yeah.
How do I do that? How do I share my screen? There's probably a change full screen.
It's present now worked for me. So you can try that. That 1, 2, 3, 4, 5th one from the bottom. With the arrow sign.
Whether you're trying, Professor, we can share it
Present
from here.
now. Present now, right?
Yeah.
Okay.
That worked for me. I don't know.
Okay.
It's not. Is yours open?
Yes, it's open now. Can you see my slide?
Not yet, but it might come. I don't know. It's not.
Choose what you want to share.
Yeah.
You can see my screen now.
Oh,
yeah,
it's fine. Fine.
It's fine, Professor. Great. Thanks very much. Okay, so I want the full screen here.
Oh.
Here we go.
Oh, very fine.
Okay, so thanks very much for having me. There's a paper on my website with 2 co-authors, as I've indicated there, and what I'm going to talk about is a little bit controversial. I've been in some discussions with various people about this. I'm going to talk about how to measure evidence a little bit. I have to give some background, and the way I propose to do it is through what I call the relative belief ratio, and that's in a Bayesian context. And I quite often get the response, well, why don't you just use the Bayes factor? Because that's a very well-known approach to this problem, and there are some reasons why I don't think that is the right way to do it. So I'm going to explain that today. So this is an argument, and it is my argument. The other side could present theirs too in some other context. So I have to give some background, and the basic idea is go back to why are we doing statistics in the first place? So we have a scientist. There's an object of interest, which I've denoted by psi here. And the scientist has collected data, And there's these questions that the scientist has about psi, and it's believed that the data contains evidence concerning the answers. So there are two basic questions, namely, we want to estimate the quantity psi, and I'm going to denote an estimate by psi of x. And I also want to say something about the accuracy of that estimator. And similarly, there might be, or separately, there might be a hypothesis that the scientist has about the value of psi. And so what is required from a statistician or a theory of statistics is to quote, is there evidence in favor of that hypothesis or evidence against that hypothesis? And I put this in italics here, together with an assessment of the strength of that evidence. It's not obviously good enough just to say, well, we have evidence in favor, we have evidence against. We really want to know not only that, but how strong is that evidence? And that really plays a key role in some of the discussion that is going to come later in the talk. So how are we to reason from the data to answer E or H? And my thesis is that that's based on characterizing and measuring statistical evidence. And there's a book on that in the CRC series. Now, I'm just going to talk about one isolated aspect of this and what the book covers. And it's really a theory of statistical reasoning that's a little bit different than others that are been proposed. It's Bayesian in nature, and we'll see why in just a moment. So we have to choose a model. We also have to elicit a prior, and this is going to be a proper prior. And what that means is that the parameter, the model parameter, and the data, they have a joint distribution, a joint probability distribution that is the prior times f theta of x, which is the sampling distribution. Now, there's some other aspects there that I'm going to skip over because really I want to go down to the very bottom then and say, okay, if I'm going to make inferences to answer those questions about psi, so this is point 7, I want that to be based upon the principle of evidence. But certainly in terms of a theory of statistical reasoning, I wouldn't skip the others, but for today's talk, I will. So what I can express everything in terms of the rules of statistical inference when I'm in a Bayesian context, because in this using a probability model, because I've given a joint distribution for theta of x, theta and x, I have a probability model now. Okay, so I'm going to just denote that generically as omega with the sigma algebra script f and the probability measure p, which would be the joint probability measure for theta and x. And now let's suppose I'm interested in whether or not the event A, so something has happened, is the event A true? I don't see whether or not it's true or false, but I do observe that an event C has occurred. And both these events for now will have positive probability. So there are 3 principles that I'm going to use as part of my theory. The first principle is the principle of conditional probability. For me, probability represents beliefs, no matter how it's assigned. And the initial beliefs are represented as P of A. That's my initial probability that A is true. Measuring my initial beliefs that A is true. After I observe that C has occurred, that's replaced by my conditional beliefs, probability of A given C. So that's the first principle. The second principle is what I call the principle of evidence. Because one of the reasons I'm a Bayesian is because I think that formulation for statistics gives a very clear way as how to describe whether I've got evidence in favor or against the event A being true. For example, if my new beliefs are increased over my initial beliefs, then observing C is evidence that A is true. If my beliefs are decreased, then that's evidence that A is false. And if they're equal, well, then that means that A and C are statistically independent, so I don't get evidence either way. The third principle here is a little bit more controversial. I don't think the first 2 are very controversial, but the third is maybe a little bit controversial. I'm going to use or measure evidence quantitatively, in part, by using what I call the relative belief ratio, which is just the ratio of the conditional probability of A to the unconditional probability of A. So if that's bigger than 1, I've got evidence in favor. If it's less than 1, I've got evidence against A being true. I'm not the first to propose that as a measure of evidence. You can certainly find that in the writings of Keynes going back to the 1920s, and I.J. Good and many other authors as well. So as I said, it's a measure of evidence. If the relative belief ratio is bigger than 1, then I've got evidence in favor of A being true, etc. Now for those questions E and H, I'm going to express my quantity of interest psi as some function of the model parameter, capital psi of theta. And it has a prior distribution, that quantity, and it has a posterior distribution. So what's the relative belief ratio? Is there evidence for or against the value psi being the true value of this quantity of interest? Well, I just calculate the relative belief ratio, which is I can do provided that the prior probability of psi is greater than 0, right? Is that ratio. And of course, that's just the ratio of the probability functions. Now, what do I do when I've got a continuous probability measure so that the probability of psi is now equal to 0 everywhere? Well, I do the usual thing. I look at a sequence of neighborhoods that converge down to the set consisting of psi by itself. Say, in the Euclidean space, this would be a set of balls, right, of radius epsilon, let's say, and let epsilon converge centered at psi, and let epsilon go down to 0. And then I'm going to define the relative belief ratio for psi being true or false as the limit of that ratio. And when I do that, I get the ratio as provided the prior density function is continuous at psi and positive, then I get the ratio of the posterior density of psi to the prior density of psi. And it's an interesting result that I'm going to make use of. It's also true, so the relative belief ratio is expressed for the conditional of psi given the data divided by the unconditional of psi. Well, it turns out that the relative belief ratio is also equal to the conditional for the data given the value of the parameter divided by the unconditional for the data. And that's sometimes called the Savage-Dickey result. And we'll make use of that a little bit later. So the relative belief ratio is a valid measure of evidence. What do I mean by that? I mean that it satisfies the principle of evidence. But it's not the only one. There are many other ways in which I could express the principle of evidence. So for that, what I want is a cutoff, some number C, such that if the measure is greater than C, then that's evidence in favor, etc. Perhaps the main measure of evidence that's been used currently is the Bayes factor, which is indeed a valid measure of evidence. And what's the Bayes factor? The Bayes factor is just the ratio of the posterior odds in favor of A being true to the prior odds. And it is indeed a valid measure of evidence. You can show that with cutoff equal to 1 as well. If the Bayes factor is bigger than 1, that's bigger than 1 if and only if the conditional probability of A being true is greater than the unconditional probability. And that, of course, requires that definition requires that the probability of A is not 0. And I'll discuss what happens when A is 0, probability of A is 0 in just a minute. So, as I said, the Bayes factor is commonly used to measure evidence, so why should we use the relative belief ratio instead? So what I'm going to do now is give a sequence of 5 or 6 points that give my argument as to why we should be using the relative belief ratio instead. First of all is simplicity. Why are we looking at ratio of odds when we can look at ratios of probabilities? In fact, the Bayes factor can be expressed as the ratio of some, thinking of a hypothesis now, and presumably the hypothesis has positive probability, if I'm going to use the Bayes factor, that is. And it can be expressed as the relative belief ratio of the hypothesis to the relative belief ratio of the alternative. So, first of all, the Bayes factor can be expressed very simply in terms of the relative belief ratio. It's not true the converse. The function of, to get the relative belief ratio from the Bayes factor is somewhat more complicated. So this ratio makes it seem like the Bayes factor is a comparison of the evidence for the null hypothesis with a comparison with the evidence for the alternative. But that's actually not true, because if there's evidence in favor of the null hypothesis, there's always evidence against the alternative, and conversely. It behaves properly as you would think a measure of evidence should. And that has a consequence, namely the relative belief ratio. If it's bigger than 1, so there's evidence in favor, the Bayes factor is always numerically at least as large as the relative belief ratio. And similarly, if there's evidence against the null hypothesis, the Bayes factor is always smaller than the relative belief ratio. And that has a consequence that we'll talk about in just a minute. This is perhaps one of the more critical criticisms that people have made concerning the relative belief ratio versus the Bayes factor. It's claimed that the Bayes factor, as a measure, it measures evidence, but not only does it tell us whether we've got evidence in favor or against, it's claimed that the size of the Bayes factor tells us something about the strength of the evidence, and that the Bayes factor does a better job at this than the relative belief ratio. I cited Keynes and Good as people who talked about something. They didn't call it the relative belief ratio, they called it something else. Good in particular has a counterexample as to why he preferred the Bayes factor to the relative belief ratio that's based on just this idea. And what I want to point out is I don't think that that is correct reasoning, okay? So Jeffries also, he treated the Bayes factor as not only a measure of evidence, but the size of the Bayes factor as measuring how strong that evidence is. And so for evidence in favor, he proposed this scale. So from 1 to about 3.1, that's evidence in favor, but he says it's barely worth mentioning. From about 3.1 to 10, it's substantial, etc. And let's go to the very bottom there. If it's bigger than 100, Jeffries says the evidence is decisively in favor of the hypothesis being true. And if you want to get it for evidence, the scale for evidence against, you just take reciprocals there with the same qualifiers. There are other people who've changed Jeffries' scale a little bit, but basically the idea is the same. They're all claiming that there's this scale on which evidence can be measured, and this is independent of the context, and I don't agree. So does the Bayes factor or the relative belief ratio measure the strength of the evidence by its size? And my answer is a categorical no. How do we measure the strength of evidence? Well, we know from either of these quantities, we get whether we have evidence in favor or against. We measure the strength of that evidence by how strongly we believe what the evidence says. And of course, if we're measuring belief, this involves probability. And of course, these will be posterior probabilities now. And I'll illustrate this by a very simple example called the prosecutor's fallacy. This is an example well known in the literature that actually arose from a court case where the prosecutor misused probability. So that's the reason it's called the fallacy. But the example is simple enough that it really illustrates a lot of points. So I like it. So you have a uniform probability distribution on a population of size n, and there's a crime that's been committed and some evidence has been left at the crime scene. Let's suppose it's some kind of genetic evidence, and it's shared by m individuals of the population. The error the prosecutor made is that he claimed that this evidence was categorical. He flipped the consequent and the antecedent and calculated the probability as 1. If he had probability is guilty given they have the trait as 1, but really what he was computing was the probability has the trait given that they're guilty as 1, and that's kind of obvious. So he quoted the wrong probability. So that's why it's called the prosecutor's fallacy. So that's been corrected, of course. But the prosecutor was, in a sense, also correct that the fact that an individual that they picked out has this trait, that's evidence that the individual is guilty. It doesn't mean they're guilty, but that is evidence in favor of guilt. If you have the trait, that is evidence that you are guilty. So let's suppose, though, that there's 1,000 people in the population that have the trait. So what's the probability that they're guilty? How strongly do we believe they're guilty? given that they have the trait, that's conditional probability is 1 over m, or in this case, it'd be 1,000. Pretty small. Now, as I said, the prosecutor is correct that the possession of the trait is evidence of guilt, and when you compute the relative belief ratio, you get the population size, n over m, and if n is big, let's suppose n is 10 million, then n over m is 1,000. Now, think about that scale that Jeffrey's quoted. That will be decisive evidence in favor, but then ask yourself the question, given that we only our belief that what the evidence is saying is correct is only 1,000, would you convict the individual? I think most people would just say, well, no, that's pretty weak evidence, right? Even though it's evidence in favor of the person being guilty, that's too weak. What about the Bayes factor? Does that fix it? No, because remember the inequalities, the Bayes factor is always going to be bigger than the relative belief ratio. And in this case, the Bayes factor is, it's not very much bigger. It's n minus 1 over m minus 1, but it's still bigger, and it commits exactly the same sin if we're going to measure the strength of evidence by its size. So my claim here is that this example shows very directly that the size of the Bayes factor, or the relative belief ratio for that matter, does not indicate the strength of the evidence. And similarly, if you ask for the probability of innocence, you get m minus 1 over m, so that will, in this case, will be virtually 1, but you have evidence against innocence, so you have weak evidence of innocence in this case. Against innocence, pardon me. So there are many other examples like this one, but this one's very simple because it's a dichotomy, right, between guilt and innocence, and it shows that I think that the size of these quantities don't measure the strength of evidence. Also, it shows that probabilities don't measure evidence. The probability of guilt was 1,000, but we definitely do have evidence that the person is guilty. So you can't try to measure evidence just by probabilities alone. You have to ask, how have my beliefs changed? And that's one reason why I like Bayesian statistics, because we get an answer to that question. Also, there's the role of utility or loss, which I haven't made any reference to here. But in the example of the crime, probably you would not convict because the consequences of conviction are so strong, right? If it was a murder case, for example, and the person was going to jail for the rest of their life, you wouldn't convict on the basis of weak evidence. But if it was a different context where there was evidence that somebody was infected with a highly infectious disease, and whether to quarantine them or not, you may quarantine them, even though the evidence is weak. And generally, my feeling is, and my thought is, that there's nothing wrong with incorporating utility and loss functions into a statistical analysis. But the first thing we want to know is, what does the evidence say? So how, in general, to assess the hypothesis that psi is equal to psi naught? Via the relative belief ratio, how strong is this evidence? Well, one thing I say is you've got to quote a posterior probability. So in some problems, you could quote the posterior probability of the hypothesis itself, but in continuous models, that won't work. So I compute something like this tail probability here. So if there was evidence in favor, and this probability was of psi naught being true from the relative belief ratio, and this posterior probability was large, then I know the posterior, my belief that the true value has even larger relative belief ratio is small, and I'm going to say that there's strong evidence in favor of the null hypothesis being true. I won't discuss that anymore now, but there are other ways in which you can measure the strength of the evidence, but it always involves posterior probabilities. Asking the question, answering the question, how strongly do I believe the evidence? And you could also calibrate the Bayes factor in the same way, but nobody does that currently. Now, what to do when the prior probability is 0? Well, I've already said what we do for the relative belief ratio. I define it as a limit. Now, I could do the same thing with the Bayes factor. Nobody does that, it seems, because when you do that, you get back the relative belief ratio. The limiting Bayes factor is equal to the relative belief ratio. And this is, I think, the natural way to do things in these continuous contexts, just as we think of the probability density as being a surrogate for the probability of a point in the continuous model via the approximation, right? For small sets around I should have said x here, right, rather than psi, then the density times the volume of that set is approximately equal to the probability of the set. But that's not what is done for the Bayes factor. What people do, and I think this goes back to Jeffreys in the 1920s, is people use a mixture prior. They put a prior probability on the hypothesis. Here that psi is equal to psi naught, and that prior probability would be p, so pi sub psi naught is a probability measure for theta concentrated on the null hypothesis, and then mix it with another probability measure on the whole parameter space. Typically, they take this probability to be 1/2, and they choose this prior probability pi sub psi naught is a probability measure concentrated on the null hypothesis, a set of psi's such that capital psi of theta is equal to little psi naught. That is what's typically done. And then you can calculate the Bayes factor, which is the ratio of those two prior predictives. This is the prior predictive under the null hypothesis, and this is the prior predictive in general. And you can also calculate a relative belief ratio. And people like the Bayes factor because it doesn't depend on p, that mixture probability. But if we wanted to calibrate it, as I described earlier, the posterior probability definitely does depend upon p. So you don't escape the use this mixture probability just by going to the Bayes factor, because at least if you accept my convention that it has to be calibrated by making some reference to posterior probabilities. Now, another aspect of this mixture probability, that the prior, if I go back, this prior here, pi, which is a continuous probability measure, that actually does induce beliefs on the null hypothesis, whether we like it or not, just by taking a limit of a set of neighborhoods of the null hypothesis and letting them shrink down to the null hypothesis itself. We get, under very reasonable regularity conditions, the conditional prior distribution of theta given psi naught. In other words, we've integrated out the nuisance parameters. Now, if you put this pi sub psi naught equal to that conditional probability measure, then the Bayes factor is identical to the relative belief ratio. And if you don't do that, then I submit that there's a contradiction in the expression of the prior beliefs. The prior beliefs pi sub psi naught for theta on the null hypothesis don't agree with the prior beliefs induced by the prior pi. Whoops, seem to jump way ahead here, sorry. Start to go over time, please just let me know. Okay. So if you're interested in the estimation problem too, so I want to compare values psi1 and psi2, I have to use a different mixture prior depending on its psi1 and psi2. I don't have one prior, I have many priors. And probably that's why the Bayes factor is not used for estimation problems. That's not a problem with the relative belief ratio because there's only one prior, namely that capital pi that I referred to. And so you estimate psi by the value that maximizes the evidence. And you've got a measure of accuracy of that estimator by just looking at what I call the plausible region. That's just the set of values that have their evidence in favor, and you compute the posterior probability of that set to see how strongly I believe the true value is in that set. So the size of that set and its posterior probability are telling me something about the accuracy of psi. You could also compute credible regions as well, but I won't talk any more about that. Now, so the fourth thing I want to talk about is a relationship. I think I might have the numbering wrong. Relationship with likelihood theory. Really, the relative belief ratio for the full parameter is a version of the likelihood. I can't multiply by an arbitrary constant or I destroy the interpretation of the relative belief ratio, but it is indeed a version of the likelihood. And that means that the estimator that I pointed out, by maximizing the relative belief ratio, is just the MLE. And the plausible region and the credible regions are likelihood regions. And that's true for a marginal parameter as well, except now we're talking about the integrated likelihood where I've integrated out the nuisance parameter. But the Bayes factor really has no, I've written down the formula here when the posterior prior probability is greater than 0, and the Bayes factor has no clear relationship with the likelihood function for the original model. And the consequence another consequence of the relative belief estimate or inference procedures is they're all invariant under smooth parametrizations. Now, what about robustness to the prior? So I'm going to compare the relative belief ratio with the Bayes factor. So I need to suppose I'm in a situation where the prior probability for theta value is greater than 0, or the Bayes factor, strictly speaking, isn't defined. Or I might be using the mixture prior. That's okay. But these robustness results I'm going to quote apply to the relative belief ratio, whether I'm in the discrete case or the continuous case. They don't matter, but not for the Bayes factor. For the Bayes factor, I always have to have positive probability at theta. And so I'm going to let T be a minimal sufficient statistic. It turns out, obviously, the relative belief ratio really only depends on the data through the minimal sufficient statistic. And now I'm going to consider linearly contaminated priors. I'm going to make contaminated at theta by a small perturbation. So the relative belief ratio is perturbed to this quantity here. I've called it RB sub epsilon. Now I'm going to calculate the Guiteau derivative, the derivative with respect of the relative belief, the log of the relative belief ratio with respect to epsilon. I should point out too, it doesn't matter whether I use the relative belief ratio or the log of the relative belief ratio. The inferences are invariant to the choice. It doesn't matter. It's just that I use the cutoff 0 with the log of the relative belief ratio as opposed to 1. It doesn't matter. And I get this formula. The interesting thing about this formula is that it doesn't depend on theta. It's constant in theta. So I'm calculating the derivative of the log of the relative belief ratio. That's measuring the change in the function as a proportion of the value of the function at a point. So that is constant in theta. Also, the expected value of that logarithmic derivative is always 0. The prior expectation is always 0. Now, what about for the Bayes factor? Well, I'm not going to read out, you don't need to read out the formula. The only thing you need to see is that it's a mess. It does depend on theta, okay? Moreover, if I isolate on one particular case where these two quantities are equal, then the logarithmic derivative of the Bayes factor at epsilon equal to 0 is the logarithmic derivative of the Bayes factor times this quantity, which is always positive. So the logarithmic derivative of the Bayes factor at theta naught, let's say, is always bigger than the logarithmic derivative of the relative belief ratio. It's less robust to the prior. It's what that is saying.
Sorry to interrupt. In fact, we are approaching time.
Okay.
Can you please conclude within 2-3 minutes?
I will. Yeah. So the information inconsistency was another nice property. Incoherent, sometimes these measures of evidence are criticized because if I have A as a subset of B, is it possible that I could have the relative belief ratio bigger than for A bigger than the relative belief ratio for B? Yes, it is. It makes complete sense. These are not incoherent, and that's described in the book. In fact, you can have evidence in favor of A and evidence against B. So let me just summarize though. So these are the points from my talk that hopefully I have made somewhat clear. All inferences should be based on a clear specification of what is meant by statistical evidence. A Bayesian formulation allows this through the principle of evidence. While there are a number of ways this can be implemented, the relative belief ratio as a measure of evidence, has a number of advantages. It isn't enough to just state whether there is evidence in favor or against the hypothesis. It is also necessary to state clearly how strong the evidence is, and this is done by measuring to what degree we believe what the evidence says. Both the Bayes factor and the relative belief ratio need to be calibrated, and this is context dependent. Thanks very much.
Thank you so much, Professor Evans, for delivering a wonderful talk on measuring evidence. It is indeed very interesting and useful in our practical life. Now the floor is open for a discussion. 1 or 2 questions may be taken. If the audience could ask questions, that would be considered. If there are no questions, I have two small queries to Professor Evans.
Yep.
See, it appears very interesting to me because I have been teaching Bayesian inference for quite some time now in our university. The fact remains that while this appears to be highly theoretical, you have supported this your findings by one illustration. Which is about the prosecutor's fallacy, taking example from uniform distribution, discrete uniform distribution. See, I have a small query in the sense the evidence here that we are going to measure is treated as the parameter.
Well,
is it the parameter of a distribution, the evidence that we are going to measure?
Well, it doesn't really matter, because as soon as you're in a proper Bayesian context, you're in the context of a full probability model. So the properties of however
you're considering the distribution, uniform distribution,
yes,
we must have drawn a random sample of size n out of say capital N.
No, it isn't strictly speaking what you would call a statistical context. It's just a probability example. But my point is that when you're a Bayesian, a proper Bayesian, you're in the context of a probability model. So the reasoning, whatever reasoning you use, has to satisfy these properties, right? It can't. It's not something separate just because it's statistical. It's something. I mean, there are aspects of statistical problems that are different, but it's just probability theory, basically.
Well, I mean to ask you whether the prior follows uniform distribution?
The probability distribution is uniform on the population, yes.
And it is the prior distribution?
Well, it's a probability distribution. It is the probability. As in a Bayesian problem, it would be the joint probability distribution for theta and x. Now, I can make that example into a statistical context like that. There's no problem with that. But that example is very simple, right? That's why I like that example.
Similarly, can we have examples from continuous probability distributions?
Yes, no problem. Okay. The Jeffreys-Lindley paradox is a good example of that, and I often present that one instead. And that's a good example where the size of the relative belief ratio or the Bayes factor, as you make a prior more and more diffuse, this is location normal, so it's continuous, the Bayes factor and the relative belief ratio go to infinity, but the evidence gets weaker and weaker.
Once again, I must thank you for a wonderful deliberation by Professor Evans, and thanks are due to all the audience, the participants. Over to Professor Satish Kumar.
Thank you, Professor Evans, for your wonderful talk. Thanks a lot. Also, we wish to thank Professor K.B. Panda for chairing the session and making this session very vibrant. Thank you so much.
Thank you so much. Thank you, Professor Evans. It's nice to see you.
Nice to see you. Thank you.
Now let us move to the next session. Arjuna, please introduce the chair and please do the further help.
Sure, sir. Good morning, good afternoon, and good evening to all the participants from around the world. We're moving on to the technical session 31 of WSTA 2023. That'll be chaired by Dr. K.S. Bhanu, Professor and former head to the Department of Statistics, Institute of Science, Nagpur, India. Dr. Bhanu has an extensive teaching experience of 37 years, during which she has guided several students in their doctoral studies and published over 60 research papers in various national and international journals. In particular, she is interested in probability theory and reliability theory. Dr. Bhanu's contributions extend beyond research and teaching. She has served as a referee for esteemed journals such as AJISA and BMMS, further establishing her prominence in the academic community. Her leadership roles are equally admirable. Dr. Bhanu has held the position of chairperson for the Board of Studies and has been a member of the Academic Council at RTM Nagpur University, India. She has also served as the in-charge director of the Institute of Science, demonstrating her administrative capabilities. Moreover, Dr. Bhanu has been actively involved as the academic head and coordinator of National Assessment and Accreditation Council, emphasizing her commitment to quality education. She is also a life member of various professional bodies, which reflects her continuous engagement and dedication towards the academic community. So on behalf of the organizing committee of WSTA 2023, I hereby extend a warm welcome to you, Dr. Bhanu, and cordially invite you to chair the session. Over to you, ma'am.
Thank you very much, Dr. Anjana, for this brief and nice introduction. At the outset, I would like to thank Professor Satish Kumar and the organizing committee for inviting me to chair this last technical session. Welcome to all the participants to the last technical session number 31 of the 8th International Webinar, WSTA 2023. Today's last session, yeah. We have two speakers here, two eminent speakers, Professor Peter and Professor Emmeline. The first speaker of today, I take pleasure in welcoming Dr. Peter Lohamander to this technical session. And this is his brief, I'll read out his brief biodata. It's a pleasure to introduce Dr. Peter Lohamander. He focuses his research on optimization, optimal control, and applications to decision problems in different sectors. Professor Lohamander was full professor of Forest Management and Economic Optimization, SLU, Faculty of Forest Sciences, Umeå, Sweden, from 2000 to 2015. Since 2015, Professor Peter is president of his own research company, Peter Lohamander Optimal Solutions. Optimization of real dynamic and stochastic decision problems, in particular via stochastic dynamic programming and stochastic dynamic control theory, has gained considerable attention in the research projects. Application areas are economics, natural resource management, forestry, logistics, global warming, bioenergy, the military, and other areas. Professor Lohamander works in all these application areas and has been actively involved in research. Today's topic is going to present on the production of apartments as a function of GNP, building costs, and population changes, statistical analysis and predictions until 2050 based on official Swedish data. It's a pleasure to welcome you here, sir, and over to you for presenting your topic, presenting your lecture.
Thank you very much, the chairman and also Chairman Professor Kumar and all the others involved in inviting me to this conference. I'm very happy to be here. Thank you very much. Today I will, as we just saw, show presentation, and I want to share my screen. Let's see. Can you see this?
No.
Now it's coming, I think. Okay, so you can see the screen?
It's okay.
Yes, yeah.
Okay. I will talk about the production of apartments as a function of GNP, building costs, and population changes. Statistical analysis and predictions until 2050 based on official Swedish data from 1975 to 2021. And first I will start with empirical background from Sweden, because the Swedish interest in this particular problem is rather big in the industry. And there is data in Sweden that has been used for this purpose. And then we'll go to generation of some hypotheses through constrained nonlinear optimization concerning how the number of constructed apartments should be affected by changes of some explaining variables. Then we'll make some statistical tests of hypotheses, and then we'll also make some conditional predictions of future numbers of constructed apartments. The empirical background comes from Sweden, and you see Sweden here in the north of the world, so to say. Here, down here we have India, but Sweden is up here. And here you see a graph from 1975 to 2021 of the number of constructed and finished apartments in Sweden. And you see that there is very, very large variation here. In the beginning, 1975, it was about 75,000 apartments per year. And then it went down to about 30,000 in 1985. Then it went up again very much. And then it went down to just above 10,000 apartments per year. And then it went up again very much up to about 50,000. So the question is it possible to understand this variation and also to control it in some simple way? Here in Sweden, we have a lot of official statistics that's available through the internet. We have Statistics Sweden, which is a very good source. Here we have one of the possible explaining factors, namely the gross national product in billion crowns per year, real values in the 2022 price level. And essentially we can see that this has been growing except for during a short period from 1990 until 1993 and from 2008 until 2009 or 2010 maybe. We have another thing which is probably also very much affecting this building of apartments in Sweden, and that's population growth. And you see here that there is a very, very large variation also in the population growth. It was fairly low in the 1975 to 1980, then it went up for a while, and then it went down, and then it went up very rapidly until about 2017. And then it went down a bit again, and then it went up. And of course, this very much depends on the immigration, partly from Afghanistan and also from Ukraine during the war and all these things. So there are many unpredicted things that may have an importance in this context. But if you just look at the population, these dramatic changes in the population growth don't show themselves very clearly. But still, of course, the population itself should also be interesting in an explaining factor when we look at the number of produced apartments. One thing which may be very important is the real building cost. You see that there is an index, and in 2022, this index has been defined as 100. And you see during the period 1975 until 1990, this was almost constant. Then it went down to about 60, and then it went up to 100. So it's been growing very rapidly from 1993 up till the present. And the growth has been from around 60 up to 100. And of course, this is dramatic change, and partly this is a result of increased administration, more complicated building rules, less area available for buildings in cities, and so on. Anyway, we'll first try to start to generate some hypotheses through constrained nonlinear optimization concerning how the number of constructed apartments should be affected by changes of some explaining variables. And in the general utility optimization problem, we simultaneously consider investments in living space, S, investments in other fundamental investments, F, and the total budget. And the utility of living space, this is an idea that it could look something like this. Here you have a function with increasing derivative, strictly positive first derivative, strictly negative second derivative, and strictly positive third derivative. This particular graph actually is what we'll look at in a few seconds in more detail. But remember that the third derivative is strictly positive. So this is the assumed functional form of the utility of living space. In other words, the utility, the marginal utility is always increasing. More space is always better. The utility of other things, such as F, other factors that are useful in life, are assumed also to have a strictly positive first derivative, at least in the beginning, and also a negative second derivative, but in fact it's assumed to be a quadratic function, so it has a unique maximum. There is no point in producing more than a particular amount of this type of commodity or investment. So here is the utility of F and S. And the question is then, if we also have a budget constraint, which we always do in reality, how should we use this budget? And can we say something about the properties of the investments in living space or in apartments as a function of the budget, based on this type of situation where we have at least two types of products that we want to invest in, or investments. And here we see that we have this budget constraint in the end of the page, and we maximize the total utility of all of these things. Okay, here is the Lagrange function of this problem. And in the optimization, we only consider interior solutions in the sense that S is strictly greater than 0, F is strictly greater than 0, and the lambda, the marginal value of the budget, the shadow price of the budget, are strictly positive. Then, according to the Karush-Kuhn-Tucker conditions, the following three simultaneous equations must be satisfied by the optimal solution. And then, in the later part of the analysis, we'll find that the optimal values of S, F, and lambda, the shadow price, really are strictly positive when they are determined from the three simultaneous equations, which confirms that the initial assumptions were correct. Okay, so here we have the three equations that give the interior optimal solution. And interior in the sense that we look at F, S, and lambda, and we want interior solutions for them. In a sense, we can also say that we are on the boundary because we use the budget. So there is no margin in the system in that sense. But anyway, from these three equations, we'll go on. Then we start with these three equations, and from 4a, we can say that lambda is what you have up here in the upper corner to the right. And from the second, 4b, we get another expression for lambda, and then we can say that S is this expression of F and the parameters. Then we can utilize the third equation for C, and we can input what we had in the earlier page. And then we have an expression of F as a function of the parameters, including B, the budget. And then we can transform this equation, the third equation that we had, to what we have on this page. And we see that we will soon come to a quadratic equation that we can use to determine the optimal value of F. So here on page 20, we see in the bottom that we are approaching this quadratic equation of F. And here we have this, the second equation, the second row. You see F2 minus something times F plus some constant here equals 0. And from this, we can determine the optimal value of F from the three equations, or from the parameters, if you want. And of course, there are two solutions, one positive and one negative. Sign can be used before the square root. So two different real solutions of F, denoted F1 and F2, are found. F1 is a solution where the negative sign is selected before the square root, and F2 is obtained if the positive sign is used. One of these F values, F1, will satisfy the budget constraint, and F1 contributes to the maximization of the utility function. F2 does not satisfy the budget constraint and can be shown to lead to an unfeasible minimum. Now, we may wonder why this is important. Well, we come to this soon. The optimization problem contains a strictly concave objective function and a linear constraint. If the first order optimum conditions are satisfied and the solution is feasible, the solution is a unique and feasible maximum. The optimal value of S can now be found via F equals F1 and the parameters. Then the shadow price of the budget can be derived, the lambda, and also the optimal value of U the utility is found through the parameters F1 and S. We can input this in a small computer program. This is written in Lingo. So here we have a computer code with numerical specification of the optimization problem. And in the end here, we also have the analytical solution that we just found. And if you run it, we get some values, but you can compare them, and they are the same from the numerical version and from the analytical version, which indicates that they are probably true, both of them. Then we can calculate, using the same equations, we can calculate the optimal values of F and S, where the optimal value of S is here. And this is really what we're interested in this context, because we wanted to look at the investment in living space in apartments as a function of the budget. We had the budget, we had the gross national product. And you see that this is strictly convex. One can do this more explicitly, analytically, but if you want to, but it's easier to see the main conclusion this way. So this is strictly positive. So if the budget increases or if the GMP increases, we should expect an exponential, more or less, growth of the